Hello there, and welcome to the Sleepy Science Channel. Tonight, we are drifting into the ancient and often hidden world of geology. It is the story of Earth's past, written in pressure, heat, and immense spans of time. Beneath your feet, the world is in a state of constant motion. Mountains rise, oceans form, and rivers carve the planet into deep valleys and majestic canyons. Even the simple stones you see around you can carry memories of vanished seas, ancient deserts, and atmospheres that no longer exist. As you listen, imagine the planet as a slow workshop, where crystals grow in total darkness, and magma cools into unusual landscapes. Even the ground you stand on is slowly morphing into something new, and ancient fossils sit in silence, waiting patiently for someone to come and discover their secrets. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is relax. Let your shoulders soften and allow your eyes to grow heavy. And as you get settled in, notice the day begin to gently fade away as we explore our fascinating planet together. Let's begin. If Earth were the size of an apple, its crust would be thinner than the apple's skin. When you hold an apple, imagine its glossy surface as the crust of the Earth. That thin outer shell beneath our feet is fragile compared to the immense planet it covers. Beneath it lies a vast mantle of hot, shifting rock that churns slowly, like an endless ocean of stone. The crust carries continents, oceans, and all the delicate life we know, yet compared to Earth's size, it is almost unimaginably thin. If you could slice the planet open like fruit, our mountains and oceans would be little more than wrinkles on its surface. Beneath them, the mantle moves with slow, steady currents that drive the continents themselves. It is humbling to realize how delicate our world truly is, balanced on this narrow skin of rock. Everything we have ever built, from cities to civilizations, rests on a shell no thicker, proportionally, than an apple's peel. Granite once flowed like molten rivers deep underground. Long before it hardened into the rugged stone we see today, granite was alive with heat. Deep within the Earth's crust, molten magma gathered in hidden chambers, moving like slow rivers of fire. Over millions of years, it cooled and crystallized into the familiar speckled rock that now forms the hearts of mountains. Each grain of quartz and feldspar once shimmered in a molten glow before solidifying forever. When you run your fingers over granite, you are touching the cooled remains of that ancient flow, frozen in time. Many of the world's great landscapes, from Yosemite's cliffs to the Scottish Highlands, were shaped by granite rising and solidifying below the surface. It holds within it the patience of the planet itself, a reminder that what appears solid today was once liquid light, slowly transforming beneath unimaginable pressure into something enduring and eternal. Diamonds can form in a heartbeat when conditions are right. Most diamonds take billions of years to grow deep within the mantle, born from carbon crushed and heated beyond imagination. But nature can be unpredictable. Under the most extreme pressures, carbon can rearrange itself into diamond almost instantly. These sudden transformations happen miles beneath the surface, where temperatures are hotter than molten metal and pressures exceed anything humans can replicate for beta long. When volcanic eruptions bring these gems upward, they travel through narrow pipes of rock called kimberlites, carrying a story from the depths of Earth's creation. Each diamond you see, no matter how small, once existed in darkness and heat so fierce it could melt steel. Whether formed slowly or in a geological heartbeat, each crystal captures a moment when ordinary carbon became extraordinary. They are nature's perfect record of transformation, born from chaos and pressure, rising toward light through the very bones of the planet. Some mountains are still rising faster than your fingernails grow. Mountains appear eternal, but they are alive with movement. Deep beneath the surface, tectonic plates push and collide, forcing rock upward inch by inch. In the Himalayas and parts of the Andes, this slow collision is still lifting peaks faster than your fingernails grow. What feels solid is actually part of an endless cycle of uplift and erosion. Wind, water, and ice tear mountains down grain by grain, while forces deep below rebuild them in a rhythm that has played out for hundreds of millions of years. A mountain may seem motionless, but if you could speed up time, you would see it breathe, swelling upward as continents collide. The stone beneath your feet may once have rested on the ocean floor, carried skyward over epochs. These giants remind us that Earth is not still at all, but in constant motion, reshaping itself even as we sleep. The ground beneath you never stops moving. Even when the world around you feels calm and steady, the surface beneath your feet is always on a slow and silent journey. The outer shell of our planet is made of enormous slabs of solid rock that glide across a deeper layer that behaves almost like softened stone. This motion is far too slow for your senses to detect, yet over immense spans of time, it completely reshapes the surface of Earth. Mountains rise, oceans widen, valleys open, and continents drift to new places. Every familiar landscape owes its shape to this gentle, persistent motion. You can imagine the ground as part of a giant puzzle that is always rearranging itself, guided by deep forces coming from the warm interior of the planet. Although we experience earthquakes and volcanic activity as sudden events, they are surface hints of a restless world always in motion. The quiet truth is that Earth never holds still, and the land you know is already on its way to somewhere new. Earth's crust is split into giant interlocking pieces. The outermost layer of our planet is not a single unbroken shell, but a mosaic of immense rocky sections that fit together like the surface of a cracked eggshell. These pieces are called plates, and each one spans enormous distances, carrying continents, oceans, or both. The boundaries between them are sites of constant change, where the plates meet, slide, separate, or dive beneath one another. Even though the crust feels unyielding and strong, it is thin compared to the layers below, and it drifts on top of a deeper zone that is much softer over long periods of time. These plates make sense of so many features around us, from deep ocean trenches to soaring mountains. Their motions determine where volcanoes appear, how coastlines evolve, and why earthquakes occur in certain regions. When you picture the entire planet covered with these colossal floating pieces, you begin to sense the graceful complexity of Earth as a living, shifting world. Tectonic plates drift at the speed of growing fingernails. The immense slabs that carry continents and oceans move at a pace so gentle it is almost poetic. On average, they drift only as quickly as your fingernails grow. This slow speed seems insignificant in everyday life, yet across millions of years it changes everything. Entire oceans can open or close. Ranges of mountains can rise where none existed before. Islands can collide with continents or drift across vast stretches of open water. The reason we can measure this drifting so precisely is that scientists use sensitive positioning instruments anchored across the globe, watching the plates shift with exquisite accuracy. The slow movement hides a tremendous amount of energy, since these plates are incredibly massive. Their motion guides the history of life, the flow of water, the distribution of minerals, and the shape of every corner of the planet. Beneath the quiet of daily life, the Earth is always gliding forward in a slow, patient dance. Continents travel across the planet like slow rafts. The continents we know, with all their mountains, forests, deserts, and cities, are carried on the backs of plates that drift through time. Each continent behaves almost like a raft made of thicker and lighter rock that floats above the denser material of the mantle beneath. These continental blocks have wandered widely. Some once touched places they are now far from. Others joined together to build supercontinents, only to drift apart again. The movement is steady rather than sudden, yet over immense timescales, continents can occupy positions that drastically affect climate, ocean currents, and the unfolding of life. When a continent passes over a hotspot, it may sprout chains of volcanoes. When two collide, the land can crumple upward into mountain ranges. Even quiet landscapes carry memories of these slow voyages. As you look at a world map, you can imagine every landmass slowly drifting, circling, and shifting as part of a vast and ancient journey. The Himalayas are still growing taller every single year. High above the clouds, the Himalayas continue to rise. Their growth began around 50 million years ago, when the Indian plate collided with the Eurasian plate, crumpling the crust like folded fabric. That collision is still happening, pushing the mountains upward by a few millimeters each year. The peaks may appear timeless, but their summits climb steadily toward the sky, even as wind and glaciers carve them down. Every tremor in the region, every deep earthquake, is a whisper of that immense pressure still at work. These mountains are not relics of the past, but the living result of an ongoing collision that began before humans existed. The same collision that built Everest continues to reshape the land beneath millions of people. In their silent rise, the Himalayas remind us that Earth's power is patient, relentless, and always in motion, sculpting continents as easily as clay. Continents drift as fast as your hair grows. If you were to measure the movement of a continent, it would advance about as quickly as your hair lengthens in a month. Yet over geological time, that small pace reshapes the entire face of the planet. Continents slide on top of the mantle, carried by convection currents deep within Earth. The Atlantic Ocean grows a little wider each year, while the Pacific slowly shrinks. In millions of years, familiar maps will be unrecognizable. Africa will move closer to Europe, Australia will edge north, and the continents may one day merge again into a single giant landmass. This slow drift connects the fossils of ancient creatures found oceans apart and explains why mountain ranges on separate continents share the same bow. Origins. The ground feels solid, but it is part of a grand, restless voyage that has never stopped since the planet was born. The ocean floor is younger than most of the continents. Beneath the waves lies a hidden world in constant renewal. While the continents hold rocks billions of years old, the seafloor is surprisingly young. Along mid-ocean ridges, molten rock rises, cools, and forms new crust that slowly spreads outward. As it drifts, it eventually sinks back into the mantle at deep ocean trenches where one plate slides beneath another. This recycling means no ocean crust lasts longer than about 200 million years, a fleeting moment in Earth's long history. The continents, by contrast, are ancient survivors that have floated above the cycle of destruction. If you could see the planet's surface over time, you would watch the oceans form and vanish like the rhythm of a breath. The seafloor is the planet's heartbeat, renewing itself endlessly, a reminder that even the deepest, darkest places on Earth are alive with motion and change. Magnetic stripes on the seafloor record Earth's ancient flips. Across the vast plains of the ocean floor, the rocks are patterned like a barcode. These alternating magnetic stripes mark times when Earth's magnetic field reversed direction, with north and south swapping places. As new crust forms at mid-ocean ridges, Minerals within the lava align with the planet's magnetic field before they cool and lock in that direction. Millions of years later, another reversal leaves the next band pointing the opposite way. By reading these stripes, scientists can trace the history of magnetic flips stretching back tens of millions of years. This discovery was one of the keys that proved the theory of plate tectonics, showing how the seafloor spreads outward over time. Beneath the oceans lies not chaos, but a perfectly ordered record of the planet's invisible forces, written in stone by magnetism, heat, and the slow pulse of geological time. Ocean floors are created at spreading ridges. Deep beneath the oceans are long underwater mountain chains where new crust is born. At these spreading ridges, molten material from the mantle rises upward through cracks created by the separation of plates. As this material cools, it forms fresh ocean floor that steadily moves away from the ridge in opposite directions. This process creates symmetrical patterns in the crust, including magnetic stripes that record the history of Earth's magnetic field. The ridges are dynamic places, with volcanic activity that continually replenishes the sea floor. Hydrothermal vents flourish along these regions, hosting strange and beautiful ecosystems that thrive in heated water rich with minerals. Although the ridges are hidden beneath deep oceans, they are among the most active features on the planet. The creation of new ocean crust is part of a continuous cycle that shapes the seafloor and drives the slow expansion of ocean basins over geological time. The Pacific plate is shrinking while others expand. Among the many plates covering Earth, the Pacific plate is unique because it is gradually decreasing in size. This shrinking happens as it dives beneath surrounding plates along long arcs of subduction zones. While the Pacific plate diminishes, other plates grow as new crust forms along their spreading boundaries. This creates an intricate balance where Earth's surface area remains constant, even though individual plates change shape and size. The Pacific plate plays a major role in global geology because its boundaries host intense volcanic and seismic activity. Many of the world's most active volcanoes sit along its edges. As the plate continues to retreat into the mantle, new geological features emerge and older ones disappear. This ongoing transformation shows that plates are not static, but living components of a restless planet where creation and destruction are always intertwined. Earthquakes reveal the boundaries of hidden plates. Although plates themselves are difficult to observe directly, their edges announce themselves through patterns of earthquakes. When plates shift, grind, or collide, stress builds along faults until the rocks suddenly slip. These slips send waves through the ground that scientists can record with sensitive instruments. By mapping where earthquakes occur, researchers can trace the outlines of known plates and even discover new or unexpected boundaries. These seismic maps often reveal structures far beneath the surface, including deep faults and zones where slabs are descending into the mantle. Earthquakes provide one of the clearest windows into the dynamic nature of our planet. Even though the events can be frightening, they also carry valuable information about how Earth works. Each tremor is a reminder that the ground is alive with continual motion, and that the planet's surface is shaped by forces operating on scales far larger than any one lifetime. The deepest trenches form where plates dive downward. In a few extraordinary places, the ocean floor plunges into narrow chasms that are deeper than any other locations on the planet. These trenches mark sites where one plate bends and sinks beneath another in a process known as subduction. The bending creates an arc of ocean floor that descends into the mantle, forming a long and shadowed depression. Life in these trenches persists under pressures so immense they would crush most organisms. The rocks here are transformed by heat, pressure, and the circulation of chemical-rich fluids. Above the trenches, Arcs of volcanoes often rise on the overriding plate. These features highlight the power of descending slabs to melt material deep within the Earth. The trenches act as portals where crust is returned to the interior, continuing a cycle that has been operating for countless ages. They are among the most remote and mysterious environments on Earth, hiding worlds we have barely begun to explore. Rocks can actually become magnets after cooling from lava. When molten rock cools on the surface of the Earth, something extraordinary happens. Tiny particles of iron and nickel inside the rock align themselves with the planet's magnetic field, like invisible compass needles. Once the lava cools and hardens, those magnetic directions are locked in forever, preserving a record of the magnetic field's orientation at that moment in time. Scientists study these natural magnets to map the shifting history of the Earth's poles. Every reversal, every wandering movement of magnetic north is captured in stone, frozen as the planet's molten skin solidifies. These magnetic fingerprints are part of how geologists proved that continents drift and seafloors spread. In every volcanic rock lies a silent record of Earth's magnetic pulse, whispering clues about ancient directions and the invisible forces that shape the space. Around our world, the planet's memory is magnetic, written in the iron heart of stone. Every volcano on Earth connects to a hidden magma chamber. Far below the surface, each volcano has a heart that beats with molten fire. These underground chambers of magma are vast reservoirs of liquid rock, feeding eruptions that can reshape landscapes and change climates. Some chambers are small and shallow, others immense and deep, reaching far beneath the crust. Inside them, crystals form, gases rise, and pressure builds until the rock above can no longer hold it back. Then, with staggering power, the chamber vents its fury through cracks and vents, pouring lava and ash across the world above. Between eruptions, these reservoirs remain hidden, slowly refilling and evolving. Modern technology allows scientists to glimpse their shapes using seismic waves, like ultrasound for the Earth. Each volcano is part of this deep, breathing network. A reminder that beneath calm fields and sleeping mountains, there are vast, glowing worlds of molten stone waiting quietly below. Some volcanic eruptions last for hundreds of thousands of years. Not all eruptions are sudden, explosive moments in time. Some are patient and relentless, flowing for ages beyond imagination. When mantle plumes release massive amounts of magma, the result can be a flood basalt, a vast outpouring of lava that continues for hundreds of thousands of years. These eruptions can bury entire regions beneath miles of solid rock. The Deccan traps in India and the Siberian traps in Russia are enormous relics of such ancient fire. During their reign, they released enough gas and heat to alter the planet's climate and change the course of life itself. Standing on one of these hardened lava plains today, it is hard to imagine the molten rivers that once stretched to every horizon. They remind us that sometimes Earth reshapes itself not with explosions, but with the slow, unstoppable rhythm of fire, spreading endlessly beneath the open sky. Basalt covers most of the ocean floor in dark, dense layers. If you could walk across the bottom of the sea, every step would land on basalt, a dark, heavy rock born of fire. It forms when molten material from the mantle erupts along mid-ocean ridges and cools quickly in contact with seawater. The result is a vast, unbroken crust stretching across the ocean basins like the planet's armor. Unlike the lighter rocks of the continents, basalt is rich in iron and magnesium, giving it its deep color and weight. Its solid layers continually renew as the seafloor spreads outward, while old sections sink back into the mantle and melt again. Each square inch of the ocean floor has been part of this endless cycle of creation and destruction. Beneath the waves, basalt holds the history of Earth's most patient movements, layer upon layer of cooled magma, forming the quiet foundation of the world's oceans. Entire land masses can tear themselves apart. Continents may look permanent and immovable, yet deep forces can stretch and weaken them until they break into separate pieces. This tearing happens when mantle currents pull on the base of the crust, or when plates around a continent shift in ways that create tension. As the land stretches, it fractures into a patchwork of faults that slowly drift away from one another. Lakes may form along these faults as the land lowers, and volcanic activity can rise where the crust becomes thin enough for magma to reach the surface. In time, the stretching can widen so much that seawater floods in, creating a new coastline. This is how enormous regions that were once joined can end up thousands of miles apart. Geologists can trace the scars of ancient continental splits by studying matching rock layers and fossil evidence along distant shores. These separations reveal that continents are not rigid, but living landscapes shaped by deep forces acting over unimaginable spans of time. Subduction recycles the crust back into the mantle. One of the most powerful processes on Earth occurs where a plate sinks downward into the deeper interior of the planet. This descent, known as subduction, pulls surface rock into a realm of enormous heat and pressure. As a slab moves downward, it releases water and other compounds carried from the ocean floor. These materials help melt portions of the overlying mantle, generating magma that may rise to feed volcanoes. Meanwhile, the slab itself continues its journey into greater depths, gradually transforming into new kinds of rock as it encounters changing temperatures and pressures. Over millions of years, this recycled material becomes part of the mantle that drives plate motion from below. Without subduction, old crust would accumulate on the surface and Earth would lose its ability to refresh and remake itself. The recycling of the crust is essential for maintaining a dynamic planet, and it is one of the driving engines behind the continuous evolution of our world. Volcano chains mark the tracks of moving plates. Scattered along the surface of Earth are remarkable lines of volcanoes that trace the slow migration of entire plates. These volcanic chains form when a plate moves over a stationary hotspot deep within the mantle. As the plate drifts, magma rises through the crust at different points along the plate's path, creating volcano after volcano in a long progression. Older volcanoes become extinct as they drift away from the hotspot, while new ones form above the rising plume. This process creates chains of islands or mountain peaks that record the direction and speed of plate motion. By studying these chains, scientists can reconstruct the history of a plate's journey across vast stretches of time. Some volcanoes in these chains rise from the sea floor to fall entire island groups, while others create long mountainous ridges on land. Each chain is a natural timeline written in stone, showing how continents and oceans shift through the ages. The Ring of Fire is a global necklace of volcanoes. Encircling the Pacific Ocean is a sweeping arc of volcanic activity known as the Ring of Fire. This region contains the majority of Earth's active volcanoes, forming a vast chain shaped by the boundaries of the Pacific Plate. Along these edges, the plate dives beneath neighboring plates, producing intense heat and melting that fuel frequent eruptions. The Ring of Fire is also one of the most earthquake-prone areas on Earth, since subduction zones store and release enormous amounts of energy. The volcanoes here range from tall stratovolcanoes that dominate their landscapes to underwater peaks hidden beneath the waves. Many of these volcanoes have shaped human history, depositing fertile soils, falling islands, and sometimes unleashing powerful eruptions. The Ring of Fire is a vivid reminder that the edges of plates are among the most dynamic regions on the planet, constantly reshaped by forces rising from deep Ka. Within Earth's interior, pillow lava freezes in shapes that look like underwater balloons. When lava erupts beneath the ocean, it cools so fast that its outer layer hardens instantly, while molten rock still pushes from within. This strange process creates rounded shapes that resemble pillows or bubbles stacked upon each other. These smooth, bulbous formations, called pillow lava, can cover entire stretches of the seafloor. Each pillow is a snapshot of fiery motion frozen in an instant, showing how molten rock interacts with cold seawater. When explorers find pillow lava on land, it tells them that the area was once deep underwater. The sight of it is eerie and beautiful, as though the stone itself still remembers flowing like liquid before being sealed by the chill of the sea. These shapes are geological sculptures of time, proof that even in the dark, crushing depths, the planet's creative forces are always alive and at work. Obsidian is volcanic glass, cooled in an instant. In moments of explosive eruption, lava can cool so rapidly that crystals never form at all. The result is obsidian, a natural glass that gleams with dark beauty. It is smooth, sharp, and reflective, formed when molten rock meets cold air or water and solidifies almost instantly. For thousands of years, humans have prized it for its perfect edges, crafting blades, tools, and ornaments. Yet behind its mirror-like surface lies a story of extreme change. Molten fire arrested mid-motion, heat transformed into fragility. Obsidian breaks easily, but along the break, it reveals stunning curved patterns called conchoidal fractures, as if each fracture remembers the flow of the original paths. Lava. This glassy rock stands as one of geology's most dramatic contrasts. Born in violence, yet perfectly still, fragile yet ageless, a piece of fire caught Ka, forever in the stillness of stone. Some rocks preserve bubbles of Earth's ancient atmosphere. Trapped within the tiniest hollows of rock, scientists have discovered microscopic bubbles of air that have survived for millions of years. These preserved pockets are like time capsules, sealing the chemical signature of the atmosphere from ages long past. By studying them, researchers can learn what gases once filled the skies, how much oxygen existed, how much carbon dioxide warmed the planet, and how volcanic activity or life itself changed the balance. Some of these bubbles formed in cooling lava, others within sediments or ice. Each one contains an echo of an ancient breath, a ghost of the air that once surrounded early forests, giant reptiles, or even the first life to breathe. To hold such a rock is to hold a fragment of vanished sky, a delicate record of the ever-changing air that connects all living things across the long history of Earth. There are mountains higher than Everest hidden beneath the sea. Far below the surface of the oceans lie mountain ranges that dwarf the world's highest peaks. Along the mid-ocean ridges, immense chains of volcanic mountains stretch for tens of thousands of miles, rising higher from their base to their crest than Everest does, above sea level. These submarine ranges are mostly unseen, shrouded in darkness and immense pressure, yet they are among the most active regions on Earth. Lava continually emerges from fissures, building new peaks and valleys in slow, steady motion. The tallest of these hidden giants, such as Mauna Kea when measured from its base beneath the sea, surpasses even the great Himalayan summits. They are reminders that much of Earth's beauty and grandeur lies unseen beneath the waves. Vast, silent kingdoms of rock that grow and shift in darkness, shaping the world from below without a single glimpse of the sun. Continental crust floats higher than oceanic crust. The continents rise above the oceans because the rock beneath them is made of lighter material that floats higher on the mantle than the denser rock beneath the sea floor. This difference in buoyancy means that continents stand tall while ocean basins form deep depressions. Continental crust is thicker and composed of minerals rich in lighter elements, making it less dense than the dark volcanic rock that forms oceanic crust. Because of this, continents act like large floating platforms that resist being pushed downward. When plates collide, the lighter continental blocks often rise, while the heavier oceanic plates sink. This contrast shapes the structure of Earth's surface and influences how the planet evolves. As continents drift, they carry their unique buoyancy with them, rising above the oceans like massive geological rafts. This natural flotation effect also helps preserve ancient crust, allowing continents to hold some of the oldest rocks on the planet. Plates carry ancient magmatism frozen into rocks. When molten rock cools at the surface or beneath the ocean, minerals within it lock into place and record the direction of Earth's magnetic field at that moment. These magnetic signatures remain preserved in the rock, even as plates move across the globe. By measuring these magnetic traces, scientists can determine where rocks originally formed and how far they have traveled. This allows researchers to reconstruct ancient continental positions with remarkable accuracy. The magnetic record is especially vivid on the ocean floor, where stripes of rock alternate in polarity as Earth's magnetic field flips over long periods of time. These stripes form matching patterns on either side of spreading ridges, creating a detailed timeline of plate movement. The frozen magnetism within the crust is like a silent compass left by Earth's past, offering clues to how continents have wandered and how the planet's magnetic field has shifted through deep time. The continents have assembled and broken apart many times. Long before the landscapes we know existed, the continents repeatedly gathered together into enormous supercontinents and then drifted apart again. This cycle is driven by the slow movement of plates that bring land masses together through collisions and later separate them as new oceans open. Each supercontinent forms a vast and unique world with its own climate patterns, ocean currents, and ecosystems. Over millions of years, heat builds under these giant land masses, eventually weakening their foundations and causing them to crack and split. The fragments then begin new journeys across the globe, sometimes joining other continents to form new supercontinents in future ages. Evidence of these ancient unions is found in matching rock formations, similar mountain ranges, and shared fossils across continents now separated by wide oceans. The continual assembly and breakup of supercontinents reveals that Earth's surface is ever-changing, shaped by cycles far larger and longer than human history can comprehend. Pangaea was only one of many supercontinents. Most people hear the name Pangaea and imagine it as the first and only time all the continents were joined. Yet the history of Earth stretches far deeper, and in that vast timeline, our world has assembled several enormous supercontinents that rose and fell long before Pangaea ever existed. Each one gathered almost all of Earth's land into a single colossal mass, forming ancient worlds with climates very different from today. Rivers flowed across endless interior plains. Coastlines were limited to distant edges. Winds carried moisture across thousands of miles of unbroken land. Before Pangaea came supercontinents such as Rodinia, Nuna, and others whose names echo like distant memories in geological research. They formed, lasted for millions upon millions of years, and then slowly tore themselves apart as heat built beneath their foundations. Their fragments drifted across the globe and eventually collided again to create new supercontinents in later ages. When scientists reconstruct these ancient landscapes using rocks and minerals that preserve their original positions, it becomes clear that Earth's continents, participants in a recurring cycle of gathering and dispersal. The world we know is only the latest chapter in a story told many times before. Earth's deepest point is nearly as far below sea level as planes fly above it. At the heart of the Pacific Ocean lies the Mariana Trench, a chasm so deep that if Mount Everest were dropped into it, the peak would still be submerged by more than a mile of water. The trench's deepest known point, the Challenger Deep, reaches nearly 7 miles beneath the surface, almost the same distance as passenger planes travel above the Earth. Down there, the pressure is immense, crushing enough to flatten steel. Yet even in that darkness, life endures. Strange organisms glow in the black water, thriving among mineral-rich sediments. The trench marks a subduction zone, where one tectonic plate slips beneath another and sinks back into the mantle. It is not just the lowest point on Earth, but one of the planet's great engines of renewal. It reminds us how small the visible world is compared to the vastness hidden below. The planet hums with micro-earthquakes you never feel. Even when the ground seems utterly still, it is vibrating with the faint murmurs of constant motion. Across the planet, thousands of tiny quakes ripple through the crust each day, too small for humans to detect. These micro-earthquakes release little bursts of energy as the Earth adjusts to stresses deep below. Scientists use sensitive instruments to record these whispers, creating detailed maps of shifting faults and hidden magma flows. Together, they form a background hum that never ceases, the quiet pulse of a living planet. This ceaseless trembling tells geologists where faults are creeping, where pressure is building, and where volcanic systems are stirring. The stillness of the world is an illusion beneath every mountain, forest, and sea. The planet moves in countless small ways, sighing, cracking, and settling in slow, secret rhythms that carry the story of Earth's restless heart. Earthquakes can make entire rivers run backward. When the ground shakes with enough force, the landscape itself can change direction. During powerful earthquakes, the land can tilt or shift so abruptly that rivers are forced to reverse their flow. This rare phenomenon has been recorded in events like the Great New Madrid earthquakes of the early 19th century, when sections of the Mississippi River temporarily flowed upstream. The sudden movement of the crust can raise one side of a fault or drop another, creating natural dams or lowering valleys. For a brief moment, the power of Earth's internal forces can overcome the steady pull of gravity that guides every drop of water. When balance returns, the rivers carve new paths through changed terrain. These moments reveal the sheer strength of geological motion, showing that even something as constant and ancient as a river can be turned backward by the planet's deep jar. Hidden forces. Some faults creep silently without any shaking at all. Not all tectonic motion announces itself with quakes or destruction. Along certain sections of faults, the crust slides so slowly and evenly that there is no noticeable shaking at the surface. This quiet movement, known as fault creep, relieves pressure in small, continuous increments. It is invisible to anyone standing above but measurable through instruments that can detect motion of just a few millimeters per year. Some faults in California and Turkey move this way, gliding smoothly while neighboring sections remain locked and tense. The creeping portions may prevent larger quakes from forming in those regions, yet they also transfer stress elsewhere. This subtle dance between tension and release is part of the planet's constant balancing act. Even without drama or noise, the ground beneath us is shifting, whispering in slow motion as the Earth adjusts itself grain by grain across the ages. Earth's core is hotter than the surface of the Sun. At the very center of the planet lies a sphere of molten and solid metal under pressures beyond comprehension. The temperatures there reach more than 9,000 degrees Fahrenheit, rivaling and even exceeding the visible surface of the Sun. This immense heat is the leftover energy from Earth's formation, combined with the constant decay of radioactive elements deep inside. Though we will never see it directly, the core drives everything from volcanic eruptions to the magnetic field that shields life from cosmic radiation. Its motion churns like a dynamo, generating invisible lines of force that extend far into space. The inner core, solid iron, rotates slightly faster than the planet above it, while the outer layer flows in liquid form. This hidden furnace is the beating heart of the Earth, the power source that keeps our world alive with movement, warmth, and quiet resilience. There may be a whole ocean hidden deep inside the mantle. Far beneath the crust, where rock glows with heat and pressure, scientists have found minerals containing vast amounts of trapped water. These discoveries suggest that an entire ocean's worth of water may exist hundreds of miles below the surface, bound within crystal structures rather than flowing crème brûlée. Freely. If released, this hidden reservoir could fill the world's oceans multiple times over. It is not a sea in the familiar sense, but a deep, secret storage of the same substance that sustains all life. The movement of tectonic plates may carry water downward into this realm, only for it to return through volcanic eruptions and rising plumes of molten rock. This unseen cycle could be one of the keys to understanding why Earth has oceans at all. Even in the deepest stone, water finds a way to endure, waiting patiently inside the planet's mantle for eons. Crystals can grow larger than a person inside underground caves. In the quiet darkness beneath the deserts of northern Mexico lies a cathedral of crystal. The Cave of the Crystals, buried deep within a silver mine, holds translucent gypsum blades stretching more than 30 feet long. Each one took hundreds of thousands of years to grow in perfect stillness, nourished by hot, mineral-rich water that once filled the chamber. When the water drained away, the crystals remained, gleaming like frozen moonlight in the humid air. Entering the cave is like stepping into another world, one built not of rock and fire, but of slow, delicate perfection. The conditions required to create such formations are almost impossibly rare, balanced between heat, saturation, and time. These enormous crystals remind us that even the hardest materials on Earth can move and change, given patience enough. They are the planet's most beautiful expression of stillness shaped by time. Giant gypsum crystals shimmer in Mexico's Cave of the Crystals. Deep below the surface, where heat and humidity can melt equipment in minutes, lies one of the most breathtaking sights ever found. The Cave of the Crystals, discovered by miners in the year 2000, contains gypsum formations so large they resemble pillars of light. Some weigh dozens of tons and stretch across the chamber like colossal glass beams. The crystals formed when mineral-rich groundwater remained at a steady temperature for hundreds of thousands of years, allowing molecules to arrange themselves with perfect symmetry. When the cave was drained, the growth stopped, freezing the scene forever. The atmosphere is so hot and thick that no one can stay inside for long. Yet for brief moments, explorers have walked among the shining walls of translucent stone. It is a vision of geological art, created not by hands, but by time, water, and a quiet chemistry of the Earth itself. Salt domes can pierce through rock like slow-motion explosions. In regions where thick layers of ancient salt lie buried beneath heavier rock, a strange and powerful phenomenon can occur. Over millions of years, the salt begins to flow upward, pushed by pressure from the surrounding layers. Although solid, salt behaves like a viscous fluid under great stress. It rises through the rock above, bending and breaking it, creating dome-shaped structures that can reach miles in height. These salt domes sometimes trap oil and gas, forming reservoirs that have shaped entire industries. From above, they appear as gentle swells in the landscape, but beneath the surface, they are vast pillars of slow movement, reshaping the earth in silence. Each one tells the story of ancient seas that evaporated long ago, leaving behind minerals that continue to climb skyward, proof that even solid ground is capable of flowing like a patient, unstoppable tide. Petrified wood is actually quartz, atom by atom. What looks like a fallen tree turned to stone is something far stranger and more delicate. When a tree is buried by volcanic ash or sediment, minerals carried by groundwater seep into its cells. Over thousands of years, each tiny structure of wood is replaced molecule by molecule with quartz, preserving every ring, knot, and fiber in perfect detail. The result is a fossil that still looks like wood, but feels cold and heady to the touch. Sometimes trace elements color it in hues of red, yellow, or green, painting a natural artwork within its grain. Holding a piece of petrified wood is like holding a memory made solid, a living thing transformed into crystal by the patience of time. It is nature's way of saying that nothing truly disappears, it only changes form, keeping the story of life locked within stone. Coal began as ancient forests trapped in swampy worlds. Long before humans walked the earth, vast tropical forests covered much of the land. When these forests died, their fallen trunks and leaves sank into oxygen-poor swamps, where decay slowed to a crawl. Layer upon layer of plant matter built up, pressing down under its own weight. Over millions of years, heat and pressure transformed that buried organic material into coal, a dense rock made of concentrated carbon. Within every piece of it lies the energy of sunlight captured by plants from a prehistoric sky. Burning coal releases that ancient sunlight once more, a ghostly return of energy stored for eons. The process that created it tells a story of transformation, where life became stone and sunlight became fuel. Every lunk of coal carries the imprint of ancient forests, the breath of a vanished world condensed into dark, glittering veins beneath our modern one. Oil comes from the buried remains of ancient plankton. Long before dinosaurs roamed the land, the oceans were filled with microscopic life. When those tiny organisms died, they sank to the seafloor and mixed with mud, forming thick layers of organic sediment. Over millions of years, the weight of the ocean pressed them deeper, heating and compressing them until their carbon-rich remains transformed into liquid hydrocarbons. Trapped within porous rock, these ancient molecules became the oil that powers modern civilization. Every drop we burn once drifted through a primordial sea, gathering sunlight through the simplest forms of life. In a way, the energy that fuels our world is the sunlight of Earth's deep past, stored beneath miles of stone. The story of oil is not only one of geology, but of biology, chemistry, and time, woven together in the quiet darkness below the surface, waiting for discovery. Every grain of sand tells the story of a vanished mountain. Each tiny grain of sand once belonged to something far greater. Long before it rested on a beach or desert, it was part of a towering mountain or an ancient bedrock plain. Over millions of years, wind, water, and ice ground that rock down to its smallest possible pieces, carrying them across rivers and seas. A single grain might have tumbled through glaciers, flowed down canyons, or drifted across oceans before coming to rest. Under a microscope, its shape and composition reveal the kind of rock it came from and the journey it took. Some grains still shine with fragments of quartz from ancient continents, others are volcanic shards from fiery eruptions long past. Every handful of sand is a storybook of time, a collection of broken worlds reduced to glittering fragments that will, one day, be pressed back into stone and start the cycle again. Desert sand can sing with a low musical note when it moves. In a few rare deserts, the shifting of sand dunes creates a deep, resonant hum that can last for minutes. These singing dunes, found in places like Morocco, Chile, and the Arabian Peninsula, produce notes so pure they sound like the voice of the earth itself. The sound comes from countless grains sliding and colliding in unison, vibrating at a frequency between a cello's tone and a thunderous roar. Scientists believe the grains must be nearly uniform in size and perfectly dry for this effect to occur. Travelers describe the experience as haunting, as though the dunes are breathing or speaking. Ancient peoples often treated these sounds as mystical, believing they came from hidden spirits or gods of the desert. In truth, it is physics and friction working together, turning the landscape into a natural instrument that sings the slow, patient music of the shifting earth. Some beaches are made entirely of tiny shells. Along certain coastlines, the sand beneath your feet was not carved from stone, but built by life. Over centuries, the shells of countless tiny marine creatures, such as mollusks and foraminifera, have broken down into fragments so fine they resemble peen, powdered ivory. These biological sands can gleam white under the sun, glimmer pink from crushed coral, or even shimmer golden from the remains of microscopic algae. Each grain is a fragment of something that once lived, a piece of the ocean's past returned to the shore. Walking along such a beach is like stepping through the ruins of invisible kingdoms, where waves and tides have turned the architecture of life into a soft, shifting tapestry. The world's most famous white beaches, like those in the Bahamas and Maldives, are living evidence that time and biology can build beauty as surely as rock and fire. There are black, green, pink, and even red sands on Earth. Not all beaches shimmer with gold or white. Some are black from cooled lava, others green from olivine crystals, pink from coral, or red from eroded volcanic rock. Each color tells a geological story about its source and the forces that shaped it. Black sands often line volcanic islands, formed when molten lava met the sea and shattered into tiny glassy fragments. Green beaches appear where rare minerals from deep within the mantle wash ashore. Pink hues come from crushed shells and coral mixed with white sand, while red sands are tinted by iron-rich rock, oxidized over time. Walking these colorful shores is like wandering through the palette of the planet itself. Every wave rearranges grains that carry the memory of fire, water, and time, blending the world's elements into natural art that shifts and glows beneath the ever-changing light of the sky. Glaciers carve landscapes like moving rivers of rock. A glacier seems still, yet it flows. Over centuries, the weight of accumulated snow compresses into dense ice that slowly slides downhill, reshaping everything in its path. These frozen rivers grind against the mountains, scraping valleys, polishing stones, and carrying debris for miles. When they retreat, they leave behind wide U-shaped valleys, scattered boulders, and shimmering lakes that fill their abandoned paths. The fingerprints of glaciers can be found on nearly every continent, from the smooth granite domes of Yosemite to the carved fjords of Norway. Even now, glaciers continue their patient work, grinding ancient rock into fine dust that drifts on the wind. They are sculptors of continents, artists of time and temperature, shaping the land, grain by grain. In their quiet persistence lies a reminder of the planet's delicate balance, where even the coldest forces flow with a power strong enough to change the world. Some glaciers move fast enough to be seen shifting by the hour. Although glaciers usually creep at the pace of inches per day, A few flow so quickly they can be observed moving within a single afternoon. These fast-moving rivers of ice surge when meltwater lubricates the ground beneath them, reducing friction and allowing massive sheets of ice to slide rapidly forward. In Greenland and parts of Alaska, scientists have documented glaciers racing ahead at surprising speeds, their fractured surfaces groaning and cracking as they go. From a distance, the motion seems impossible. Solid ice behaving like liquid stone. Yet this movement carries enormous power, reshaping valleys and transporting rock by the ton. As they surge, they also remind us that even in their frozen stillness, glaciers are alive with motion. To witness one in movement is to see time itself accelerate. The slow rhythm of the Earth condensed into a visible, breathtaking surge. Ice, under pressure, behaves like slow-flowing honey. Beneath the surface of a glacier, where pressure is immense and temperatures hover just below freezing, ice stops behaving like a solid. Instead, it flows. Not quickly, but slowly and continuously, folding and bending like honey poured in slow motion. The crystals within the ice deform and slide past each other, allowing entire masses to creep downhill. This movement gives glaciers their fluid grace, their ability to carve mountains and shape valleys over tens of thousands of years. Under the right conditions, even solid rock can behave this way, flowing over geological timescales. Watching ice deform under pressure in laboratory experiments reveals how matter blurs the line between solid and liquid. What appears unyielding becomes supple with enough time and weight. The planet's greatest transformations often happen not in sudden bursts, but through the quiet persistence of materials learning to move under pressure. Fossils can capture raindrops that fell hundreds of millions of years ago. Sometimes the smallest traces of the past survive in stone. On slabs of ancient sedimentary rock, scientists have found delicate impressions of raindrops that fell onto soft mud long before humans existed. Each tiny crater records a moment in time, a storm that passed across a primeval landscape, its droplets scattering across a world filled with strange plants and early life. Within seconds, the marks were buried by new layers of sediment, sealing them in darkness until the rock hardened. When the surface is exposed again, it reveals a perfect imprint of weather from a vanished age. These fossilized raindrops remind us that even fleeting moments can last forever when preserved by chance. In a single stone, we can read the touch of a storm that ended hundreds of millions of years ago, its rhythm still visible on the pages of the planet's memory. Some fossils preserve soft tissues, even colors and feathers. For centuries, fossils were thought to capture only bones and shells, the hard remains of ancient creatures. But discoveries over the past few decades have revealed something astonishing. Under rare conditions, even delicate tissues can survive. In certain rocks, scientists have found impressions of skin, muscle, and feathers, sometimes with traces of pigment that show the original colors of dinosaurs and birds. These fossils form when mineral-rich water seeps through the remains before decay can destroy them, replacing organic molecules with stone. The result is a moment of life, turned to sculpture, preserved in perfect detail. Some even retain microscopic structures that hint at how these creatures moved, breathed, and shone in the sunlight of their time. To hold such a fossil is to bridge worlds, feeling the echo of warmth and color from beings that vanished hundreds of millions of years ago. Stromatolites record the oldest known life on Earth. Long before animals or plants evolved, simple microbes built layered structures in shallow seas. These formations, called stromatolites, are the planet's oldest living fossils. They were created by mats of bacteria that trapped and bound sediment, forming domes that slowly grew toward the sunlight. Some ancient examples are more than 3.5 billion years old, making them among the earliest evidence of life anywhere. Remarkably, stromatolites still exist today in a few remote places, such as Shark Bay in Australia, where microbial communities continue their slow whirl. Rhythmic growth. Looking at one is like peering directly into the dawn of biology, when the first cells began shaping the planet. They remind us that life's story began not with motion or complexity, but with patience. Layers of living film turning light, water, and time into the very foundation of everything that followed. Earth once turned completely white during a global snowball Earth. Around 700 million years ago, our planet nearly froze solid. Ice stretched from pole to equator, sealing the oceans under miles of frozen crust and reflecting sunlight back into space. It is believed that volcanic activity, changes in atmospheric gases, and shifts in solar energy combined to trigger this global deep freeze. For millions of years, Earth remained a vast, silent world of ice, its surface gleaming white beneath a dim sun. Yet life endured, hidden in pockets of liquid water beneath the glaciers or near volcanic vents. Eventually, volcanic eruptions released enough carbon dioxide to trap heat again, thawing the planet in a dramatic, world-spanning melt. The return of liquid oceans may have helped trigger an explosion of complex life. Snowball Earth stands as one of the greatest transformations in planetary history, a near-death and rebirth written in ice and stone. Volcanoes may have ended that frozen age with a greenhouse burst. During the depths of the global freeze, volcanoes continued to erupt, pumping carbon dioxide into the air for millions of years. With the oceans sealed beneath ice, this gas could not dissolve as it normally would, so it built up in the atmosphere, trapping heat. When the ice finally began to melt, the process accelerated dramatically. Dark, exposed rock absorbed sunlight, amplifying the warming effect. Within a geologic blink, the planet shifted from frozen white to steaming blue-green seas once more. This thawing unleashed floods, erosion, and perhaps even chemical changes that nourished early life. In a way, volcanoes may have saved the planet, their quiet persistence beneath the ice, keeping Earth's climate alive. What was once an age of silence became one of rebirth, proving that even in the planet's darkest cold, fire and renewal were waiting patiently below. Oxygen in the air was first made by ancient microbial mats. The air we breathe owes its existence to tiny organisms that lived billions of years ago. These microbes, ancestors of modern cyanobacteria, thrived in shallow seas and used sunlight to split water molecules, releasing oxygen as a double-E byproduct. Over time, their waste transformed the planet. At first, the oxygen reacted with iron in the oceans, forming vast deposits of rust-colored rock. Only after these minerals were saturated did the gas begin to fill the atmosphere, slowly turning it into the life-giving mixture we depend on today. This event, known as the Great Oxidation, changed everything. It allowed complex cells to evolve and eventually made possible the rise of plants and animals. Every breath you take is a gift from those ancient microbes, whose simple chemistry turned a barren world into a living one, paving the way for forests, oceans, all that followed. Iron formations mark the moment the planet began to breathe. In ancient seabeds around the world lie bands of red and grey rock that shimmer with metallic luster. These banded iron formations are the fossilized record of the time when oxygen first appeared in Earth's atmosphere. As primitive microbes began producing oxygen through photosynthesis, the gas reacted with dissolved iron in the oceans, creating rust-like minerals, the crustimi, settled to the seafloor in layers. Over millions of years, these sediments hardened into rock, capturing the breath of a newly awakening planet. Today, those same formations are mined for iron, the backbone of modern industry, yet they began as the byproduct of microscopic life. Each stripe in the stone is a heartbeat in the planet's transformation, marking the slow transition from a world without air to one alive with oxygen, where the Bra. Chemistry of life itself began to take hold across land and sea. There was once a time when the seas were purple. Before oxygen filled the air, Earth's oceans looked very different. The water may have shimmered with shades of red and violet, colored by ancient microbes that used molecules of sulfur, not oxygen, to capture sunlight. These organisms thrived in chemical-rich seas under an orange sky, producing pigments that tinted the water with strange hues. As photosynthetic bacteria began to release oxygen, these purple oceans slowly faded to the blue we know today. The shift from a sulfur world to an oxygen one was one of the greatest transitions in Earth's history, altering everything from the atmosphere to the chemistry of rocks. For a time, though, our planet glowed in colors we can scarcely imagine. Seas of violet under a dim sun, the signature of life experimenting with light long before the age of forests, coral reefs, or any creature that breathed air. Entire mountain ranges have vanished without a trace. The continents we see today are only the latest version of Earth's face. In deep time, entire mountain ranges have risen and eroded away so completely that no trace of them remains. Wind, water, and gravity work patiently, wearing down even the tallest peaks, grain by grain. The roots of ancient mountains sometimes survive as crystalline rock buried beneath newer layers, clues left behind for geologists to find. Some of the oldest continental crusts once bore enormous ranges, now reduced to flat plains. Over hundreds of millions of years, erosion can erase a mountain as easily as waves smooth a pebble. The planet is always rebuilding itself, and what seems eternal to us is only a temporary sculpture in the ongoing art of geology. Every plain and valley was once a summit, and every stone carries the ghost of a vanished mountain in its heart. Continents have collided and split apart many times in Earth's past. Over the course of billions of years, the continents have gathered and drifted apart like slow-moving puzzle pieces. Driven by heat rising from the mantle, the crust has folded, fractured, and rearranged itself again and again. Each collision built new mountains, each separation opened new oceans. This process, known as the supercontinent cycle, has repeated at least half a dozen times. When continents collide, rocks are buried deep and reborn through heat and pressure. When they separate, new crust forms, carrying ancient fragments of lost worlds. The scars of these migrations are visible in matching fossils and rock patterns found on opposite sides of modern oceans. The land beneath our feet is not fixed, but part of a restless dance that never ends. Proof that the ground we stand on has traveled far, carrying the history of countless ancient worlds within its foundations. There have been at least 6 supercontinents before ours. Before Pangaea, before even Rodinia, the Earth assembled and broke apart at least 6 times, forming vast supercontinents that drifted through the ages. Each one had its own mountains, oceans, and climates, its own rise and fall written in stone. Nuna, Columbia, Rodinia, Anosia, and Gondwana are names given to these lost worlds, their remains scattered across the globe. When they existed, life was often microscopic, yet their formation shaped the chemistry of the oceans and atmosphere. Each breakup and reunion altered the course of evolution, stirring the climate and shifting the deep currents of the planet. The continents we know are pieces of those ancient giants, survivors of a cycle that spans billions of years. To study them is to read Earth's autobiography, written across time, where even the land itself is temporary, and nothing stays whole for long. Pangaea was only the most recent supercontinent. About 250 million years ago, nearly all land on Earth gathered into a single vast supercontinent surrounded by a global ocean. This colossal landmass, called Pangaea, stretched from pole to pole, connecting regions that are now continents apart. Its interior was harsh and dry, far from the sea's moderating influence, while its coasts teemed with early reptiles and forests. Over tens of millions of years, heat beneath the crust built pressure until cracks appeared, splitting the land apart. The Atlantic Ocean opened, and the continents began drifting toward their modern positions. Fossils of identical plants and animals found on opposite sides of the ocean are silent witnesses to that ancient unity. Pangaea's breakup shaped modern geography and climate, setting the stage for everything that followed. It was not the first supercontinent, nor will it be the last, only one chapter in Earth's endless drift. The next supercontinent may already be forming under the Pacific. Far beneath the waves, the slow movements of the tectonic plates are setting the stage for the next great rearrangement of Earth's surface. Scientists predict that in 200 to 300 million years, the continents may once again converge into a new supercontinent. Some models suggest the Pacific Ocean will close as Asia and the Americas move together, forming a landmass sometimes called Amasia. Others imagine the Atlantic closing instead, drawing Europe and the Americas toward each other. Though the outcome is uncertain, the process is inevitable. The same invisible currents that tore Pangaea apart are still at work, shifting continents inch by inch. To imagine the world that far ahead is to realize how temporary our maps truly are. The Earth is always remaking itself, and somewhere deep below, the first motions of the next supercontinent have already begun. Australia is drifting north toward Asia every single year. Far beneath the continent of Australia, the tectonic plate that carries it is slowly gliding northward at a pace of a few centimeters each year. Over millions of years, this gentle motion adds up to thousands of kilometers. Eventually, Australia will collide with the islands of Southeast Asia, raising new mountains and reshaping coastlines. Satellite measurements already track its yearly drift with astonishing precision. The motion is powered by deep convection currents in the mantle, where heat from the planet's core moves vast sheets of rock as if they were rafts on a molten sea. Though the movement is imperceptible to us, it changes maps, climates, and even ecosystems. Coral reefs grow where land once lay. Deserts inch toward the tropics, and someday new mountain ranges will rise between the two regions. The continent's slow voyage north is one of the most graceful migrations on Earth. Africa may one day split into two separate continents. Deep within East Africa, a great rift stretches for thousands of kilometers, marking the place where the continent is slowly tearing apart. Volcanic activity, earthquakes, and thinning crust reveal that a new ocean may eventually form there. The East African rift is a visible reminder that continents are never truly solid. They bend and stretch like skin over a living body. In a few tens of millions of years, the region that includes Ethiopia, Kenya, and Tanzania could separate from the rest of Africa, drifting eastward into its own Crete. Landmass. Lakes such as Tanganyika and Malawi fill the rift's deep scars, early clues to the ocean that will someday flood in. Standing on its edges is like glimpsing the birth of a future continent. The process is slow beyond imagination, yet it is happening right now beneath our feet, shaping the world of tomorrow. Iceland sits directly above a tear in Earth's crust. The island of Iceland exists because it straddles the mid-Atlantic ridge, a boundary where two tectonic plates are moving apart. Here, molten rock wells upward through a long tear in the crust, building new land as it cools. The entire island is a crossroads of fire and ice, with glaciers resting beside active volcanoes. Hot springs, geysers, and lava fields testify to the restless energy below. Every few years, eruptions remind residents that their homeland is still under construction. The island's unique position makes it one of the few places where this boundary rises above sea level, allowing scientists to study the raw mechanics of plate tectonics in plain view. Iceland is a living experiment of creation, a place where the Earth quite literally grows before our eyes, balancing on the edge between the frozen North Atlantic wall and the molten heart of the planet. The Hawaiian Islands are a moving chain built by a stationary hotspot. In the middle of the Pacific Ocean, a plume of molten rock rises from deep within the mantle, punching through the crust to create volcanoes. As the Pacific Plate drifts slowly northwestward, each new eruption forms an island that eventually moves away from the hotspot, allowing another to take its place. This process has created a long chain of islands and undersea mountains stretching thousands of kilometers across the ocean floor. The youngest island, Hawaii, still glows with active lava flows, while the oldest islands, far to the northwest, have eroded into low atolls. By tracing this chain, scientists can map the movement of the Pacific Plate over millions of years. The hotspot itself stays fixed, while the surface glides above it, leaving a dotted record of time and motion. Each island is a chapter in an ongoing story of creation written in molten stone. Yellowstone hides one of the largest volcanic systems on Earth. Beneath the forests and geysers of Yellowstone lies an immense reservoir of magma, large enough to fuel one of the most powerful volcanic systems ever discovered. The park's steaming vents, bubbling pools, and dramatic eruptions of boiling water are surface clues to the heat below. Scientists monitor the region closely, mapping the hidden chambers that stretch for dozens of kilometers beneath the crust. Although it is not expected to erupt anytime soon, its past explosions reshaped much of North America, scattering ash across entire continents. Today, the region breathes through its geysers, releasing pressure in spectacular bursts that remind us of its inner fire. Yellowstone is both a sanctuary of beauty and a window into the restless nature of the planet, where even beneath tranquil landscapes, ancient forces of heat and pressure continue to shape the Earth in silence. Supervolcanoes can alter the planet's climate for centuries. When ordinary volcanoes erupt, they affect local weather for a few seasons. When supervolcanoes erupt, they can transform the entire planet. These titanic explosions release thousands of cubic kilometers of ash and gas into the atmosphere, blocking sunlight and cooling the globe for decades or even centuries. Evidence of such eruptions appears in ash layers and climate records from Yellowstone, Toba, and Topa. The aftermath includes volcanic winters, where temperatures drop and ecosystems struggle to adapt. Though rare, these events remind us of the delicate balance between Earth's interior and its surface. The power locked beneath our feet has shaped evolution itself, sometimes triggering mass extinctions that cleared the way for new life. Yet even in their fury, supervolcanoes are part of the planet's long rhythm of renewal, cycling materials between crust and atmosphere, reminding us that life and fire are deeply entwined. The largest known volcanic eruption happened in what is now Indonesia. Around 74,000 years ago, a colossal eruption at Lake Toba in Indonesia changed the world. It expelled more than 2,000 cubic kilometers of ash and magma, leaving behind a caldera 100 kilometers wide that is still visible today. The blast darkened skies across the globe, lowering temperatures and spreading volcanic ash over continents. Some scientists believe it caused a brief volcanic winter that may have influenced early human populations. Even after the eruption ended, volcanic gases lingered in the atmosphere, tinting sunsets and cooling the planet for years. The event was so vast that it dwarfs any eruption in recorded history. Today, the tranquil lake that fills the caldera seems peaceful, but beneath its calm waters lies one of Earth's most powerful scars. A reminder that the planet's greatest moments of creation often come wrapped in destruction. Some eruptions have left ash that still circles the globe today. Fine volcanic ash can drift in the upper atmosphere for years, carried by winds that circle the planet. Particles from major eruptions such as Mount Pinatubo in the Philippines or Krakatau in Indonesia have been detected long after the explosions ended. These microscopic fragments scatter sunlight, producing brilliant red sunsets and slightly cooling global temperatures. High above the weather, they form thin veils that reflect light in ways that painters once captured after historic eruptions. Some layers of airborne ash even return to Earth centuries later, discovered in ice cores and ocean sediments. Every eruption, no matter how remote, connects to the atmosphere that wraps the entire planet. The air we breathe today carries traces of eruptions from distant ages, a delicate reminder that even the calmest sky holds echoes of the Earth's fiery breath. Lava lakes can remain molten for decades without cooling. In a few rare volcanic craters around the world, molten rock never solidifies. These lava lakes, such as those in Erta Ale in Ethiopia and Kilauea in Hawaii, are sustained by constant supplies of heat and magma from below. Their surfaces churn and ripple like fiery oceans, crusting over only to break apart again. At night, they glow like windows into the planet's heart, their orange light flickering against dark rock and smoke. The heat balance is so precise that the lakes can persist for decades, continually refreshed by deep circulation. Watching one is mesmerizing. A living furnace breathing and pulsing in slow rhythm. They offer scientists rare insights into the chemistry and physics of magma that cannot be replicated in laboratories. Each lake is a reminder that the Earth's fire still burns just beneath its thin, cooling crust, timeless and alive. Lightning can strike inside volcanic ash clouds. When a volcano erupts, the immense friction between ash particles creates powerful electrical charges. As these charges build, they discharge as lightning bolts that crackle through the ash plume. Volcanic lightning can illuminate entire skies, creating storms of fire and light above erupting mountains. Unlike ordinary thunderstorms, these flashes are born entirely from the energy of rock and gas. Photographs capture branching bolts arcing through columns of black smoke, each strike lasting only a heartbeat but carrying immense power. Scientists study these flashes to understand the flow of ash and to track eruption intensity, since lightning can signal how violently material is being ejected. To witness one is to see the fusion of Earth's elemental forces. Solid, liquid, and gas meeting electricity. A brief, awe-inspiring display that reveals how even destruction can shimmer with extraordinary beauty. When volcanoes meet ice, they create explosive steam eruptions. In places where glaciers rest atop volcanoes, heat and ice collide in spectacular ways. When magma rises beneath the ice, it melts huge volumes of water in an instant, producing steam that expands with explosive force. These eruptions can blast through the glacier, sending floods and ash clouds cascading down valleys. Iceland's volcanoes often behave this way, hidden beneath thick ice caps, until pressure builds high enough to burst free. The interaction leaves behind unique landforms, ridges and plateaus sculpted by fire and water together. Scientists call them tuyas, monuments to the strange partnership of heat and cold. Each eruption beneath ice rewrites the landscape, proving that even the most opposite elements of nature are connected in a cycle of creation, transformation that has shaped our planet since its earliest days. Entire new islands have risen from volcanic eruptions within living memory. Across the oceans, new land sometimes appears where there was once only water. Submarine volcanoes occasionally erupt with such force that they build islands from the seafloor upward. In the past century, eruptions near Iceland, Japan, and Tonga have created fresh patches of land that still steam and harden under the sun. Some vanish again within years, eroded by waves, while others grow stable enough to host life. These newborn islands reveal the planet's creative power unfolding in real time. To watch one form is to witness the process that built continents long ago. Birds, plants, and eventually humans find their way there, turning raw lava into ecosystems. The emergence of new islands reminds us that Earth is not finished with its work. The planet continues to build, break, and begin again, renewing its surface one eruption at a time. Some lakes are filled with dissolved carbon dioxide that can erupt like soda. In parts of Africa, certain deep lakes contain massive amounts of carbon dioxide trapped beneath their surfaces. When the balance of temperature or pressure changes suddenly, that gas can burst upward in a deadly, invisible wave. Lake Nyos in Cameroon released such a cloud in the 1980s, suffocating life in nearby valleys. Scientists now monitor these lakes carefully and install systems to safely release gas before pressure builds too high. The phenomenon is called a limnic eruption, a rare but powerful reminder of how even tranquil waters can conceal immense energy. The gas originates from volcanic sources below the lakebed, seeping upward through cracks in the crust. Over centuries, it dissolves into the water like carbonation in a bottle. When it finally escapes, the result is silent and shocking. A natural event as strange as it is terrifying. Sinkholes can swallow buildings in seconds. Beneath many cities and fields, hidden cavities form where limestone or salt dissolves slowly in underground water. When the roof of one of these voids collapses, the ground above can suddenly drop away, creating a sinkhole. Some are only a few meters wide, others can stretch hundreds across, devouring cars, trees, and homes without warning. They form most often after heavy rain, when water seeps through cracks and weakens the layers below. Entire neighborhoods have been built atop such fragile foundations without realizing it. Scientists map vulnerable regions with radar and ground sensors to detect cavities before disaster strikes. Though dramatic, sinkholes are part of the planet's natural recycling of rock, where water patiently sculpts the landscape from beneath. Each collapse reveals the fragile balance between solid ground and the hidden hollows that lie quietly just below our everyday world. Karst landscapes hide secret rivers flowing through stone. Where limestone or dolomite dominates the bedrock, rainwater slowly carves intricate networks of tunnels and caverns. These underground systems can stretch for hundreds of kilometers, carrying entire rivers beneath the surface. The land above collapses in places, forming sinkholes, valleys, and jagged ridges characteristic of karst terrain. Water disappearing into a cave entrance might re-emerge miles away as a clear spring. In some regions, entire ecosystems have adapted to these lightless waterways, from blind fish to translucent insects. Karst landscapes are found on every continent and provide drinking water for millions of people, yet their hidden nature makes them vulnerable to pollution. Exploring them is like entering the circulatory system of the planet, where stone and water move together in endless dialogue, dissolving, shaping, and renewing the phase. Surface of the earth drop by drop. Stalactites grow from the ceiling, stalagmites from the floor, and they can meet to form pillars. Inside limestone caves, dripping water carries dissolved minerals that slowly crystallize as it evaporates. From the ceiling, each droplet leaves behind a tiny ring of calcite that lengthens downward over centuries, forming a stalactite. Where the drops land, matching mounds grow upward as stalagmites. Eventually, they can meet to create towering columns that seem to hold the cave aloft. The process is so gradual that growth rates are measured in millimeters per century. Lantern light reveals their delicate textures. Frozen waterfalls, sculpted by time and patience. These formations are living records of the cave's history, recording changes in water chemistry and climate. When viewed together, they resemble forests of stone, where every branch and trunk was born from a single droplet that fell through darkness, carrying the memory of rain and the passage of unthinkable time. Cave formations grow slower than fingernails. The breathtaking shapes found in caves are products of unimaginable patience. Stalactites, flowstones, and crystal draperies accumulate one layer at a time as water leaves behind thin films of mineral. A single centimeter of growth can take hundreds of years. The rate depends on the drip of water, the purity of minerals, and even the temperature of the surrounding rock. Some formations still glisten wet from drops that began their journey through the ground decades ago. Studying their layers allows scientists to reconstruct past climates, revealing droughts, floods, and shifts in rainfall patterns long before written history. Walking through a cavern is like entering a slow-motion clock, where time moves at the pace of minerals crystallizing. These subterranean sculptures remind us that beauty can emerge not from speed or force, but from stillness and persistence beyond human measure. Some caves have their own weather systems. Deep underground, large cave networks can develop microclimates distinct from the surface. Temperature, humidity, and airflow combine to create fogs, winds, and even tiny clouds that drift through the chambers. Warm air rising from deeper passages meets cooler air near entrances, producing swirling currents that resemble miniature weather fronts. Some caves experience regular breathing, exhaling warm air in winter and inhaling cool air in summer as outside conditions change. Moisture condenses on walls, dripping to sustain delicate formations and ecosystems. To step inside is to feel the planet inhale, the rhythm of air and rock joined together. These hidden climates preserve fossils, artifacts, and species that cannot survive elsewhere. Within their stone lungs, caves remind us that even the most solid parts of Earth are filled with movement, breath, and subtle patterns of living atmosphere. Earth's longest cave stretches for hundreds of miles underground. Beneath the rolling hills of Kentucky lies Mammoth Cave, the largest known cave system on Earth. Its passages extend for more than 400 miles, and new tunnels are still being discovered. The network was carved by ancient rivers dissolving limestone over millions of years, branching and looping in a labyrinth that could hide entire cities within its prow. Depths. Explorers move through narrow crawls, towering chambers, and underground rivers that still reshape the rock today. The air remains cool and still, and the silence is so deep it seems alive. The cave's vastness challenges the imagination, reminding visitors how much of the planet exists unseen beneath our feet. Mammoth Cave is both a geological wonder and a living record of time, carved by water's persistence into a cathedral of stone that stretches into darkness without end. Earthquakes can permanently change the length of a day. When a massive earthquake shifts the distribution of Earth's mass, the planet's rotation subtly changes. The effect is tiny, usually measured in microseconds, but still measurable. By moving enormous slabs of rock, an earthquake can slightly alter the planet's moment of inertia, just as a spinning skater speeds up when pulling their arms inward. After the 2004 Sumatra earthquake, scientists calculated that the day shortened by fractions of a second. The event also nudged the position of the poles and adjusted the shape of the planet ever so slightly. These shifts remind us that even the concept of a day, which feels absolute, is influenced by the deep movements of rock and gravity. Each quake is not only a surface event, but a planetary one, echoing through the rotation of the world itself and whispering change into the rhythm of time. Shockwaves from massive quakes travel all the way around the globe. When a powerful earthquake strikes, the energy it releases doesn't just stop at the epicenter. Seismic waves ripple outward through the entire planet, racing through rock and mantle like sound through a bell. Sensitive instruments can detect the same quake echoing around the world several times before fading. The largest quakes make the entire Earth tremble, subtly flexing its crust as energy moves from one side of the globe to the other. Even regions thousands of kilometers away can feel the faint aftershocks. Scientists use these global reverberations to map the planet's interior, tracing how the waves bend and reflect inside molten layers. Each tremor reveals something about the structure of the deep Earth, where it's solid, where it's fluid, and how heat moves within. Every great quake briefly turns the world into a single vibrating instrument, humming softly with its own heartbeat. Some earthquakes release energy equivalent to millions of tons of TNT. The scale of an earthquake's energy is staggering. When the largest faults rupture, they can release as much power as several million tons of explosive material detonating at once. The shaking that we feel on the surface is only part of it. Most of the energy travels deep into the crust, moving rock layers that weigh more than an entire mountain, ranges. The moment magnitude scale scientists use today was designed to measure these immense forces more accurately than older systems. During the 2011 Tohoku quake in Japan, the energy released was enough to alter the rotation of the planet and shift the seafloor by several meters. It's difficult to grasp such numbers, but each quake reminds us that the Earth's crust is under constant pressure, always storing and releasing energy in a slow, powerful rhythm that shapes continents and seas over time. Rocks deep underground can flow like putty under pressure. Though stone feels solid and unyielding to us, deep inside the Earth it behaves differently. At great depths, where temperatures and pressures rise beyond imagination, rock begins to deform slowly, flowing like an extremely thick liquid. Over millions of years, this plastic movement allows entire mountain ranges to rise, fold, and melt into new formations. Minerals stretch and twist, creating patterns seen in metamorphic rocks exposed at the surface today. In laboratory experiments, geologists have watched samples of rock bend rather than break when heated and compressed, confirming that time itself changes how matter behaves. The mantle beneath our feet constantly moves this way, its flow driving the drifting of continents above. It's a reminder that even what seems rigid is capable of motion, and that the strength of stone lies not only in hardness, but in its ability to yield, reshape, endure. Metamorphic rocks record the history of pressure and heat inside the planet. When rocks are buried deep within the Earth's crust, they are transformed. Immense heat and pressure reorganize their minerals without melting them entirely, creating new textures and structures. Granite becomes gneiss, limestone becomes marble, shale becomes slate. Each type of metamorphic rock carries a record of the forces that shaped it, like pages in a geological diary. Scientists can read these records to reconstruct ancient mountain-building events or the depths at which certain rocks once rested. Some metamorphic formations even reveal the direction of tectonic movement through their mineral alignments. When uplift eventually exposes them at the surface, we glimpse the planet's internal history frozen in crystalline form. They are stones that remember, preserving within their folds the immense energies that flow invisibly beneath the crust, showing that every mountain once lay hidden, being, rewritten by heat, pressure, and time. Slate was once mud pressed by time into stone. Beneath ancient seas, layers of mud once settled in quiet darkness. Over millions of years, these sediments compacted under the weight of newer layers above them, squeezing out water and aligning clay minerals into flat sheets. With heat and pressure, that mud hardened into slate, a rock so finely layered that it can be split into smooth tiles. The transformation is a story of stillness turned to strength, the patience of sediment reborn as stone. Slate once formed entire sea floors. Today it roofs cottages and lines pathways, carrying the imprint of ancient oceans into our modern world. If you hold a piece and tilt it to the light, you can still see the sheen of its compressed minerals, tiny echoes of clay that once drifted lazily through water. It's proof that even the softest materials can, through time and pressure, become enduring and strong. Marble began its life as limestone filled with sea fossils. Long before it gleamed in temples and sculptures, marble began as humble limestone on the sea floor. That limestone was composed of shells and skeletons of marine creatures. Coral, plankton, and mollusks compacted over millions of years. When buried deep within the earth, it met heat and pressure that caused its crystals to grow, erasing visible fossils and creating the smooth, interlocking texture of marble. Trace minerals added subtle colors: iron for red, serpentine for green, graphite for gray. When polished, these minerals catch the light, giving marble its famous glow. Ancient civilizations prized it because it seemed to hold sunlight within. In truth, it is a relic of vanished oceans, born from life, death, and transformation. Every polished surface of marble, from a cathedral column to a carved statue, was once part of the living sea that hardened into timeless beauty. Every gemstone tells the story of its geological birth. Hidden deep in the Earth's crust, heat, pressure, and chemistry collaborate to create crystals of astonishing beauty. Diamonds form under crushing forces hundreds of kilometers down, while emeralds grew in mineral-rich veins where water and rock exchange elements. Rubies, sapphires, topaz, and quartz each arise from precise conditions of temperature and chemistry that rarely coincide. That rarity makes them precious. When cut and polished, their clarity reveals the harmony of their atomic structures, a glimpse into order forged in chaos. Gemstones travel from deep rock to human hands through volcanoes, erosion, and time. Each one is a messenger from a different environment within the planet, a record of its hidden processes. To look into a gemstone is to peer backward into the Earth's memory, seeing the patience of pressure and the art of crystallization written in perfect, glittering symmetry. Rubies and sapphires are the same mineral colored by different elements. At first glance, rubies and sapphires seem like completely different stones, but both are varieties of the same mineral, corundum. In its pure form, corundum is colorless, composed of aluminum and oxygen in a tightly packed crystalline lattice. When tiny amounts of chromium enter that structure, it glows red and becomes ruby. When iron and titanium take its place, the result is blue sapphire. Other trace elements produce yellows, greens, or even pinks. These subtle substitutions in atomic makeup change the way light passes through the crystal, giving each gem its hue. The fact that two of the world's most prized stones come from the same mineral shows how small changes at the atomic level can yield astonishing beauty. Every color is a fingerprint of chemistry, proof that nature's artistry begins in the invisible dance of elements deep within the earth. Emeralds form only under the rarest conditions of pressure and chemistry. Among gemstones, emeralds are among the most elusive. They require a perfect meeting of two very different worlds: silica-rich rocks and beryllium-bearing fluids, conditions that rarely coincide in nature. When they do, the mineral beryl forms, colored green by traces of chromium or vanadium. This delicate balance occurs only in certain mountain regions where tectonic activity has blended these ingredients. The result is a gem that carries the tension of its birth within every shimmering facet. Most emeralds contain tiny fractures and inclusions, called jardins or gardens, that mark their natural formation. These imperfections are not flaws but signatures of authenticity, evidence that the stone is a true child of the earth. To hold one is to hold the story of improbable chemistry, immense pressure, and geological patience that conspired to create something impossibly rare, luminous. Opal forms from ancient groundwater seeping through silica-rich rock. Opal is unlike most gemstones because it isn't crystalline. It forms when water-carrying dissolved silica trickles through rock, depositing microscopic spheres that stack in delicate layers. These spheres scatter light, producing opal's characteristic rainbow shimmer known as play of color. Many opal deposits began in arid landscapes that were once wet millions of years ago. As the water evaporated, it left behind these intricate, glowing structures. Under magnification, opal reveals a world of order hidden within apparent chaos, a natural mosaic of color suspended in stone. Australia, home to some of the finest specimens, was once part of an ancient inland sea where these processes unfolded. Every opal captures not only the light we see, but the memory of vanished rain, lost rivers, and the quiet chemistry that turns water and sand into fire, frozen forever in stone. Meteorites on Earth tell stories from before our planet was born. When fragments of rock fall from space, they bring messages from the earliest days of the solar system. Some meteorites formed billions of years ago, long before Earth existed, from the same cloud of dust and gas that gave birth to the sun and planets. They contain minerals that have remained unchanged since that time, preserving a record of ancient chemistry. Scientists study them to learn how the building blocks of planets assembled, melted, and differentiated into cores and crusts. Some even carry organic compounds, hinting that the ingredients for life were scattered through space long before Earth began to form. To hold a meteorite is to touch something older than our world, a piece of cosmic debris that has traveled across time and distance to rest in our hands, carrying the memory of creation itself. Some rocks are older than the solar system itself. Within certain meteorites, scientists have discovered microscopic grains called pre-solar dust, remnants of ancient stars that existed before the sun. These tiny crystals formed in the outer layers of dying stars and were carried into space by stellar winds. Over billions of years, they drifted through the galaxy, eventually becoming trapped in the material that built our solar system. Their isotopic fingerprints reveal their alien origins, differing from anything found naturally on Earth. To find such grains inside a rock is to discover stardust untouched by planetary processes, matter that predates the world itself. When we analyze these particles, we read stories written before the sun rose. The echoes of supernova and the slow breath of red giants. Each grain is a whisper from the galaxy's past, proof that the Earth itself was born from recycled stars. Lunar rocks brought back by astronauts helped date Earth's early crust. The samples collected from the Moon during the Apollo missions did more than reveal lunar history. They unlocked secrets about Earth's own beginnings. The isotopic composition of lunar rocks matches that of Earth's mantle, supporting the theory that the Moon formed from debris left behind after a colossal collision between a young Earth and another planet-sized body. By studying those rocks, scientists could estimate when Earth's crust first solidified, around 4.5 billion years ago. Some of the oldest lunar basalts also record impacts that shaped the early solar system. Their surfaces, pitted by micrometeorites, have remained unchanged for eons, preserving a record of ancient bombardment lost on our eroded planet. Every moon rock brought home is a time capsule, connecting two worlds forever linked by a single, violent origin story, written in dust and fire. The oldest minerals ever found are tiny zircons from ancient Australia. In the ancient rocks of Western Australia, geologists discovered microscopic crystals of zircon that date back more than 4 billion years. These resilient minerals formed soon after the Earth itself, surviving countless cycles of erosion and metamorphosis. Inside each one lies a trace of uranium that has slowly decayed into lead, allowing scientists to measure their age with extraordinary precision. The zircon's composition shows that liquid water already existed on the planet when they formed, suggesting that Earth's surface cooled surprisingly quickly after its sea. Violent birth. They are among the few surviving witnesses of the planet's earliest chapter, fragments that outlasted the destruction of entire continents. To hold a zircon under a microscope is to look directly into the dawn of Earth's history, a crystal memory of a time when the world was still forming its oceans, crust, and atmosphere. These zircons record the first liquid water on Earth. Analysis of those ancient zircons revealed chemical ratios consistent with rocks that had interacted with liquid water. That discovery pushed the timeline for Earth's oceans far earlier than once thought, perhaps within 200 million years of the planet's formation. Before this finding, scientists believed the young Earth was a molten sphere for hundreds of millions of years. The zircons showed that the surface had cooled enough to sustain rain, rivers, and oceans surprisingly soon. This realization reshaped our understanding of habitability, suggesting that conditions suitable for life appeared quickly. Each zircon, smaller than a grain of sand, is a microscopic archive of water's arrival on Earth. Through them, we glimpse a world where vapor condensed, clouds formed, and the first drops of rain fell upon cooling rock. The beginning of the blue planet we know today. The continents were once covered in lava fields the size of countries. Throughout deep time, enormous volcanic events, known as flood basalt eruptions, blanketed vast regions of the Earth in sheets of molten rock. These outpourings sometimes continued for millions of years, forming plateaus thousands of meters thick and covering areas larger than modern nations. The Deccan traps in India and the Siberian traps in Russia are two dramatic examples. Such eruptions released immense volumes of gas into the atmosphere, altering climate and ecosystems. When they cooled, they left behind landscapes of stepped rock and rich soils that still shape agriculture today. Standing atop one of these regions is to stand upon frozen lava that once flowed in rivers of fire, rewriting continents. These fields of basalt remind us that the Earth's calm present hides a fiery past when entire regions pulsed with magma and the air shimmered with volcanic light. Those lava floods have caused mass extinctions in the past. The largest volcanic outpourings didn't just reshape continents, they reshaped life itself. The gases and ash released during flood basalt events can poison the air, darken skies, and disrupt climate for thousands of years. The Siberian Trap's eruption around 250 million years ago coincided with the greatest extinction in Earth's history, wiping out most marine species and many on land, These catastrophic releases of carbon dioxide and sulfur dioxide triggered acid rain and global warming, unraveling ecosystems. Yet in the aftermath, new life eventually flourished, adapting to the changed world. These cycles of destruction and renewal are woven into Earth's long story, reminders that even the most devastating events become part of the foundation for what comes next. In every extinction lies the seed of evolution, a silent transformation written in ash and stone. Ash from ancient eruptions still lies buried in modern soils. Across the world, thin layers of volcanic ash are preserved within sediment and soil, silent records of eruptions that occurred thousands or even millions of years ago. Each layer can be traced to its source volcano by the unique chemical signature of its minerals, allowing scientists to match distant sites and build precise timelines of past events. Farmers sometimes unknowingly work these ancient ashes into their fields, their minerals enriching the soil with nutrients. In places like Italy, Iceland, and Japan, volcanic deposits have made the land extraordinarily fertile. To dig into such soil is to touch history, the residue of fire transformed into life. The same ash that once blotted out the sun now nourishes crops and forests, completing a cycle where destruction feeds creation and the remnants of catastrophe sustain the quiet persistence of growth. The Atlantic Ocean was once just a long rift valley. Before the ocean we know existed, the land that became Africa and the Americas was joined in a single supercontinent. Deep cracks began to open between them around 200 million years ago, forming a vast rift that filled with water as the continents drifted apart. Over millions of years, volcanic activity widened the gap, and a new ocean was born. The Mid-Atlantic Ridge, where new crust still forms today, marks the original line of separation. Ancient rift valleys like the one in East Africa offer glimpses of what the early Atlantic once looked like. Long depressions scarred by fault lines and filled with rising magma. What is now an ocean began as a fracture in the Earth's crust, proof that even immense seas start as narrow wounds in stone that slowly deepen until they become worlds of chaff, their own. The sea floor spreads outward from the Mid-Atlantic Ridge like a conveyor belt. In the heart of the Atlantic lies a mountain range hidden beneath the waves, where new crust is continuously formed. Magma rises through cracks, cools, and pushes older rock aside in a steady, symmetrical flow. As this happens, the continents on either side drift farther apart, carried by the movement of the seafloor itself. Magnetic minerals within the cooling lava align with the direction of the planet's magnetic field, creating striped patterns that record ancient field reversals. By measuring these stripes, scientists confirmed that the seafloor truly spreads, validating the theory of plate tectonics. The process continues at a few centimeters per year, imperceptible yet unstoppable. This underwater conveyor of creation expands the ocean even as old crust is pulled downward at subduction zones elsewhere, keeping the surface of the Earth in constant, living motion. Hydrothermal vents create black smokers on the ocean floor. Deep beneath the ocean's surface, along the ridges where tectonic plates meet, seawater seeps into the crust through cracks and fissures. It descends until it touches molten rock, heating to hundreds of degrees before rising again, laden with dissolved metals and minerals. When that superheated water bursts back into the cold ocean, it cools instantly, precipitating clouds of dark material that billow upward like smoke. These black smokers are underwater chimneys of mineral and heat, continuously forming and collapsing. They build mounds of iron, sulfur, and other compounds that shimmer faintly in the deep. Around them, the water glows faintly from reflected particles, and a strange form of life thrives, feeding not on sunlight, but on chemistry. Each vent is a miniature world, a living reminder that even in eternal darkness, the planet finds ways to breathe, burn, and build. Those vents support entire ecosystems without sunlight. Far from the reach of sunlight, life gathers around deep-sea hydrothermal vents in dense colonies. Here, instead of photosynthesis, organisms rely on chemosynthesis, a process where bacteria use chemical energy from sulfur and methane to produce food. Giant tube worms, clams, crabs, and fish all depend on these microscopic producers, forming ecosystems unlike any other on Earth. Temperatures near the vents can swing from near freezing to over 300 degrees Celsius within meters. Yet life not only survives, but thrives. The discovery of these ecosystems in the 1970s changed our understanding of biology forever, revealing that life does not require sunlight, only energy and water. Scientists now suspect similar environments could exist on icy moons like Europa and Enceladus. The dark ocean floor, once thought barren, hums with life powered by the planet's heat. A partnership between geology and biology still unfolding. Minerals there build chimneys taller than houses. At hydrothermal vent sites, minerals continuously precipitate from the superheated fluids streaming into the ocean. Over time, they accumulate into towering chimneys that can reach heights of more than 20 meters. These structures grow upward as long as the flow continues, layer upon layer of sulfides and other minerals forming intricate columns that resemble cathedrals in the deep. Some collapse under their own weight, only to rebuild again. Within these formations, metallic ores concentrate, the same types humans mine on land. Their shimmering surfaces host entire communities of microorganisms and animals, each adapted to the searing temperatures and chemical gradients. The vents pulse like underwater volcanoes, their chimneys smoking gently in the dark. They are proof that even in the most extreme environments, the Earth sculpts beauty from pressure and heat, crafting elaborate monuments that few eyes will ever double-bar. See directly. Earth's magnetic field has flipped hundreds of times. Throughout its history, the planet's magnetic poles have reversed repeatedly, swapping north for south. These flips occur irregularly, sometimes separated by hundreds of thousands of years, other times by millions. The cause lies deep within the molten outer core, where swirling currents of liquid iron generate the magnetic field. As these currents shift, the field weakens, reorganizes, and eventually reverses. Evidence of this constant flipping is written in volcanic rocks on the sea floor, where iron minerals align with the magnetic field as the lava cools. Each stripe of opposite polarity marks a moment in this long cycle. Although a reversal could take thousands of years to complete, life has persisted through every one of them without disruption. The phenomenon reminds us that even the invisible shield protecting Earth from cosmic radiation is dynamic, a living force shaped by the movement of the planet's molten heart. During those flips, compass needles would have pointed south. If you could stand on Earth during a period of magnetic reversal, your compass would slowly begin to misbehave. Over centuries, magnetic north would drift toward the equator, then beyond it, until it pointed roughly south. These changes unfold gradually as the magnetic field weakens, splits into multiple poles, and finally re-establishes itself in reverse. Rocks preserve the memory of such shifts, their magnetic minerals frozen in the direction that was north at the time of their formation. Studying these ancient orientations has allowed scientists to trace the timeline of reversals and the wandering of poles across the planet. Though the idea might seem unsettling, reversals are natural and frequent in Earth's history. They have never caused mass extinctions or atmospheric collapse. Instead, they reveal the vitality of the geodynamo, the deep, unseen engine that keeps the planet's magnetic heart beating across the ages. Even today, the magnetic poles wander by miles each year. The Earth's magnetic field is not fixed in place. The North Magnetic Pole, once located in the Canadian Arctic, is now racing towards Siberia at a speed of more than 30 kilometers per year. This drift happens because of changes in the molten iron flowing through the planet's outer core. As convection currents shift, they alter the balance of magnetic forces above. Instruments aboard satellites continuously track the pole's movements, updating navigation systems that rely on their position. While the magnetic north wanders, the geographic North Pole remains steady, making the 2 points distinct. To most people, the difference goes unnoticed, but to scientists, the shifting poles are a reminder that the field protecting our atmosphere is alive and evolving. The same invisible motion that guides compasses also reveals the slow liquid heartbeat of the world beneath our feet. The moon stabilizes Earth's wobble, which shapes long-term geology. Without the moon's steadying influence, Earth's tilt could vary wildly over time, swinging from near upright to deeply angled. Such instability would cause chaotic climate shifts, turning frozen poles into tropical zones and back again. The moon's gravity, however, keeps the planet's axial tilt stable within a narrow range. This stability has allowed long-term geological and biological cycles to flourish, providing consistent patterns for ocean currents, ice ages, and weather systems. The tides created by the moon's pole also help distribute energy through the oceans, influencing erosion and sediment movement along coastlines. Our planet's geological calm, its balance between order and change, owes much to this silent partner orbiting above. Every gentle tide and rhythmic season is, in part, a gift from the moon, which has guided Earth's dance for more than 4 billion years without missing a single turn. Tides caused by the moon sculpt coastlines across millennia. Each day, the ocean rises and falls as the moon's gravity tugs at Earth's water. Over years and centuries, these tides do more than move waves, they reshape entire coastlines. Tidal forces carve estuaries, widen bays, and carry sediments that build beaches and deltas. The gentle push and pull erode cliffs and transport nutrients that sustain marine life. In some regions, the tidal range exceeds 10 meters, creating vast intertidal zones that alternate between land and sea. These dynamic environments are nurseries for fish, birds, and countless invertebrates. Over geological time, tides have even influenced the formation of continental shelves and barrier islands. The rhythm is ancient and constant, linking the motion of distant celestial bodies to the patterns of sand beneath our feet. The shoreline we see today is a moving sculpture shaped grain by the patient breath of the moon. Coral reefs are living geological structures made of calcium skeletons. Coral reefs, though teeming with life, are also monumental geological formations. Each coral polyp builds a tiny limestone skeleton, and together, countless generations stack these structures upward toward sunlight. Over thousands of years, the result is a reef so vast it can be seen from space. The Great Barrier Reef, for example, stretches for more than 2,000 kilometers, formed layer by living builders. When corals die, new ones grow atop their remains, continuing the cycle. These structures serve as natural barriers that protect coastlines and as archives of ocean history, recording temperature and chemistry in their layers. Even fossilized reefs tell stories of ancient seas that once covered modern continents. Every coral colony is both a biological community and a geological monument, living rock that breathes, grows, and preserves the memory of the oceans. That shaped our world. Some coral reefs are older than many mountain ranges. Beneath the calm surfaces of tropical seas lie reefs that have been growing continuously for tens of millions of years. Some began forming when dinosaurs still roamed the Earth. Over geological timescales, entire mountain chains have risen and eroded away, while these underwater structures quietly expanded. Their cores are made of compacted limestone formed by the skeletons of billions of tiny organisms. As sea levels rose and fell, reefs adapted, climbing upward or migrating toward the light. Fossilized remnants of ancient reefs now appear in deserts and on mountaintops, proof that what was once ocean has become land. The endurance of coral reefs shows the planet's continuity through upheaval, their layered skeletons tracing both biological and geological time. Each one is a cathedral of life and stone, older than civilization, older than mountains, a living bridge between eras of Earth's unfolding story. Dust from deserts can fertilize entire rainforests across oceans. Tiny grains of mineral dust lifted from the world's great deserts travel thousands of kilometers through the atmosphere, carried by winds across continents and seas. Much of this dust eventually falls upon distant ecosystems, where it delivers vital nutrients. The Amazon rainforest, for example, depends on phosphorus-rich dust blown from the Sahara each year to replenish its soils. Without it, tropical rains would wash essential minerals away. These airborne particles connect ecosystems that might seem unrelated, linking arid wastelands to lush jungles. Satellite images have captured vast plumes crossing the Atlantic, shimmering in sunlight before settling as invisible nourishment. Each grain is a geological traveler, a fragment of rock that left one landscape to sustain another. In this quiet planetary exchange, deserts and forests become partners in an endless cycle of erosion, wind, and renewal that spans the entire globe. Rocks on Earth contain tiny fragments of stardust. Inside certain meteorites, and even within ancient terrestrial rocks, lie microscopic grains that originated in dying stars long before the solar system formed. These specks of stardust survived the collapse of the gas cloud that birthed the sun, eventually becoming part of the material that built the planets. Their isotopic signatures are unlike anything produced on Earth, marking them as truly alien in origin. When scientists isolate these particles, they can trace the life cycles of stars, from their formation to their explosive ends. Each grain carries within it atoms forged in stellar furnaces, proof that everything on our planet, including ourselves, was once part of the cosmos. These ancient fragments bridge time and space, reminding us that geology is not confined to Earth alone, but part of a universal story of matter, transforming endlessly through creation and decay. Gold and platinum came from ancient meteor impacts. The precious metals that gleam in jewelry and technology were not part of Earth's original crust. During the planet's formation, nearly all of its gold, platinum, and similar heavy elements sank into the molten core. The metals we mine today arrived later, delivered by meteorites during a period of intense bombardment more than 4 billion years ago. These impacts scattered metallic debris across the surface, enriching the upper crust with treasures forged in stellar explosions. Every gold vein or platinum deposit is a cosmic inheritance, the residue of cataclysmic events that once lit the solar system with fire. To wear or hold a piece of gold is to touch the memory of that ancient rain of metal from the stars. It is a tangible link between celestial violence and earthly beauty, a fusion of cosmic history preserved in the veins of stone. Some impact craters are so eroded they're almost invisible. Over millions of years, wind, water, and tectonic motion can erase nearly all traces of a meteor impact. What begins as a vast circular crater gradually fills with sediment, its rim softened and its scars hidden beneath forests or seas. Yet the clues remain in the rocks, shocked quartz, melted minerals, and buried rings of fractured crust that reveal a violent origin. Scientists use satellite imagery and magnetic surveys to uncover these hidden scars, many of which once hosted lakes or entire cities unaware of their cosmic sow. Foundation. In North America, Africa, and Australia, ancient craters have been discovered beneath layers of younger geology, some dating back billions of years. The near invisibility of these structures shows how the planet heals itself, slowly smoothing even the deepest wounds until they become indistinguishable from the land around them. One giant impact may have triggered the age of the dinosaurs. Around 200 million years ago, a massive asteroid may have struck Earth near what is now Canada, coinciding with the end Triassic extinction event. The collision released enough energy to darken skies and ignite wildfires across continents. Volcanic activity followed, and global temperatures swung dramatically. Many reptile species perished, while dinosaurs, better adapted to the changing environment, began to dominate. The crater left behind, though eroded, still carries traces of molten rock and chopped minerals that tell the story of devastation and renewal. Impact events like this one have repeatedly reset the course of evolution, erasing some lineages while clearing the way for others. In the wake of destruction, ecosystems rebalance and entirely new forms of life emerge. From the ashes of chaos, the great reptilian rulers of the Mesozoic rose to power, reshaping Earth's biological future for millions of years. Another may have ended it. 66 million years ago, an asteroid about 10 kilometers wide slammed into what is now Mexico's Yucatan Peninsula, releasing energy equal to Balpao. Billions of atomic bombs. The impact vaporized rock, ignited global wildfires, and threw enough dust into the atmosphere to block sunlight for years. Photosynthesis collapsed, food chains failed, and more than 70% of species vanished, including the Nanavian dinosaurs. The crater it left, Chicxulub, remains buried beneath layers of limestone, but perfectly preserved in shape. Beneath its rim lies evidence of immense heat and pressure, a frozen record of one of Earth's most violent moments. Yet from that extinction came the rise of mammals, and, eventually, humans. The event that ended one age began another, demonstrating how destruction and creation are inseparable in the story of the planet's ever-turning wheel of change. Earth's surface is dotted with hidden scars from ancient collisions. While many impact craters remain visible, countless others lie buried beneath oceans, deserts, or younger rock. Geologists discover them by studying subtle gravitational and magnetic anomalies that betray circular patterns deep below. Some of these hidden scars mark the sites of collisions so ancient that they date back to the earliest eons of the planet. In those times, Earth endured a storm of impacts that reshaped its crust and perhaps even delivered the water and carbon essential for life. These scars, though concealed, are part of the foundation we walk upon, the quiet evidence of a turbulent cosmic youth. Each discovery reminds us that our seemingly stable world has endured unimaginable violence. Over time, erosion and plate tectonics erased the marks, but deep inside the rock, the memory remains, waiting patiently to be read by those who listen to stone chaff. Even today, space dust adds hundreds of tons of new material each day. Our planet is still growing, grain by grain. Every day, tiny particles of cosmic dust drift through space and fall into Earth's atmosphere, burning briefly as meteors or settling unseen onto land and sea. Scientists estimate that more than 100 tons of this material accumulate daily. Most of it comes from comets and asteroids, shedding fragments as they orbit the Sun. Collectors in Antarctica and on rooftops worldwide have gathered microscopic spheres of this interplanetary dust, their metallic surfaces glinting under SAR. microscopes. Over billions of years, such accumulation has subtly increased Earth's mass, even as erosion and the escape of gases have removed some. These particles are reminders that the planet remains connected to the wider cosmos, continuously exchanging matter with the universe around it, a gentle, ceaseless rain of stars falling upon our world. Geology links every mountain, ocean, fossil, and living thing in one story. The study of Earth's history reveals that nothing exists in isolation. The same forces that lift mountains also stir the seas, recycle rocks, and shape the conditions for life. Fossils tell how climate and geography guided evolution, while minerals record the deep processes that sculpted the continents. Every river carries the memory of erosion, and every grain of sand once belonged to stone. Over billions of years, the cycles of plate movement, volcanism, and weathering have woven together an unbroken story connecting land, life, and time. Geology is the language of that story, the script written in layers beneath our feet. It reminds us that the world is both ancient and alive, that everything we see and touch is part of an ongoing transformation, and that by studying the Earth, we are seven. Reading the autobiography of the planet itself, the rocks beneath our feet are the planet's memory, written in stone. Every pebble, cliff, and mountain is a page in the vast diary of Earth. Within their grains lie records of ancient seas, fiery eruptions, glacial ages, and the slow drift of continents. Radiometric clocks measure their ages, while fossils and mineral patterns reveal the climates and creatures that came before us. Rocks remember pressure and heat, flood and drought, creation and decay. Together, they form the grand archive of time, the evidence that the world is always in motion yet endlessly patient. Standing upon solid ground feels like permanence, but in truth we stand atop history in motion, a crust forever forming, breaking, and reforming. To listen to the earth is to hear its long, quiet memory, the murmuring of stone recording the story of a world that has never stopped changing, growing, and remembering itself. Entire continents float like rafts on molten rock. The ground beneath us drifts on a hidden sea of molten rock. Beneath the crust lies the mantle, a region so hot that solid rock behaves like an incredibly slow-moving liquid. The continents rest on this mantle as enormous rafts of rigid stone, drifting across it through time. They slide, collide, and separate at rates of only a few centimeters per year, but over millions of years, those tiny movements reshape the world. Oceans open and close, mountain ranges rise, and entire climates transform. The continents we know are travelers, always in motion, though the journey is invisible to us. This slow drifting is what once united all land into the supercontinent Pangaea, and will one day bring the continents together again. Our planet is alive beneath its calm surface, and we are passengers on its vast drifting plates, carried across geological seas without ever feeling the motion chill. Earth's surface is constantly recycling itself through plate tectonics. Nothing on the planet's surface is permanent. The continents and sea floors we see today are part of an endless process of destruction and renewal known as plate tectonics. Where plates collide, mountains rise. Where they separate, new ocean crust forms as molten rock wells upward. In other places, one plate dives beneath another and sinks back into the mantle, melting to become part of the Earth once more. Even the ground beneath the oceans is born, spreads, and disappears on a timescale of tens of millions of years. Every grain of sand, every cliff, every volcanic plain is part of this great planetary cycle. Earth is the only world we know of that recycles itself so completely, using the slow power of heat and gravity to keep its surface young. The planet's skin is never truly still, but forever shedding and remaking itself in quiet, graceful motion. Mountains rise from plates colliding with immense force. When two plates press against one another, the pressure they generate can lift entire regions of rock skyward. Over millions of years, repeated compression folds and thickens the crust until great mountain ranges rise where flat plains once stood. This is how many of the tallest and most dramatic landscapes on Earth formed. The rocks inside these mountains often reveal astonishing histories, including traces of ancient oceans, deep buried roots, and minerals formed under crushing dowel pressures. As mountains grow, they influence wind patterns, rainfall, and the movement of glaciers. They can even shape the evolution of plants and animals that live along their slopes. Although mountains feel eternal, they are always changing due to the uplift that builds them and the erosion that wears them down. What appears to be solid and timeless stone is actually a monument to the slow collision of plates, rising and reshaping the sky. The Himalaya are still growing taller every year. The tallest mountain range on our planet is not finished rising. The collision between the landmass of India and the continent of Asia continues to push the ground upward as the two plates remain locked in a slow but powerful embrace. The rocks within the Himalaya bear witness to this immense force, showing signs of compression, folding, and uplift that reflect their ongoing rise. As the mountains grow, they influence regional climate by shaping monsoon patterns and capturing moisture carried by winds. Their glaciers feed major rivers that support millions of people. Although erosion carves valleys and wears down the peaks, the collision is strong enough to keep the range ascending over long stretches of time. Standing before these mountains, one can feel the weight of geological history still unfolding. The Himalaya are a living testament to the power of plate tectonics to sculpt the world. New oceans can split open inside continents. Across vast stretches of time, a continent can begin to stretch and thin until great cracks open through its interior. When this stretching becomes intense enough, the land slowly drops downward, forming long rift valleys that grow wider and deeper. Over millions of years, these rifts can fill with water and evolve into new ocean basins. This remarkable process shows that oceans do not only exist between continents, they can be born from the breaking of the continents themselves. As the crust pulls apart, magma rises into the gaps, solidifying into fresh rock and marking the earliest stages of a spreading ridge. What begins as subtle fractures can eventually become full ocean floors with mid-ocean ridges, volcanic activity, and complex coastlines. Scientists study regions like the East African Rift to glimpse the birth of a future ocean. The idea that a sleeping continent can carry a young ocean within its seams reminds us that Earth is always changing, even in the places that appear most stable. Hotspots create islands far from plate boundaries. Most volcanoes appear where plates collide or pull apart, but hotspots are extraordinary exceptions. These deep-rooted plumes of rising heat can punch through the crust in places far from any plate edge. When a hotspot reaches the surface, it feeds volcanoes that can build islands in the middle of oceans or erupt within continents far from tectonic boundaries. Hotspots are believed to tap into regions of the mantle heated enough to push melt upward toward the surface. Their eruptions can form chains of volcanoes that become natural markers of a plate's movement. Some hotspots remain active for tens of millions of years, building large volcanic plateaus or islands that drift away as the plate continues to move. The presence of islands in the middle of vast oceanic plates is one of the strongest clues that hotspots are deep and powerful features of Earth's interior. The Hawaiian Islands march across a fixed mantle plume. The Hawaiian archipelago is a clear illustration of how a plate can glide over a stationary source of rising heat. Beneath the Pacific plate lies a plume that channels hot material upward, feeding volcanic activity at the surface. As the plate moves across this plume, new islands form directly above the hotspot, while older islands drift away and slowly erode. Each island in the chain represents a different moment in the plate's journey across the mantle plume. The youngest island sits above the hotspot and is volcanically active, while the islands further along the chain become progressively older and more worn. Deep beneath the ocean floor, extinct volcanic mountains continue the chain for a vast distance, extending the record far beyond the visible islands. This moving parade of landmasses shows how the slow migration of a plate can create entire island chains that stretch across great reaches of the Pacific Ocean. Earth may one day form a new supercontinent. The continents around us are still moving, and their journeys hint at a distant future where all land masses may once again come together to form a new supercontinent. The slow drift of plates is invisible on human timescales, yet it steadily reshapes the globe. Some researchers envision a future world where the Americas collide with Asia. Others imagine Africa drifting northward to close the Mediterranean and merge with Europe. There are even models that predict an entirely new supercontinent forming near the equator or closer to the northern regions of the planet. No one can say which path the continents will take, but all scenarios share one idea. The surface of Earth is not fixed. It is part of a long cycle driven by heat within the mantle that pushes and pulls the continents in repeating patterns. A future supercontinent would alter climate, ocean circulation, and the entire layout of life on Earth. The quiet drifting we hardly notice today is already guiding the shape of the world that generations far beyond our own will inherit. This distant possibility reminds us that even the continents themselves are temporary forms in an ever-changing planet. The mid-Atlantic ridge pushes continents apart. Beneath the Atlantic Ocean lies a vast underwater mountain chain that snakes from the far south to the icy northern seas. This enormous ridge is a boundary where two plates are slowly moving away from each other. As they separate, molten material from deep inside the Earth rises into the gap and cools to form new ocean floor. This simple process, repeated continuously over immense spans of time, gradually widens the Atlantic Ocean. The continents on either side drift further apart as fresh crust pushes outward from the ridge. Scientists have mapped the ridge using sonar and have discovered that it is not a single smooth line, but a complex landscape of valleys, volcanic peaks, and fracture zones. The ridge is also home to hydrothermal vents, where superheated water rich with minerals bursts from the seafloor and nurtures unique life forms. All of this activity takes place in complete darkness beneath miles of water. The Mid-Atlantic Ridge is one of the longest mountain systems on Earth, and it quietly reshapes the face of the planet with every passing moment. Iceland stands on a ridge that is splitting apart. Iceland is one of the few places on the planet where a major spreading ridge rises above sea level. The island straddles the boundary between the North American and Eurasian plates, which are pulling away from each other. You can visit locations where the ground is visibly cracking open, where valleys widen year after year, and where new crust forms as molten rock wells up from below. This geological setting explains why Iceland is so volcanically active. It sits directly on a place where the Earth opens itself to release heat and magma from deep within the mantle. The island's dramatic landscapes of lava fields, geysers, and steaming vents are reminders of the powerful forces shaping it. Iceland even grows ever so slightly larger as new material fills the space between the separating plates. It is a living laboratory of plate tectonics, offering a rare surface view of a process that usually happens far beneath the oceans. Africa is slowly tearing along the East African rift. Deep within the African continent lies a spreading rift that is gradually pulling the land apart. The East African rift extends for thousands of miles, marked by deep valleys, towering escarpments, and volcanoes that rise from regions where the crust is scanty. Thinning. Lakes fill many of the low-lying areas created by this stretching, and some of these lakes are among the deepest on Earth. The rift is not a single fracture, but a network of faults and uplifted regions shaped by the complex forces pushing from below. Scientists believe that in the distant future this rift may widen enough for ocean water to flood in, splitting eastern Africa into a new landmass. The rift is also home to some of the richest fossil sites on the planet, preserving evidence of early human ancestors who lived along its evolving landscapes. The slow tearing of Africa illustrates how continents change from within, transforming themselves through deep geological processes that operate far beyond the pace of modern life. The Red Sea is an infant ocean in the making. Between Africa and the Arabian Peninsula lies a long and narrow body of water that offers a glimpse into the early stages of ocean formation. The Red Sea sits above a spreading zone where the African and Arabian plates are pulling apart. As the land separates, magma rises to fill the gap, creating new crust that pushes the sides even further apart over time. This process mirrors the early development of major oceans such as the Atlantic. The Red Sea is still young in geological terms, yet it already shows many features of a mature ocean. It has deep basins, active volcanic regions, and hydrothermal systems hidden along its floor. Over immense stretches of time it will widen and eventually grow into a full-sized ocean with its own central ridge. Standing on its shores, you are quietly watching the birth of a future ocean basin. The Red Sea reveals that even today, the planet continues to create new oceans in real time. Australia is drifting northward toward Asia. The continent of Australia is not fixed in place. It is steadily moving northward, riding upon the Indo-Australian plate as it travels toward Asia. Modern positioning instruments placed across Australia measure this motion with remarkable precision, showing that the continent shifts a small but significant distance each year. Over millions of years, this slow drift will bring Australia into closer contact with the islands and landmasses of Southeast Asia. Geological models predict that mountain building and changes in ocean circulation may follow as the two regions interact more directly. Australia's northward journey is part of a larger pattern of plate movements that shape the entire Pacific region. The continent's unique wildlife and ecosystems, which evolved in relative isolation, may encounter new environments in far distant futures. The idea that a massive continent can slide across the surface of the planet without anyone noticing in daily life is a gentle reminder of how quietly Earth moves. Beneath us, California is sliding toward Alaska along a fault. Along the western edge of North America, a complex network of faults marks the boundary between the Pacific Plate and the North American Plate. The most famous of these is the San Andreas Fault, where the plates slide horizontally past each other. This movement carries parts of California slowly toward the region of Alaska over geological timescales. The sliding motion does not happen smoothly. Instead, tension builds along locked sections of the fault until it is released in sudden jolts that we experience as earthquakes. The landscape along the fault bears the marks of this ongoing motion. Streams are offset, valleys are twisted, and even mountains have been repositioned over time. Scientists carefully monitor these faults to understand how stress accumulates and how the land is shifting. Although the movement is measured in small increments each year, the cumulative effect is enormous. Entire regions are gradually migrating northward, guided by forces deep below the surface. Some plates have completely disappeared into the deep. The surface of Earth today is only a snapshot of a world in constant flux. Many plates that once shaped ancient oceans and continents have vanished entirely, carried downward into the mantle through long histories of subduction. Their remnants may linger far below, preserved as distorted slabs detected through seismic imaging. Some of these lost plates once formed major boundaries that influenced climate, ocean currents, and the distribution of life. Over time, as they sank deeper, they became part of the convecting mantle that fuels plate motion itself. Geologists piece together their stories using clues left in mountain belts, island arcs, and magmatic patterns preserved in rocks. These traces reveal where ancient oceans once lay, and how continents approached or retreated from each other. The disappearance of entire plates shows that nothing on Earth's surface is truly permanent. Even massive structures of solid rock eventually return to the depths from which they came. The Juan de Fuca plate is vanishing under North America. Off the western coast of the United States lies a small but significant plate known as the Juan de Fuca plate. It is steadily sliding beneath the North American plate in a region where the ocean floor is being consumed into the mantle. This subduction zone fuels volcanic activity across the Cascade Range, a chain of volcanoes that includes peaks such as Mount Rainier and Mount St. Helens. As the plate descends, it carries water-rich oceanic crust into depths where heat and pressure release fluids that help generate magma. That magma then rises to feed eruptions at the surface. The plate itself becomes more compressed, heated, and altered as it moves deeper into the mantle. Over the long periods of time, the Juan de Fuca plate will disappear completely, leaving only its geological fingerprints behind. Its slow vanishing is part of the ongoing cycle that continually reshapes the margin of North America and renews the crust through subduction and volcanic activity. Ancient plate remnants lie buried deep in the mantle. Far beneath the continents and oceans, past layers of rock that shift over unimaginable spans of time, lie the preserved remains of ancient tectonic plates that disappeared long ago. These slabs sank into the mantle through subduction and now rest as cold, dense regions suspended within the warmer flowing rock around them. Scientists detect these ghostly relics by studying how seismic waves travel through the planet. The waves slow and speed up in patterns that reveal the shapes of hidden structures. Some of these buried slabs may be hundreds of miles long, folded and warped by the great pressures of the deep interior. They record the history of vanished oceans, forgotten boundaries, and long-lost landmasses. Each sunken plate represents a chapter in Earth's past that ended millions of years ago, when the surface changed and the old crust sank from view. The presence of these silent relics shows that nothing on the surface truly disappears. It simply returns to the depths where it becomes part of the planet's long memory, waiting for scientists to uncover its story. The mantle flows like soft, solid rock over vast time. Deep beneath the crust is a realm that seems still and solid at first glance, yet behaves like a slowly shifting sea on geological timescales. The mantle is made of rock that is firm enough to feel rigid in the short term, but warm and pressured enough to flow very gradually over immense stretches of time. This flow moves so slowly that a single inch of displacement can take years, yet the cumulative effect drives the motion of continents and the creation of tema, mountains and oceans. Convection within the mantle circulates heat from the deep interior toward the surface, moving material upward and downward in cycles that last millions of years. The rock deforms in subtle ways, folding and stretching as currents push through it. This seemingly impossible mixture of solid strength and gentle fluidity creates the foundation for plate tectonics. When you imagine the mantle as a soft, ancient current flowing beneath the crust, you begin to sense how Earth continually reshapes itself from within. Heat from Earth's interior drives plate motion. The immense motion of continents and oceans is ultimately powered by the warmth that radiates from the deep interior of the planet. This heat comes from the decay of radioactive elements, the lingering warmth from Earth's formation, and the slow release of energy trapped within the mantle and core. As heat rises through the layers, it creates convection currents that move material in great looping patterns. These slow movements push and pull the plates above, guiding the drift of entire continents. The flow is not forceful in a sudden way. Instead, it is persistent, patient, and constant. Over millions of years, the rising warm material and sinking cooler material create a hidden engine that shapes the surface of Earth. Without this deep internal heat, the crust would remain still, oceans would never open or close, and mountains would not rise. The landscapes we know owe their existence to energy that has been flowing from the heart of the planet since the earliest days of its history. Convection currents stir the mantle like a slow soup. Within the mantle, heat moves upward, while cooler material sinks, creating enormous circulating currents that operate like a gentle churning motion. Although the mantle is solid rock, the pressures and temperatures allow it to deform slowly, permitting these currents to roll through it over millions of years. This movement drives the shifting of plates at the surface. Warm regions rise, spread out beneath the crust, and eventually cool enough to descend again, cycling continuously. These currents vary in speed and shape, depending on the structure of the mantle and the thermal energy rising from below. They can lift parts of the crust, thin others, and create regions of tension or compression. These circulating flows are also responsible for hotspots and other deep plumes that generate volcanic activity far from plate boundaries. When scientists model these currents, they see a planet alive with slow, sweeping motion beneath a shell that appears solid from above. The mantle's internal stirring is one of the great engines of Earth's geology. Slab pull is one of the strongest forces moving plates. Among the many forces that influence plate motion, one of the most powerful is the downward tug exerted by subducting slabs. When a dense oceanic plate sinks into the mantle, its own weight acts like an anchor, pulling the rest of the plate behind it. This process accelerates the movement of the plate across the surface, guiding its direction and speed. The sinking slab drags cooler material downward and helps establish convection patterns that sustain the entire tectonic system. Slab pull can influence the formation of trenches, volcanic arcs, and the motion of continents connected to the plate. Scientists studying plate speeds often find that the fastest moving plates are those with large subducting edges, proving how significant this force is. The strength of slab pull shows that gravity plays a powerful role in shaping the planet. As slabs descend, they help return old crust to the mantle and maintain the long-term recycling process that keeps Earth geologically active. Ridge push helps drive continents across the globe. At spreading ridges where new crust forms, the rising magma pushes the surrounding plates outward. As this hot material cools and becomes part of the ocean floor, it sits slightly higher than older, cooler crust, further away from the ridge. This height difference creates a gentle slope that causes the newly formed crust to slide away, pushing the plates along with it. Although ridge push is not the strongest force affecting plate motion, it adds steady and significant pressure that helps move continents and oceans across the planet. This outward expansion is part of the balance between creation and destruction in plate tectonics. As new crust forms at ridges, older crust is consumed at subduction zones. Ridge push makes sure that the spreading centers continually supply momentum to keep the plates in motion. Over millions of years, this slow outward pressure can shift continents thousands of miles, altering coastlines, climate patterns, and the global layout of land and, quote, sea. The lithosphere floats on a layer called the asthenosphere. The outer shell of Earth, known as the lithosphere, consists of the crust and the uppermost portion of the mantle. It is rigid and strong, forming the plates that move across the planet. Beneath it lies the asthenosphere, a warmer and more flexible layer that behaves in a soft, deformable way over long periods of time. The lithosphere rests on this layer much like a raft on a slow-moving current. Although the asthenosphere is still solid rock, the heat and pressure allow it to flow slowly, enabling the lithosphere to glide above it. The boundaries between these layers influence how plates move, how earthquakes form, and how volcanic regions develop. The contrast between the rigid lithosphere and the softened asthenosphere is essential for plate tectonics to function. Without this underlying layer, the crust would be locked in place, unable to shift or reshape the planet's surface. The floating effect of the lithosphere creates the foundation for a dynamic and evolving Earth. The asthenosphere behaves like a warm plastic layer. The asthenosphere sits beneath the lithosphere and forms a zone of rock that is heated enough to become pliable over long spans of time. It is not molten, yet the combination of heat and pressure allows it to deform like warm plastic. This softening enables the plates resting above to move, bend, and interact with one another. The asthenosphere responds to stresses by flowing very slowly, redistributing material over millions of years. This behavior allows mountain ranges to rise, ocean basins to expand, and rifts to open as plates adjust to forces from below. The asthenosphere also transmits energy from deep convection currents that guide plate motion. Scientists study it through seismic waves that travel differently through this warm layer compared to the cooler, more rigid lithosphere above. The asthenosphere's unusual ability to act as both a solid and a slowly flowing medium makes it one of the most important regions inside Earth. Earth's interior holds more water than all oceans combined. Deep inside the mantle, far beyond the reach of any ocean, is water locked within minerals in quantities that may exceed the combined volume of all the surface. Oceans. This water is not liquid in the traditional sense. It is bound within the crystal structures of minerals that form under intense pressure. As slabs of oceanic crust descend into the mantle, they carry water-rich rocks with them. The minerals transform under heat and pressure, storing water in ways that allow the deep interior to become a vast hidden reservoir. Over time, this water can influence mantle melting, volcanic activity, and the buoyancy of rising plumes. When the mantle brings this water back toward the surface through volcanic processes, it contributes to the long-term cycling of water between the interior and the crust. The existence of this deep reservoir reveals that Earth's water story is far more complex than the oceans alone. The interior of the planet holds secrets that reshape our understanding of where water can exist in solid rock. Subducting plates carry water deep into the planet. When an oceanic plate sinks beneath another, it brings with it water that has seeped into cracks and minerals on the ocean floor. As the plate descends, this water becomes trapped within the rocks and carried into the high-pressure world of the mantle. The deep transport of water sets off processes that can profoundly affect the chemistry and behavior of the interior. At certain depths, minerals release some of this water, which helps melt the surrounding mantle and generate magma. This is one reason volcanic arcs form above subduction zones. Deeper still, other minerals capture water and store it within their structures, contributing to the hidden reservoirs deep inside Earth. This downward journey of water also softens rocks, influences how slabs bend, and helps maintain the long-term cycling of material between the surface and the deep interior. Subduction is more than the sinking of cold crust. It is a conveyor that carries water and minerals into the heart of the planet. That water helps create magma deep below volcanoes. When water is carried downward by a subducting plate, it does something extraordinary within the mantle. As the descending slab heats up, the water locked inside its minerals is slowly released into the surrounding rock. This water lowers the melting point of the mantle and allows it to partially melt at depths far greater than where ordinary surface water could ever reach. The resulting molten material begins to rise because it is lighter than the surrounding solid rock. As it travels upward, it collects in chambers where it evolves, mixes, and gathers enough pressure to feed volcanic activity at the surface. This deep-sourced water-driven melting is responsible for many of the volcanoes that form along subduction zones. The presence of water also influences the chemistry of the magma, contributing to the explosive style of many eruptions in these regions. This process shows that the water cycle of Earth stretches far beyond oceans, clouds, and rain. Water moves silently through the depths and plays a vital role in the creation of new crust and the renewal of landscapes shaped by volcanic forces. Some volcanoes sit directly above subducted slabs. In many mountain belts and island arcs, chains of volcanoes rise in a nearly perfect line above the point where an oceanic plate bends downward beneath a continent or another oceanic plate. These volcanoes form because the sinking slab carries water and minerals deep into the mantle, where they help generate magma that ascends to the surface. The alignment between the descending slab and the overlying volcanoes is so consistent that geologists can trace the geometry of the slab simply by studying growth, the location and chemistry of the volcanoes. In some regions, the slab is so steep that the volcanoes sit close to the trench. In others, the slab dips more gently, pacing volcanoes farther inland. The depth at which the slab releases water can also influence the type of volcanic activity that occurs. These volcanoes often store vast reservoirs of magma that evolve over long periods of time before erupting. They are reminders that the surface of Earth is directly connected to the deep interior by pathways that channel heat, minerals, and molten rock upward from regions far beyond our everyday experience. Tremendous pressure transforms subducting rocks. As oceanic crust sinks beneath another plate, it enters zones of pressure so intense that the rocks begin to change their structure and composition. Minerals rearrange themselves into new forms that can withstand extreme conditions, creating rocks that only exist deep within the planet. Basalts from the ocean floor may transform into dense minerals such as eclogite, which plays an important role in pulling slabs downward because of its stream. Increased weight. Water trapped within the subducting crust can promote changes in mineral structure, further altering the rock. With continued descent, temperatures rise and the rocks undergo additional transformations, recording a journey that few samples ever survive. Occasionally, slices of these transformed rocks are thrust back to the surface through mountain-building processes. When they appear in exposed terrains, they become rare windows into the deep earth. These rocks reveal the intense pressures and temperatures that sculpt the interior of the planet. Their presence at the surface is a reminder that mountains can lift material from astonishing depths, transporting the stories of vanished slabs into daylight. Diamonds form under extreme plate boundary conditions. Diamonds may appear delicate and sparkling at the surface, yet their creation depends on brutal conditions deep within the mantle. They form where pressures are immense and temperatures are high enough to transform carbon atoms into rigid crystalline structures. Many diamonds originate at depths far below the crust, in regions where ancient slabs once descended or where continents have thickened during collisions. The carbon that becomes a diamond may come from the mantle itself or from material carried downward by subducting plates. Over time, volcanic eruptions known as kimberlite events transport these crystals to the surface at incredible speeds, preserving their structures before they can transform into ordinary carbon. The inclusions trapped inside diamonds can contain minerals that only form under extreme conditions, offering clues about the composition of deep earth. Some diamonds even contain tiny pockets of water or gases that reveal information about ancient mantle environments. Each diamond is a geological time capsule shaped by pressure, heat, and the long history of tectonic movement. The oldest ocean floor is shockingly young. Although continents hold rocks that date back billions of years, the ocean floor tells a very different story. Due to the continuous creation of new crust at spreading ridges and its destruction at subduction zones, the ocean floor is constantly being renewed. As a result, the oldest seafloor preserved today is only a small fraction of Earth's age. Older oceanic crust has long since been consumed into the mantle. This youthful nature of the sea floor helps scientists track plate movement, since magnetic patterns and rock ages preserved within it form a clear timeline of kaka, spreading and subduction. The relatively short lifespan of oceanic crust also reveals how efficiently Earth recycles its surface. While continents grow older and accumulate layers of history, the ocean floor undergoes a continuous cycle of birth and descent. This rapid turnover is an essential part of plate tectonics, helping maintain a dynamic equilibrium between creation and destruction across the surface of the planet. Continents preserve billions of years of ancient crust. Unlike the ocean floor, continental crust is thick and buoyant, allowing it to survive far longer without being recycled into the mantle. This buoyancy protects ancient rocks that record some of the earliest chapters in Earth's history. Within continental interiors lie cratons, stable regions composed of extremely old rocks that have withstood countless tectonic events. These ancient fragments preserve minerals that formed when the planet was young, long before complex life appeared. By studying these rocks, scientists uncover evidence of early atmospheres, primitive oceans, and the beginnings of plate tectonic processes. The surfaces we walk upon often contain layers built over eons, recording volcanic eruptions, mountain building events, and the collisions and separations of continents. These preserved histories allow us to trace the evolution of Earth from a young, hot world to the diverse planet we know today. The continents act as vast archives, holding memories that the oceans continually erase. Plate edges can flip and change direction. Plate boundaries are not fixed in their roles. Over long spans of geological time, a region that once experienced spreading may later become a site of subduction. A margin that once pulled apart may later become a zone where plates collide. These flips occur when forces within the mantle shift or when the geometry of plate interactions evolves. Evidence for these changes can be seen in regions where ancient spreading centers have been compressed into mountain belts or where subduction zones have reversed direction. Sometimes the movement of one plate can drag another into a new configuration that alters the stress patterns of the entire region. These transitions show that plate boundaries are dynamic features shaped by the deeper currents of the mantle. They evolve as the planet cools, as slabs sink, and as continents move across the globe. The changing nature of plate edges reveals how adaptable and interconnected Earth's tectonic system truly is. Plates sometimes break into new pieces. Although plates are massive, they are not indestructible. When stresses build within a plate due to mantle forces or collisions with other plates, the lithosphere can crack and split into new fragments. This process creates new plates or microplates, each with its own movement and boundaries. Such breaks can occur within continents or oceans and can lead to the formation of rifts, new spreading centers, or changes in the direction of plate motion. The splitting of a plate can influence volcanic activity, seismic hazards, and the long-term evolution of landscapes. Scientists detect these emerging fractures through patterns of earthquakes, GPS measurements, and the alignment of volcanic features. The creation of new plates shows that Earth's surface is still evolving. Even regions that seem stable can experience deep changes over geological timescales. The fragmentation of plates adds complexity to the global tectonic puzzle, and demonstrates the planet's continual reshaping. Microplates hide between larger plates like puzzles. Between the major tectonic plates lie smaller fragments known as microplates. These pieces occupy narrow zones and often accommodate subtle shifts that larger plates cannot easily absorb. Microplates typically form where stresses create complex patterns of faults and fractures, such as near-spreading centers transform boundaries, or regions where several plates converge. Although small compared to continental plates, microplates play an important role in the overall behavior of Earth's surface. They can move at different speeds and directions, sometimes rotating or sliding between their larger neighbors. Scientists study these microplates to understand how stresses are distributed across plate boundaries and why certain regions experience frequent earthquakes. The presence of microplates reveals that Earth's lithosphere is not simply divided into a few large pieces. It is a detailed, intricate mosaic with many smaller components that fit together like a vast geological puzzle. The Caribbean Plate is a tiny, independent traveler. The Caribbean Plate is one of the smaller but more geologically active plates on Earth. Nestled between the North American, South American, Cocos, and Nazca plates, it moves independently through a region filled with subduction zones, volcanic secti, arcs, and transform faults. Its motion creates a chain of islands that curve across the Caribbean Sea, many of which host active volcanoes fueled by the subduction of the ocean floor. Beneath the plate, the Caribbean Plate also carries deep basins, underwater plateaus, and ancient crustal fragments that hint at a long and complex history. Its boundaries are sites of frequent earthquakes as it interacts with the larger plates surrounding it. The independent movement of this small plate demonstrates that even modest-sized fragments of the lithosphere play significant roles in shaping regional landscapes and hazards. The Caribbean region owes much of its beauty and complexity to the steady motion of this tiny traveler. The Nazca Plate creates the Andes as it subducts. Along the western edge of South America, one of the most dramatic geological processes on Earth unfolds as the Nazca Plate sinks beneath the continent. This subduction generates immense pressure that folds and uplifts the crust, giving rise to the towering Andes. As the oceanic plate descends, it carries water-rich minerals into the deep mantle, where they help generate magma that rises to feed volcanoes along the mountain chain. The interaction between the sinking slab and the overriding continent creates a region of powerful earthquakes and constant reshaping. The Andes stretch for thousands of miles and include some of the highest peaks outside the Himalaya. Their rocks preserve a long history of collisions, volcanic eruptions, and crustal thickening. The ongoing motion of the Nazca Plate ensures that the Andes continue to evolve, slowly rising, shifting, and transforming as one plate dives beneath another. This endless interplay demonstrates how deeply interconnected the surface of Earth is with the great forces hidden below. The Mariana Trench marks Earth's deepest descent. In the western Pacific Ocean lies a feature so deep and shadowed that it feels almost like a boundary between worlds. The Mariana Trench marks the point where the Pacific Plate bends downward beneath the Philippine Sea Plate, creating the deepest known place on Earth's surface. The trench plunges more than 6 miles below sea level, forming a narrow arc of darkness where pressure is immense and sunlight never reaches. Life endures even here in forms adapted to the crushing environment, feeding on nutrients that drift down from above or rise from chemical reactions along the power. Seafloor. The trench is part of the larger subduction system that fuels volcanic arcs, deep earthquakes, and long chains of underwater mountains. The shape of the trench reveals the angle of the descending slab and offers clues about how oceanic crust ages, bends, and eventually sinks into the mantle. The Mariana Trench stands as a reminder that the surface of Earth hides vast realms still largely unexplored. Tsunamis begin when seafloors suddenly shift. Tsunamis are often imagined as enormous walls of water, yet their origins lie in subtle and unseen movements far below the ocean surface. Along subduction zones, stress can build as plates press together until the seafloor abruptly slips. When this locked portion of the plate finally gives way, it lifts or drops large sections of the ocean bottom in a single moment. The displacement pushes huge volumes of water upward, creating long waves that spread across the ocean at incredible speeds. In deep water, these waves are barely noticeable, yet as they approach shallow coastlines, they rise into towering surges capable of reshaping entire landscapes. Volcanic eruptions, landslides, and even meteor impacts can also trigger tsunamis, but the sudden shifting of seafloors is one of the most common causes. Scientists monitor subduction zones and use seismic and ocean sensors to detect these events as quickly as possible. Tsunamis demonstrate how tightly the surface of the ocean is linked to the hidden motion of the plates beneath it. Island arcs form beautiful curving chains across oceans. When one oceanic plate sinks beneath another, a graceful arc of volcanic islands often forms above the point where the descending slab releases water into the bar, mantle. This water promotes melting but generates magma, which rises to build volcanoes at the surface. Over long periods of time, these volcanoes can grow tall enough to break through the ocean and form island chains that bend in sweeping curves. The shape of these arcs reflects the geometry of the subducting plate, which bends into the mantle like a great ribbon. Island arcs, such as those found in the Pacific, are home to lush forests, active volcanoes, and deep ocean trenches that trace the outline of the sinking slab. Their curved form tells a story of motion, pressure, and the deep processes that continually shape the ocean floor. These arcs are dynamic landscapes where earthquakes, eruptions, and island building occur side by side as part of a single interconnected system. Volcanic arcs can grow into massive mountain ranges. Volcanic arcs begin in the ocean, where subduction generates magma that builds volcanoes along a curved line. As time passes and continents drift, these arcs may collide with larger land masses. When this happens, the volcanic islands become welded onto the edge of the continent, adding layers of new crust that can eventually uplift into extensive mountain TT belts. Some of the world's most impressive mountain ranges contain the remnants of ancient volcanic arcs that were long ago sutured to continental margins. These collisions add material to the crust, thicken it, and drive further uplift. The process can also trigger new episodes of melting, feeding additional volcanic activity that contributes to the growing landscape. Over millions of years, erosional forces shaped these mountains into rugged peaks and deep valleys. The origin of such ranges is often recorded in the chemistry of their rocks, which bear the unmistakable signatures of volcanic arcs raised from the sea, transformed into towering landforms. Some continents contain the ghosts of ancient arcs. Hidden within the bedrock of many continents are fragments of volcanic arcs that formed long before humans existed. These arcs once stood as island chains above subducting plates, but over millions of years they drifted toward continents and became fused into their margins. Geologists discover these ghosts by finding rocks with chemical fingerprints that match volcanic arc origins. Some consist of volcanic flows, ash layers, and intrusive bodies that cooled within ancient island settings. Others include deep-sea sediments that were trapped and uplifted as the arc collided with a continent. These preserved fragments provide clues to the history of vanished oceans and the long journeys of plates. They reveal when continents grew through accretion, when they collided with neighboring landmasses, and how mountain belts were assembled. The presence of these ancient arcs shows that continents are patchworks made from many earlier worlds stitched together across deep time. The Himalaya hide rocks that once sat on ocean floors. It may seem impossible when standing before their vast snowy peaks, but some rocks in the Himalaya were once part of ancient ocean basins. When India drifted northward and collided with Asia, the ocean floor between them became trapped and forced upward during the immense compression of the collision. These rocks were folded, crushed, and lifted to altitudes far above sea level. Today they appear as sequences of marine sediments, basaltic crust, and fragments of deep ocean minerals embedded within the highest mountains on Earth. Their presence proves that the Himalaya are the result of a monumental convergence between continents. As the land rose, the once horizontal layers twisted and folded into complex patterns that record the violence and persistence of the collision. These uplifted oceanic rocks provide rare evidence of ancient seas that vanished as land masses collided and reshaped the entire region. The Alps rose from a closing ancient sea. Long before the Alps towered over Europe, an ancient ocean lay between the plates that would eventually form this famous mountain range. Over millions of years, the ocean narrowed as the African plate moved northward, pushing sediments and crust toward the European continent. Eventually, the ocean closed entirely as Africa continued its slow approach. The pressure of this collision forced the seabed upward, folding its sediments into the rising Alps. The rocks within the range record this story in layers of limestone, shale, and metamorphic minerals that were once buried beneath deep seawater. As the collision continued, the crust thickened and mountains grew ever higher. Glaciers later carved the dramatic valleys that now define the landscape. The Alps stand as a testament to the closing of an ancient sea and the immense power of plates converging in a long and patient embrace. Greenland may have been connected to Europe long ago. The island of Greenland, now separated from Europe by the cold waters of the North Atlantic, once lay much closer to the continent and may have been directly connected to parts of what is now Scandinavia. Geological evidence on both sides reveals matching rock formations and ancient mountain belts that suggest these regions shared a common origin before the Atlantic Ocean began to open. When spreading started at the mid-Atlantic ridge, Greenland was carried westward on the North American plate, while Europe drifted eastward on the Eurasian plate. This slow separation widened the ocean between them and isolated Greenland in its current position. Scientists continued to study magnetic patterns, fossil distributions, and rock ages to refine the ancient connection between Greenland and Europe. The history preserved in these rocks reminds us that coastlines and continents shift through time, rearranging themselves in ways that are unrecognizable compared to modern maps. Antarctica once had forests and dinosaurs. The frozen continent of Antarctica, now covered with thick ice and buffeted by relentless winds, once hosted lush forests and thriving ecosystems. Before it drifted to the southernmost part of the globe, Antarctica occupied warmer latitudes where its climate supported trees, flowering plants, and even dinosaurs. Fossilized leaves, petrified wood, and ancient bones have been discovered across the continent, revealing a world utterly different from the icy expanse that, quote, exists today. As Antarctica moved southward on its plate, ocean currents and atmospheric patterns shifted, gradually cooling the region. Over countless millennia, glaciers advanced and the continent transformed into the frozen landmass we know. The ancient forests and animals vanished, leaving only their geological remains. These fossils show that plate motion can drastically alter the fate of entire continents, transforming vibrant landscapes into remote icy deserts through slow and inexorable movement. The Atlantic Ocean was once closed, like the Mediterranean. The wide Atlantic Ocean, which now separates continents and shapes global weather patterns, began as a much narrower and more confined space. Long before its deep waters existed, the area that would one day become the Atlantic resembled something far closer to the present-day Mediterranean. It was bordered by land on many sides and filled with young, shallow seas resting between slowly stretching continental plates. Over millions of years, tension built as the land masses on either side drifted apart. Faults opened, molten material rose, and the first hints of an oceanic basin began to appear. As spreading continued, the narrow seaway widened until an entire ocean unfurled across the planet. The transformation from a closed sea to a vast ocean altered climates, guided the evolution of countless species, and reshaped global circulation. Modern coastlines still carry clues of this ancient transition in matching rock layers and mirrored continental outlines. The Atlantic reminds us that even the largest oceans begin as small rifts, expanding patiently through time. The Mediterranean is a remnant of an older ocean. Today, the Mediterranean appears as a beautiful enclosed sea, bordered by continents and steep coastlines, yet it holds the last surviving waters of an ancient crust ocean known as Tethys. This older ocean once stretched across much of the globe, separating huge land masses before the rise of modern continents. As Africa moved northward and collided with Europe and Asia, the mighty Tethys Ocean slowly closed, leaving behind only small remnants of its once sweeping expanse. The Mediterranean is the most significant remnant of this vanished world. Beneath its waters lie fragments of ancient ocean crust, folded sediments, and mountain roots that formed as the surrounding plates collided. At times in its history, the Mediterranean nearly dried out when its connection to the Atlantic was cut off, filling with thick layers of salt that remain buried beneath the sea floor. Every coastline around it carries clues of the long transformation from a global ocean to an enclosed sea. The Mediterranean stands as a window into a past world that shaped the very layout of modern continents. Plate motion has changed Earth's climate over time. The movement of continents has influenced Earth's climate more profoundly than almost any other natural force. As plates drift across the globe, they redirect the paths of winds and ocean currents, which in turn alter global temperatures and precipitation patterns. When continents cluster together near the equator, they can trap heat and create warm, humid climates. When they drift toward the poles, they can foster cold conditions and encourage the formation of ice sheets. The opening or closing of oceans changes how warm waters circulate, sometimes cooling whole regions or warming others. Mountain building events caused by collisions can also reshape climate by redirecting airflow and affecting how moisture travels across the landscape. Over millions of years, these shifting arrangements have helped trigger ice ages, warm periods, and dramatic swings in global conditions. The slow motion of the plates creates a constantly evolving planet where climate is never truly fixed, but always responding to the shifting shape of Earth's surface. Continental positions affect global ice ages. Earth's history is marked by long cycles of glaciation, and the arrangement of continents plays a major role in determining when ice ages begin. When large land masses drift toward the poles, they provide stable surfaces where snow can accumulate year after year. Over time, this snow compresses into ice sheets that grow thicker and spread outward. The presence of ice reflects sunlight, cooling the planet even further and reinforcing the glacial cycle. If continents cluster in certain patterns, they may also disrupt ocean currents that normally carry warm water to higher latitudes. Without this warmth, polar regions cool dramatically, and ice can advance across vast areas. Geological evidence shows that at different times in the past, continents sat in positions that encouraged global cooling and allowed ice sheets to expand across multiple regions. These slow continental journeys reveal that climate is shaped not only by the atmosphere, but by the shifting geography beneath it. Ocean currents shift when continents move. The oceans circulate through a complex network of currents that transport heat, nutrients, and life across the globe. The shape and position of the continents determine how these currents flow. When a continent drifts into a new position, it can block old pathways and open new ones, radically changing how water moves. The creation of the Drake Passage near Antarctica, for example, allowed a powerful circumpolar current to form, isolating the continent and contributing to its deep freeze. The opening of the Atlantic altered the flow of warm water from equatorial regions, helping shape the climate of Western Europe. As continents separate or collide, narrow seaways can widen into oceans or close entirely, diverting currents into new patterns. These adjustments influence global climate, marine ecosystems, and weather systems. Every shift in ocean circulation is a reminder that plate tectonics guides the heartbeat of the oceans. Some continents once sat near the South Pole. The continents we know today have not always occupied their familiar positions. At various times in Earth's history, several large landmasses wandered into cool southern latitudes, where they spent long periods near the South Pole. Evidence for this polar past comes from glacial deposits, striated rocks carved by ancient ice sheets, and fossils of cold-adapted plants that once grew near the edges of massive glaciers. In some cases, entire continents carried these glacial scars before drifting back toward warmer climates. The shifting of continents through polar regions helped trigger large-scale climatic events, including periods when ice covered much of the planet. These journeys reveal that even the warmest regions known today may once have been frozen landscapes. The wandering paths of continents across latitude lines transform climates on global levels and help explain the dramatic climatic shifts preserved in the rock record. Plate tectonics shapes where animals and plants evolve. The drifting of continents has created new environments, isolated populations, and opened pathways that guided the evolution of life. When a continent splits, species are separated and begin evolving independently, often resulting in entirely new forms. When continents collide, land bridges can form, allowing species to migrate into new territories and compete with existing ecosystems. Mountain building events create fresh habitats with varying temperatures and elevations, encouraging species to adapt in creative ways. The movement of plates also influences climate, which in turn affects where plants and animals can thrive. Over millions of years, these changes have shaped the distribution of life across the globe. Many unique species found on isolated continents owe their origins to long periods of separation caused by plate motion. Plate tectonics is not just a physical process. It is one of the great architects of biodiversity, guiding the rise and spread of life in countless ways. Fossils reveal old continental connections. Long before the theory of plate tectonics was developed, scientists noticed striking similarities between fossils on continents now separated by wide oceans. Identical species of ancient plants and animals were found in distant places, suggesting that these lands were once connected. Fossils of the reptile Mesosaurus appear in both South America and Southern Africa, yet this creature could not have swum across an entire ocean. Fossilized plants from the coal-forming forests of long ago appear on continents now far apart. These puzzles created early clues that continents had drifted through time. Today, these fossil patterns help reconstruct ancient supercontinents, showing where landmasses once joined into larger forms. Fossils provide a biological map of Earth's past geography, confirming that life once moved freely across regions now separated by oceans. They reveal a world far different from our own, shaped by long-vanished connections. South America and Africa share matching geological clues. The eastern edge of South America and the western edge of Africa fit together like two pieces of an ancient puzzle. Beneath their shorelines, matching rock formations, mineral deposits, and mountain structures reveal that these continents were once joined. Identical layers of sandstone, volcanic rock, and ancient sediment appear on both sides of the Atlantic. Fossils preserved in these rocks show that the same plants and animals once lived across a single connected landmass. When the Atlantic began to open, the rift tore this shared landscape apart, leaving mirrored geological features on opposite continents. Today, scientists still use these clues to trace the opening of the ocean and the spreading of the mid-Atlantic ridge. The geological match between South America and Africa is one of the strongest lines of evidence that continents drift, reshaping the world across immense stretches of time. India raced northward faster than any other continent. Among all the continents that have moved across Earth, India holds a remarkable distinction. After breaking away from the ancient supercontinent Gondwana, India began a rapid journey northward across the Indian Ocean. Paleomagnetic measurements reveal that it traveled at a pace far faster than typical plate motion, driven by powerful forces acting on the plate beneath it. India's speedy voyage eventually led to its collision with Asia, an impact so forceful that it built the Himalaya and uplifted the Tibetan Plateau. The rocks in the collision zone preserved the staggering compression created by India's arrival. This journey altered global climate, changed ocean circulation, and reshaped the geography of an entire region. India's fast-moving past shows how even enormous land masses can behave unpredictably under the influence of deep mantle forces. It remains one of the most dramatic examples of continental motion in Earth's history. The collision of India and Asia changed the entire planet. When India reached the southern edge of Asia after its unusually rapid journey, the impact reshaped not only the region, but the entire planet. The force of this continental collision caused the crust to crumple, fold, and rise into the Himalaya, which became one of the tallest mountain ranges on Earth. As India continued to push beneath Asia, the Tibetan Plateau rose and expanded, creating a vast, elevated landscape that influences weather patterns across half Tianjin. The globe. The collision altered atmospheric circulation by redirecting jet streams and strengthening seasonal wind systems. It changed ocean currents, affected the delivery of moisture, and helped shape the monsoon cycle that supports billions of people. The uplifted terrain also exposed deep rocks to erosion, drawing carbon dioxide from the atmosphere as these rocks weathered, which in turn cooled the planet over our long periods of time. This single continental collision demonstrates how the motion of a plate can influence climate, ecosystems, and the global balance of life for millions of years. The Himalaya influence monsoons and global winds. The Himalaya do far more than rise majestically above the landscape. Their immense height and width act as a barrier that shapes the movements of winds and moisture across Asia. When warm, moisture-rich air flows northward from the Indian Ocean, it encounters the towering wall of mountains that forces the air upward. As it rises, the air cools and releases its moisture, creating the intense rainfall that defines the South Asian monsoon. Without the Himalaya, the monsoon would be far weaker, and the climates of India, Nepal, Bhutan, and surrounding regions would be dramatically different. The mountains also influence global wind patterns by deflecting the jet stream and shaping the distribution of atmospheric pressure systems. Their presence helps guide storms, influence seasonal changes, and control the timing of rains essential for agriculture. The Himalaya serve as a vast atmospheric engine, turning the collision of continents into weather patterns that sustain entire civilizations. Deep earthquakes occur where slabs bend into the mantle. Most earthquakes happen close to the surface, yet some originate far below in regions where subducting slabs bend and descend into the mantle. These deep earthquakes can occur hundreds of miles beneath our feet, far beyond the depth at which rocks are expected to break in the usual way. Scientists believe that these deep quakes are driven by unusual processes, such as transformations within minerals that release sudden bursts of energy or the baltar, rapid movement of fluids within the slab. As the descending plate is compressed and heated, its minerals rearrange into new forms that may trigger sudden shifts. These quakes travel through the mantle and provide valuable information about the structure of sinking slabs. Because they occur so deep, they rarely cause damage at the surface, yet they offer a rare glimpse into a world of crushing pressure and intense heat, where the behavior of rock entirely different from that at shallow depths. Some quakes happen hundreds of miles beneath our feet. There are earthquakes so deep that they defy ordinary intuition. These events take place at depths where temperatures and pressures are so extreme that rocks should deform slowly rather than fracture. Yet seismic instruments record sharp jolts of energy from regions deep within the mantle, sometimes originating nearly 400 miles below the CR surface. At these depths, minerals transform into denser forms as they are pushed under overwhelming pressure. These changes can release energy in sudden bursts that behave like earthquakes. Some scientists also suggest that fluids trapped within slabs may trigger deep movement as the plate warms and dehydrates. These deep quakes help map the sinking slabs and reveal their shapes as they plunge toward the interior. They are powerful reminders that Earth remains active at depths far beyond human reach, and that the processes shaping our world extend into the hidden interior where rocks behave in mysterious and unexpected ways. Slow slip events reveal hidden movements along faults. Not all tectonic motion occurs in sudden, violent earthquakes. In some regions, faults move gradually over days, months, or even years in what scientists call slow slip events. During these episodes, the fault surfaces slide past each other at a pace too gentle to cause shaking that humans can feel. Seismic instruments detect faint signals of movement, while GPS stations record small but measurable shifts in the landscape. These slow slips can release as much energy as large earthquakes, yet they do so quietly, offering a peaceful counterpart to sudden seismic ruptures. Sometimes slow slip events precede major earthquakes, while in other cases they relieve stress and reduce the likelihood of a large rupture. Studying them helps scientists understand how faults store and release energy, and how different regions of a fault behave under varying conditions. These silent movements reveal a subtle dance beneath the surface that continues long after the last visible earthquake has faded. Invisible tremor waves vibrate continually through Earth. Deep within subduction zones, tiny vibrations ripple through the crust in patterns known as tremor waves. They are too gentle for humans to feel, yet sensitive instruments detect them as continuous humming signals that can last for hours or days. These tremors often occur alongside slow slip events and may reflect the movement of fluids or the creeping motion of rocks deep within the fault. They do not produce sudden jolts, but instead form a constant background whisper of tectonic activity. Tremor waves help scientists identify the boundaries of subducting slabs and understand how faults behave at depth. Their persistent presence shows that plates rarely rest completely. Instead, they shift and adjust in tiny increments that record the friction, heat, and pressure shaping the subsurface. Tremor waves act as a quiet voice of the deep Earth, carrying information from places too remote and inaccessible for direct observation. Mantle plumes can punch through crust like blowtorches. Mantle plumes are powerful columns of rising hot material that originate deep within the mantle. As they ascend, they bring intense heat toward the crust, sometimes melting it enough to create massive volcanic eruptions. When a plume reaches the base of a plate, it can punch through the crust and form large volcanic provinces or long chains of islands. Unlike volcanoes at plate boundaries, plume-driven volcanoes occur even in the middle of plates, where the crust would otherwise remain relatively quiet. The arrival of a plume can create enormous volumes of magma, reshape landscapes, and influence global climate through the release of gases into the atmosphere. Some plumes remain active for millions of years, leaving trails of volcanic activity that track the movement of the plate above. The power of mantle plumes reveals the deep thermal forces at work within the planet, pushing upward with enough energy to reshape continents and oceans from below. Massive flood basalts once reshaped Earth's surface. Throughout Earth's history, there have been rare but astonishing events in which huge volumes of lava poured onto the surface in repeated eruptions that lasted for hundreds of thousands of years. These flood basalts covered vast regions with thick layers of solidified lava, sometimes stacking into plateaus thousands of feet thick. Such eruptions occurred when enormous quantities of magma rose from deep within the mantle, often associated with the arrival of mantle plumes. The Siberian traps and the Deccan traps are examples of these immense volcanic provinces. The gases released during these events can alter global climate, influence ocean chemistry, and affect life on a massive scale. Flood basalts reshape landscapes, bury ecosystems, and leave behind rock formations that stretch across hundreds of miles. They stand as reminders that volcanic activity can occur not only in small bursts, but also in world-changing episodes that transform the surface for millions of years. The Siberian traps erupted for an astonishing length of time. One of the most dramatic volcanic events in Earth's history occurred in the region that is now Siberia, where repeated eruptions built layer upon layer of basalt across a vast territory. These eruptions were not brief moments, but part of a prolonged episode that continued for an extraordinary length of time. The volcanic activity released immense amounts of gas, including carbon dioxide and sulfur-rich compounds, into the atmosphere. These emissions altered climate patterns, warmed the planet, and affected the chemistry of the oceans. Many scientists believe that the environmental changes triggered by the Siberian traps played a role in one of the largest mass extinctions known from the fossil record. The region today contains thick sequences of basalt that reveal the scale of this ancient volcanic event. The Siberian traps demonstrate how deep mantle processes can influence both geology and life on a planetary scale. The Deccan traps coincide with a global transformation. In what is now India, another enormous volcanic province formed through repeated eruptions that laid down thick layers of basalt, known as the Deccan traps. These eruptions occurred during a period of dramatic planetary change that included shifts in climate and the disappearance of many species. The volcanic activity released large amounts of gas into the atmosphere, influencing global temperatures and altering atmospheric chemistry. Some scientists suggest that the environmental stress caused by the Deccan eruptions contributed to the challenges faced by ecosystems during this period. The timing of these eruptions overlaps with the impact of a large extraterrestrial object, adding complexity to the story of global transformation. The lava flows of the Deccan traps record the scale of volcanic energy unleashed from deep within the mantle. Their presence offers insights into how Earth responds to massive internal and external forces acting simultaneously across the planet. Supervolcanoes are linked to ancient plate interactions. Supervolcanoes are not ordinary volcanic features. They arise from deep-seated processes connected to the slow and powerful interactions of tectonic plates. When plates collide, stretch, or shift over long periods of time, they can create weaknesses in the crust that allow enormous reservoirs of magma to accumulate beneath the surface. Some of these magma chambers grow far larger than those of typical volcanoes, storing vast amounts of molten rock rich in gases. Over immense spans of time, This magma becomes highly pressurized as the heat rises from below and gases concentrate within it. In some cases, the crust above thins or fractures due to old plate boundaries or ancient rifting events, allowing the immense pressure to build without immediate release. When a supervolcano finally erupts, it does so with tremendous force, altering landscapes, affecting global temperatures, and leaving behind caldera's many calcra, miles across. These extraordinary volcanic systems often sit in regions shaped by long histories of plate movement that created the structural pathways allowing deep magma to gather. Their existence shows how ancient tectonic events can leave behind scars that influence eruptions millions of years after the original plate interactions occurred. Yellowstone sits above a deep-rooted hotspot. Beneath the calm forests and steaming geysers of Yellowstone lies a plume of rising heat that originates deep within the mantle. This hotspot remains fixed in place, while the North American plate drifts slowly across it, leaving a trail of volcanic features that stretch across the continent. Yellowstone itself is only the latest expression of this long-lived plume. The heat from below melts the crust, feeding a vast and evolving magma reservoir that powers the region's famous thermal springs, boiling mud pools and occasional prey. Volcanic activity. Although the surface appears peaceful, the landscape rests on layers of cooled lava, ash, and caldera remnants from ancient eruptions. Scientists study the seismic signals passing through Yellowstone to map the shape of the magma chamber and the plume beneath it. The Yellowstone hotspot illustrates how deep thermal forces can shape the surface far from any plate boundary. It is a reminder that the mantle remains active even beneath regions that seem geologically quiet on the surface. Rift valleys can eventually become vast oceans. When continental plates begin to stretch and pull apart, long rift valleys open across the landscape. These valleys are marked by steep cliffs, volcanic activity, and basins that may fill with lakes. As the rifting continues, the crust becomes thinner and magma rises to create new crust along the widening fractures. Over millions of years, the valley deepens and may eventually allow seawater to flow in, transforming the rift into a young ocean basin. This is how many of Earth's major oceans began, including the Atlantic, which opened from a similar rift long ago. Rift valleys such as the East African Rift show the early stages of this transformation. The spreading forces, volcanic activity, and changing landscapes reveal a young continent beginning to reshape itself. If the rifting continues, the land will split entirely, creating coastlines and new oceanic crust. Rift valleys are gateways to the birth of oceans, offering a glimpse into the slow but profound processes that reshape continents. The Atlantic once looked like today's East African Rift. Before the Atlantic Ocean became the vast expanse we know, it began as a narrow system of rift valleys that resembled the modern East African Rift. Faults opened through a once continuous landmass, creating long depressions bordered by high cliffs and volcanic fields. Seawater had not yet entered the rift, and the region would have appeared as a landscape filled with lakes, young volcanoes, and widening valleys. As the continental crust stretched, it eventually thinned enough for magma to rise and produce new oceanic crust. Once this process began, seawater flooded the region, and the rift transformed into a developing ocean basin. Over immense stretches of time, continued spreading widened the basin into the ocean we know today. Studying the East African Rift allows scientists to watch a similar process in real time. It provides a living window into the earliest stages of ocean formation, echoing the distant past when the Atlantic was little more than a cracking seam between drifting continents. Transformed faults allow plates to slide sideways. Along transformed faults, tectonic plates neither collide nor pull apart. Instead, they slide past each other horizontally in a movement known as strike-slip motion. These boundaries can extend for hundreds of miles and are often marked by straight valleys, offset streams, and linear ridges that show the direction of the sliding motion prey. Despite their quiet appearance, transform faults store significant stress as two massive blocks of crust grind against one another. When this stress is released, earthquakes occur. Some transform boundaries lie along ocean floors, connecting spreading ridges into continuous networks. Others cut across continents, shaping the landscapes above them. Transform faults play a crucial role in accommodating the motion of plates as they move in different directions. They act as edges that release built-up energy slowly over time or suddenly through seismic jolts. These sideways moving boundaries reveal another dimension of plate tectonics, showing that the Earth's surface shifts in more ways than simple pushing or pulling. The San Andreas Fault is only one of many transform boundaries. The San Andreas Fault is widely known for its seismic activity, yet it is only one example of a transform boundary among many distributed across the ND globe. This fault marks the meeting point of the Pacific Plate and the North American Plate, which slide past each other in a slow but persistent motion. The region contains countless smaller faults branching from the main boundary, each contributing to the complex behavior of the system. However, transform boundaries of similar nature exist in Africa, the Middle East, New Zealand, and along mid-ocean ridges. Many of these boundaries generate frequent earthquakes and shape the landscapes around them. Some lie beneath the ocean, hidden beneath thousands of feet of water, yet they play an essential role in guiding the movement of plates across the seafloor. The San Andreas is famous because it cuts through populated regions, but the global network of transform boundaries is far larger, revealing how common sideways plate motion truly is. Continental crust thickens under colliding plates. When continents collide, the crust between them undergoes compression so intense that it thickens dramatically. Rocks stack upon one another, fold into intricate patterns, and may even be thrust upward along large faults. As the crust thickens, it becomes buoyant and rises, forming mountain ranges that can stretch across entire regions. Deep beneath these mountains, rocks are subjected to high pressures and temperatures, transforming into new metamorphic forms. Some rocks may even melt partially, feeding volcanic activity in the collision zone. The thickened crust also affects gravity, groundwater flow, and erosion patterns. Over millions of years, erosion exposes deeper layers, revealing the complex internal structure of the mountain belt. Regions such as the Himalaya and the Alps contain crustal thicknesses far greater than the global average, demonstrating the immense power of continental breccia. Collisions. The thickening of the crust is one of the clearest indicators of the forces at work when continents converge. Tectonic pressure can warp land without breaking it. Not all deformation caused by tectonic forces results in fractures or faults. In many regions, pressure builds gradually and bends the crust into smooth, sweeping curves known as folds. These folds can extend across miles of rock and may take millions of years to develop. The layers bend because the crust behaves like a solid over short periods of time, yet becomes more flexible when pressure acts slowly across vast spans of time. The result is a landscape shaped not by sudden breaks, but by gentle, persistent warping. These folded structures can appear in mountain belts, along continental margins, or in regions where plates compress one another. Their shapes reveal how rocks flowed and adjusted to the pressure without shattering. By studying folds, scientists can reconstruct the history of stress that shaped the land. These graceful curves remind us that the Earth bends long before it breaks, recording its slow adjustments in patterns carved deep into the crust. Rocks can fold into immense curving structures. Under the right combination of heat, pressure, and time, Rocks that seem rigid and unyielding can fold into elegant arcs that stretch across entire mountain ranges. These folding events occur when tectonic forces compress the crust, squeezing layers of sedimentary or metamorphic rock into looping shapes. Some folds are gentle and broad, while others are tight and intricate, reflecting the intensity of the forces that shape them. These structures can rise into anticlines, where layers arch upward, or sink into synclines, where layers bend downward. Over millions of years, erosion can carve through these folds to reveal their internal patterns, creating dramatic cliffs and valleys. Folds record the history of continental collisions, the motion of ancient seas, and the long evolution of mountain belts. They show that rocks are not static, but capable of bending and flowing when the planet presses upon them with slow, persistent force. Some mountain ranges hide entirely buried roots. Beneath many mountain ranges lie deep roots that extend far into the crust, balancing the immense height of the peaks above. These roots form when the crust thickens during continental collisions. The buoyant mass of rock sinks deeper into the mantle, much like the submerged portion of an iceberg beneath the water. Although hidden from sight, these roots play a crucial role in supporting the mountains and stabilizing the range. Over time, changes in temperature, pressure, and erosion can remodel these deep structures. Some roots slowly rise as the mountains erode, bringing ancient rocks to the surface. Others remain buried, preserved as frozen reminders of long-vanished mountain belts. By studying seismic waves, scientists can map these hidden features and discover the full extent of ancient collision zones. Mountain roots reveal that every tall range has a vast, unseen counterpart below, shaped by the same forces that lifted the peaks toward the sky. Plate tectonics creates Earth's most valuable minerals. Many of the minerals we consider precious or essential are created or concentrated through the movement of tectonic plates. When plates collide, separate, or slide past one another, they generate heat, pressure, and fluid circulation that move elements through the crust. These forces create perfect environments for minerals to grow and collect in rich deposits. Gold, copper, zinc, silver, and countless other metals often form in regions shaped by ancient subduction zones or volcanic arcs where fluids carried dissolved metals through cracks and pores. As these fluids cool, the metals crystallize into veins that can become valuable ore deposits. Diamonds are formed under pressures associated with deep continental roots and are brought to the surface through volcanic events linked to plate motions. Even gemstones such as sapphires, rubies, and emeralds owe their origins to metamorphic and igneous conditions created by shifting plates. Without plate tectonics, the crust would remain far more uniform and would lack the concentrated mineral deposits that support modern technology, human civilization. Many ore deposits form at ancient plate boundaries. Some of the richest mineral resources on the planet are found along boundaries where plates once collided or split apart. These ancient zones are preserved in the crust long after the original tectonic activity has ended. During the time when the plates moved, fluids rich in metals circulated through cracks and faults, depositing minerals as they cooled. Over millions of years, additional layers of rock buried these deposits, protecting them until erosion or uplift brought them closer to the surface. Volcanic arcs created during ancient subduction events often contain gold and copper deposits, while rift zones can hold minerals such as lead, zinc, and rare earth elements. Even regions that appear calm today may hide deep geological histories rich in ore-forming processes. The metals that support modern society often originate in these long-forgotten tectonic environments, showing how deeply the Earth's shifting plates influence human life. Earth's magnetic field records plate motion in stripes. As molten rock rises along spreading ridges and cools to form new ocean floor, minerals within the rock align with the Earth's magnetic field. Because the magnetic field has flipped many times throughout history, these minerals capture a record of the field's direction at the moment they solidify. As plates move away from the ridge, they carry these magnetic signatures with them. The result is a symmetrical pattern of magnetic stripes on either side of the ridge, with each stripe reflecting a past magnetic reversal. These patterns allow scientists to determine how fast plates spread, how often the field has flipped, and how ocean basins have evolved through time. The magnetic stripes provide a natural barcode of Earth's geological past, revealing the steady creation of crust and the gradual drift of continents. This discovery was one of the crucial pieces of evidence that confirmed the reality of plate tectonics and transformed our understanding of Earth's history. Seafloor stripes proved that continents move. Before the discovery of magnetic stripes on the seafloor, the idea that continents drifted was controversial. Many scientists were skeptical that entire land masses could move across the Earth's surface. The symmetrical bands of magnetic patterns on either side of the mid-ocean ridges changed everything. These stripes showed that new crust was continuously formed at the ridges and pushed outward in both directions. The discovery provided a clear, measurable record of spreading and proved that continents attached to the plates must be moving as well. The stripes revealed the age of the seafloor, with younger rocks near the ridge and progressively older rocks farther away. This evidence demonstrated that the seafloor was not static, but constantly renewed and shifted by tectonic forces. Combined with other clues such as fossil patterns, matching coastlines, and seismic activity, the magnetic stripes offered decisive proof that continents drift over time. This breakthrough led to the acceptance of plate tectonics as the unifying theory of geology. The theory of plate tectonics revolutionized geology. Before plate tectonics, many geological phenomena seemed disconnected. Mountain ranges, earthquakes, volcanoes, and continental shapes were understood only in fragments. When the theory of plate tectonics emerged, it unified all these observations into a single, elegant explanation. It showed that the Earth's lithosphere is divided into moving plates that drift on the softer mantle below. With this understanding, scientists could explain why earthquakes follow clear boundaries, why volcanoes form in arcs, why continents fit together like puzzle pieces, and why rocks of similar age appear on opposite sides of oceans. The theory reshaped the study of Earth, guiding new research in paleontology, climate science, mineral exploration, and planetary evolution. Plate tectonics revealed that the planet is dynamic and alive with slow but powerful forces that continually renew and reshape its surface. It stands as one of the most important scientific concepts of the modern era, transforming our understanding of Earth from a static world into a living, shifting system. GPS stations track plate movement with stunning precision. Around the globe, thousands of GPS stations quietly observe the movement of tectonic plates. These instruments detect changes in position so small they would be invisible to the naked eye. Over days, months, and years, the stations record the steady drift of continents, the gradual buildup of strain along faults, and the subtle deformation of tidal air. Landscapes responding to deep forces below. Scientists use this data to create detailed maps of plate motion, revealing which regions are moving fastest, which are locked under stress, and which are slipping slowly. GP's observations have shown that even the most stable appearing regions experience movement. These precise measurements help predict where seismic hazards may be higher and allow researchers to monitor changes near volcanoes and earthquake zones. The wealth of information gathered by GPS has transformed plate tectonics from a theory based on geological evidence into a real-time observation of chaos. Earth's surface in motion. Volcanoes on different plates erupt in distinct styles. The style of a volcanic eruption depends deeply on the tectonic setting in which the volcano forms. Volcanoes above subduction zones often produce explosive eruptions because their magma is rich in dissolved gases and thick in consistency. These volcanoes may create towering ash plumes and powerful pyroclastic flows. In contrast, volcanoes located on spreading ridges or hotspots often produce flowing lava that spreads out in wide, gentle sheets because the magma is hotter and less viscous. Some volcanoes erupt underwater, forming pillar-shaped lava as it cools instantly upon contact with seawater. Others build tall volcanic islands or produce repeated eruptions that form entire mountain chains. Each tectonic setting influences the chemistry, temperature, and gas content of the magma, shaping the way the volcano behaves. The diversity of volcanic styles reflects the diversity of plate interactions and the deep processes that generate magma in different environments. The shape of coastlines echoes ancient connections. Many modern coastlines reflect the scars of ancient rifting and the remnants of long-vanished connections between continents. When landmasses split apart, the jagged edges of the separation can create coastlines that mirror one another across great distances. The famous match between the coasts of South America and Africa is only one example. Other regions, such as the margins of India, Antarctica, and Australia, also contain clues of past arrangements. Subtle indentations, promontories, and curved bays may all be shaped by the geometry of ancient faults and the stretching that occurred during the breakup of Kao. Supercontinents. Some coastlines sit along old, passive margins where rifting once opened new oceans. Others mark places where continents were torn into fragments and carried far apart. The shape of a coastline is often more than a natural border. It is a geological memory, preserved in rock and geography, hinting at the long journeys continents have taken. Earth's surface would be flat without plate tectonics. If plate tectonics did not exist, Earth would be a very different and surprisingly dull world. The constant motion of plates creates mountains, valleys, volcanoes, islands, and ocean trenches. Without these forces, erosion would slowly wear the surface down until the planet became a mostly uniform low-lying landscape. There would be no towering peaks like the Himalaya, no deep trenches like the Mariana, and far fewer volcanic islands. The continents would have much less variation in climate because mountains play a major role in directing winds and rainfall. The diversity of ecosystems would be dramatically reduced. The Earth's interior heat would remain trapped, with no efficient way to release it. Plate tectonics is responsible for nearly every major landform. It constantly renews the crust, allowing fresh landscapes to rise and old ones to disappear. Without it, the planet would be smoother, quieter, and far less dynamic. Life on Earth may depend on plate-driven recycling. The movement of plates does far more than reshape landscapes. It drives a long-term recycling system that helps regulate the atmosphere, oceans, and climate in ways essential for sustaining life. When volcanoes release gases from the mantle, they replenish the atmosphere with carbon dioxide and other elements necessary for plants and marine organisms. When mountains rise and erode, their minerals react with the atmosphere and draw carbon dioxide out, helping to stabilize global temperatures. Subduction carries water and carbon-rich rocks into the mantle, where some of the material eventually returns through volcanic activity. This slow exchange of elements between the surface and the interior maintains a balance that keeps Earth habitable. Without plate tectonics, the carbon cycle could stall, oceans could lose vital nutrients, and the planet might become too hot or too cold for complex taos. Life. Plate motion may be one of the key reasons Earth remains a living world. Plate tectonics helps regulate carbon through deep time. Earth's carbon cycle is not limited to the atmosphere, oceans, and living organisms. Deep within the crust and mantle, plate tectonics drives a powerful and long-term exchange of carbon that helps keep the planet's climate stable. When mountains rise through continental collisions, rocks rich in minerals that react with carbon dioxide are exposed to rain and air. Over millions of years, these reactions remove carbon dioxide from the atmosphere and store it in carbonate rocks. At the same time, subduction carries carbon-rich sediments into the mantle, where some of this carbon is stored for immense stretches of time. Volcanoes later release portions of it back into the atmosphere, returning carbon that would otherwise be locked away forever. This balance between storage and release prevents carbon dioxide levels from rising or falling too dramatically across geological ages. Without the constant recycling driven by plate motion, Earth's climate would drift into extremes that could endanger life. The interplay between the surface and the deep interior reveals a planet that regulates itself slowly and steadily through its own tectonic heartbeat. Without plate motion, Earth might resemble a lifeless world. The slow drifting of continents and the recycling of crust may seem unrelated to life, yet they are essential for maintaining the conditions that allow organisms to thrive. Without plate motion, the deep carbon cycle would stagnate. Volcanoes would become rare, shutting down the natural release of gases that replenish the atmosphere. Weathering of mountains would slow, reducing the drawdown of carbon dioxide that keeps global temperatures in balance. Oceans would lack many of the minerals and nutrients delivered by volcanic eruptions and the erosion of rising mountain ranges. Over time, the atmosphere could become too hot, too cold, or too depleted to sustain life as we know it. Planets without plate tectonics often show signs of climate instability or atmospheric loss. By continually renewing the crust and recycling essential elements, plate motion helps maintain a dynamic equilibrium that supports complex ecosystems. Earth's living richness is closely tied to the restless movement beneath its surface. Venus may lack plate tectonics and shows the consequences. Venus is often called Earth's twin because of its similar size and overall composition, yet its surface tells a very different story. Unlike Earth, Venus appears to lack active plate tectonics. Instead of a mosaic of moving plates, its crust seems to behave as a single rigid shell. Without subduction zones to recycle heat and material, the planet's interior may trap energy until it is released in catastrophic volcanic resurfacing events. Much of Venus is covered by lava plains that suggest large-scale eruptions reshaped the surface in relatively recent geological times. The atmosphere of Venus is dominated by thick clouds of carbon dioxide, creating temperatures hot enough to melt lead. Without the cooling, recycling, and balancing effects of plate motion, carbon may have accumulated unchecked in the atmosphere. Studying Venus helps scientists understand the importance of tectonics in regulating planetary environments. It offers a glimpse of how a world similar to Earth can become hostile when deep geological processes operate differently. Mars displays clues to an ancient tectonic past. The surface of Mars appears quiet today, with no clear signs of active plate tectonics. However, its landscapes contain hints that the planet may once have experienced tectonic processes during earlier stages of its history. Large volcanic structures such as Olympus Mons rise to heights far greater than anything on Earth, suggesting that the crust remained stationary over long-lived gray. Volcanic hotspots. Rift valleys like Valles Marineris stretch for thousands of miles and resemble features formed by crustal stretching. Magnetic stripes preserved in the crust of Mars hint that its magnetic field may once have reversed, a behavior associated with tectonic cycling on Earth. Although Mars no longer shows evidence of active plates, these ancient signatures suggest that the planet once possessed internal heat and forces capable of reshaping the surface. Over time, Mars cooled and its crust thickened, shutting down tectonic motion. The remnants of its tectonic youth reveal how planetary interiors evolve and how their geological stories unfold. Some exoplanets might have their own form of plate motion. As astronomers discover planets orbiting distant stars, they are beginning to identify worlds that may possess tectonic processes of their own. The movement of plates depends on a delicate balance between internal heat, crustal composition, and the presence of water or other materials that allow the surface to deform. Some rocky exoplanets may be large enough and warm enough to sustain convection within their mantles, creating forces capable of driving plate motion. Others may have surfaces that deform in ways unlike Earth, producing unique forms of tectonics shaped by different compositions or temperatures. Observations of their atmospheres may reveal gases associated with volcanic activity, while studies of their densities and thermal properties hint at dynamics. Interiors. If tectonics is common among rocky planets, then many worlds across the galaxy could maintain climates and environments capable of supporting life. These distant planets may demonstrate that Earth's geological vigor is not unique. Tectonic activity can create habitable conditions on other worlds. On any planet, life depends on a stable climate, a supply of nutrients, and the recycling of essential elements. Tectonic activity can provide all three. When plates move, they expose fresh rocks to weathering, releasing minerals into oceans or lakes. Volcanic eruptions release gases that help maintain an atmosphere capable of trapping heat. The recycling of crust moves carbon and water between the surface and the interior, preventing the atmosphere from becoming too thick or too thin. On worlds with enough internal heat and a flexible crust, tectonics could help maintain habitable conditions for billions of years. Even moons orbiting giant planets might experience tectonic-like processes driven by tidal forces, rather than internal heat alone. In such places, the bending and stretching of the crust could generate heat that melts ice and maintains subsurface oceans. Tectonics, in all its forms, is one of the most powerful engines for creating environments where life could flourish. Earthquake lights might be linked to tectonic stresses. Across history, people have reported mysterious glows, flashes, or faint illuminations in the sky before or during earthquakes. These rare phenomena, known as earthquake lights, remain one of the most intriguing puzzles in geology. Some scientists propose that intense tectonic stresses deform rocks in ways that release charged particles into the air. These particles may ionize the surrounding atmosphere, creating faint glows or flashes of light. Others suggest that friction along faults generates electrical fields strong enough to produce visible effects. Although the exact cause remains uncertain, these lights are often reported near major fault zones or during strong seismic events. Modern instruments occasionally detect unusual electromagnetic signals before earthquakes, hinting that the rocks under stress may behave in unexpected ways. Earthquake lights remind us that tectonic processes can influence not only the ground beneath our feet, but also the air above, producing phenomena that blend geology with atmospheric physics. Strange rocks called ophiolites reveal ancient ocean floors. In some mountainous regions, geologists find unusual rock sequences that once formed the crust of ancient oceans. These rocks, known as ophiolites, include layers of deep-sea sediments, oceanic crust, and upper mantle material that were thrust upward during ancient collisions between plates. Ophiolites provide a rare chance to study parts of the ocean floor without needing to drill deep beneath the sea. Their minerals record the chemistry of ancient spreading ridges, the movement of hydrothermal fluids, and the structure of the mantle beneath old oceans. They reveal how oceanic plates formed, aged, and eventually met their end in subduction zones. These rocks are often found in mountain belts created by continental collisions, where slices of oceanic crust were scraped off and preserved on land. Ophiolites allow scientists to reconstruct the vanished oceans that once separated continents and to understand how the seafloor evolves through time. Some continents carry fragments of completely lost plates. Not all tectonic plates of the past survive today. Some were entirely consumed by subduction, yet pieces of them remain embedded within continents as small fragments of ancient crust. These fragments may appear as unusual geological terrains that do not match the surrounding rocks. They often contain fossilized ocean floor, volcanic arcs, or island remnants carried long distances before becoming welded to a continent. By studying these fragments, scientists identify the paths of lost plates and the oceans that once existed between landmasses. These preserved pieces reveal the complexity of Earth's tectonic history, showing that continents grew through the gradual addition of pieces torn from other regions. Each fragment carries a record of environments that no longer exist, including coral reefs, volcanic islands, and deep ocean sediments. They are geological time travelers, offering glimpses of landscapes erased from the surface long ago. Earth's restless crust continues to shape its future. Even now, with continents appearing familiar and oceans seemingly permanent, the surface of Earth remains in motion. Plates continue to drift, collide, open rifts, and build mountains. Volcanoes erupt along boundaries and hotspots, seeding new land with minerals and gases. Earthquakes shift coastlines and reshape valleys in moments, revealing the tension stored over years. The planet is not finished evolving. New oceans will form where continents stretch, and existing oceans will close where plates converge. Mountains will rise in some regions and erode in others. Climate patterns will shift as continents wander toward new latitudes. The slow but unstoppable movement of Earth's crust ensures that the planet of the distant future will look very different from the world we know. Plate tectonics continues to write the story of Earth, one slow-motion chapter at a time. Mountains are born from the slow collision of continents. Far beneath your feet, continents move at the speed that fingernails grow. Yet when they meet, their strength is unstoppable. Over millions of years, these vast slabs of rock push against each other until the crust begins to buckle and fold. What was once a flat seabed rises inch by inch, becoming the ridges and summits that crown the world. These collisions are slow but relentless, driven by the deep motion of Earth's molten mantle. The Himalayas began this way when the Indian plate collided with Asia, crushing upward the highest mountains on Earth. Each peak carries the memory of that impact, a frozen wave of stone still rising in silence. To look at a mountain is to see the moment continents met and refused to let go, turning pressure into beauty and time into height. The color of a mountain reveals its geological story. Every shade of a mountain's surface speaks of the minerals that built it and the processes that shaped it. Rusty red slopes often contain iron that has oxidized like old metal, while greenish hues suggest the presence of copper minerals. Pale cliffs of limestone mark ancient seabeds, while dark volcanic rock tells of eruptions from the deep mantle. In deserts, mountains can shimmer in pink, ochre, or violet, painted by layers of sediment deposited over eons. Some peaks change color, with the light glowing gold at sunrise and blue at dusk. Even the snow that crowns them can carry stories, tinted by volcanic ash or desert dust carried on the wind. To geologists, a mountain's palette is a language of time and chemistry. To the rest of us, it is beauty distilled into stone, the Earth's memory written in color. Some glaciers hide entire mountain ranges beneath them. Beneath certain polar ice sheets, the surface looks deceptively smooth, a gently rolling plain of white that stretches to the horizon. Under that calm exterior, radar instruments have revealed rugged landscapes with peaks, ridges, and deep basins completely buried in ice. These hidden mountains can rival well-known ranges in height and complexity, yet they have not seen open sky for an immense span of time. The ice above presses down with great force, filling valleys and smoothing sharp edges, but the stony skeleton of the range still shapes how the ice flows. Subtle humps on the surface can mirror towering peaks thousands of feet below. Meltwater streams may be guided along buried ridgelines, feeding secret lakes that never feel the warmth of the sun. In these concealed highlands, geology and glaciology intertwine, creating a world that modern instruments are only beginning to map in detail. Mountain shadows can stretch for hundreds of miles at sunrise. When the first light of dawn strikes a tall peak, it casts a long shadow that can extend far across the landscape, tapering to a sharp triangle even if the mountain T itself is irregular. This happens because the sun is low on the horizon, turning the entire Earth into a canvas for light and geometry. On massive peaks like Everest or Kilimanjaro, the shadow can stretch for hundreds of miles, visible as a perfect pyramid of darkness against the glowing air. Climbers often watch this phenomenon from the summit, seeing their own mountain projected across the morning sky. As the sun rises, the shadow shortens and fades, swallowed by the light. The moment lasts only minutes, but it feels timeless, as though the mountain itself were awakening, casting its first breath into the dawn before vanishing into day. Some mountains rise faster than they erode away. It may seem that erosion always wins, carving mountains into valleys and plains. Yet in some places, the Earth's upward push outpaces the slow work of wind and water. When tectonic forces lift the land more quickly than rain and ice can wear it down, summits grow higher even as they crumble. In the Andes, parts of the range are still climbing at a rate of several millimeters each year. The crust beneath them thickens as if breathing upward. Rivers that try to cut valleys through the rising stone find themselves trapped in narrow gorges, unable to keep up. This delicate balance between uplift and erosion shapes the drama of the landscape, where time becomes a race between the forces that build and those that destroy. Each growing mountain is a slow-motion victory of the deep earth over the endless patience of the sky. There are glaciers so clear they look like frozen glass. Most people think of glacier ice as white or softly blue, but in some rare places, the ice becomes astonishingly transparent. Over time, layers of snow are compacted so thoroughly that almost all the tiny air bubbles are squeezed out. The ice crystals grow larger and more uniform, scattering less light and allowing it to pass straight through. When such ice is exposed in a broken wall or along a polished surface, it can resemble a window into the heart of the glacier. Stones, trapped leaves, or small pockets of older, cloudier ice appear suspended in a clear medium, as if held in a glass sculpture. This clarity is not only beautiful, it tells scientists that the ice has experienced intense pressure and careful, orderly growth deep within the glacier. What began as fluffy, reflective snowflakes has transformed into a dense, luminous solid that reveals the patient work of time and pressure. Some mountains have permanent lenticular clouds shaped like flying saucers. Above certain peaks, when strong winds flow steadily across the landscape, smooth, lens-shaped clouds can form and hover in place. These are lenticular clouds, created when air rises over a mountain, cools, and then sinks again in a repeating wave. To those who see them, they often appear otherworldly, glowing pink and gold at sunset, their curved edges sharply defined. Pilots avoid flying near them because the air beneath can churn with turbulence. In places like Mount Fuji, Mount Rainier, and the Andes, these clouds come stacking layers like floating disks. They seem motionless, but inside them, air rushes in constant motion. For centuries, lenticular clouds have inspired myths and mistaken reports of strange objects in the sky. Yet their beauty is simply the breath of the planet made visible, a reminder that even still air hides waves we cannot see. Entire mountain ranges can move across the planet over time. Mountains may appear fixed and eternal, but they are passengers on drifting continents. As tectonic plates glide across the planet's surface, they carry entire ranges with them. The rocks of the Appalachians, for instance, were born near the equator and have traveled thousands of miles north over hundreds of millions of years. The Alps, too, have migrated across shifting crust, carried like wrinkles on the moving skin. Even volcanic mountains, seemingly rooted in place, can drift if the hot spots beneath them change position. Each range carries within its layers a record of the journey, fossils of tropical seas hidden inside icy summits, hints of the worlds they once inhabited. Though the movement is invisible in a single lifetime, the continents never sleep. They glide through deep time, and the mountains move with them, crossing oceans of stone. Ancient air is trapped inside glacier ice. When snow falls on a cold landscape and never fully melts, each layer buries the one before it. As the snow is compressed into firn and then into solid ice, tiny pockets of atmosphere become sealed inside. These microscopic bubbles are time capsules. They hold the very air that once flowed around living creatures, over oceans and forests, through storms and quiet days long ago. By drilling deep into thick ice and bringing long cylinders of it back to the surface, researchers can sample those bubbles and measure the gases within. They can detect changes in carbon dioxide, methane, and other components that reveal how the climate has shifted through ages of ice and warmth. Each depth corresponds to a different moment in planetary history, stacked one upon another in a frozen archive. It is as if the glacier carries a layered record of breaths, storms, and seasons from worlds that no human ever saw. Some mountains are made of rock older than the continents themselves. Deep within the ancient cores of our planet's oldest ranges lie rocks that date back more than 4 billion years, nearly to the dawn of Earth's formation. The Acasta gneiss of northern Canada, for example, formed when the planet's crust was still cooling from its fiery youth. These rocks have survived collisions, erosion, and the birth and death of entire continents. They are fragments of Earth's first crust, transformed by pressure, but never erased. To hold one of these stones is to touch a relic from a time when the planet's surface was still molten and life had not yet begun. Mountains built from such ancient rock are like fossils of the Earth itself, carrying within their crystals the record of creation. They are the oldest witnesses to our planet's long and restless story. Older than the seas, older than the continents, older than memory. The oldest mountain range on Earth is nearly unrecognizable today. In South Africa, the ancient Barberton Greenstone Belt holds the remnants of the planet's first mountains, born more than 3 billion years ago. They no longer stand tall, worn down by billions of years of wind, water, and shifting crust. What remains are low hills and twisted rocks that once formed volcanic peaks and deep ocean floors. Within their layers lie microscopic fossils of some of Earth's earliest life forms, tiny traces of bacteria preserved in stone. These mountains existed when the sky was filled with volcanic haze and the oceans were green with iron. They watched the birth of continents and the arrival of oxygen. Though their summits have long since crumbled to dust, their story endures in every grain of rock. The Barberton Range is a memory of Earth before it knew trees, a whisper from a world still learning to be alive. Glaciers move like slow rivers of solid ice. They appear frozen in place, yet their ice is always shifting, flowing outward under its own tremendous weight. Down at the crystal level, individual ice grains creep past one another, bending and deforming, so that the whole body of ice inches forward, day after day. Sometimes the surface carries long, dark stripes of rock and dust, like currents traced across a frozen stream, revealing the paths that the ice has followed for years. Stakes placed on a glacier do not stay put. They drift down slope, quietly marking the passage of time in the landscape. Where the ice is thickest, or where meltwater lubricates the bed beneath, the motion can become surprisingly quick, enough to reshape valleys and push rocky debris far from its source. This movement is relentless. Even in the coldest darkness of winter nights, the ice keeps on going, carrying the memory of snowfalls that fell long before anyone was watching. The Himalayas are still growing taller every year. When the Indian plate slammed into Asia around 50 million years ago, it did not stop. Even today, it continues to press northward, pushing the Tibetan plateau higher and folding the crust into soaring ridges. The Himalayas rise a little more each year, roughly the width of a fingernail. Earthquakes ripple through the region as the strain builds, a constant reminder that the collision is not yet over. As the land climbs, glaciers scrape new paths across the summits, feeding rivers that sustain billions of lives below. The tallest peaks, like Mount Everest and K2, are not ancient relics, but living formations, growing and shifting even as they shed stone and snow. Each centimeter gained is a breath of the planet's inner strength, a silent expression of motion that has never truly ceased. The mountains of today are still being born. The Andes were once a seabed before being lifted skyward. Long before the Andes towered above South America, their rocks rested at the bottom of an ancient ocean. Layers of sand, coral, and shell slowly turned to limestone, shale, and sandstone. When the Nazca Plate slid beneath the continent, those sediments were crushed, folded, and pushed upward into jagged ridges. Fossil shells can still be found high among the peaks, reminders that these heights were once underwater. Volcanoes erupted along the new mountain chain, adding fresh layers of lava to the rising stone. Over millions of years, the seabed became the backbone of a continent. Even now, deep earthquakes and smoking peaks mark the boundary where the old ocean floor continues to descend beneath the land. To stand on an Andean summit is to stand upon what was once the floor of a vanished sea. Glaciers can flow uphill under the right conditions. At first, that sounds impossible, since gravity pulls everything down slope. The key is that ice behaves not only as a solid, but also as a material that responds to pressure differences in surprising ways. When a glacier is thick and heavy, the pressure at depth can drive ice from regions of high pressure to regions of lower pressure, even if that path leads slightly upward over a buried bump in the bedrock. From above, the surface might still appear to descend overall, yet along the base, ice can be forced up and over ridges before continuing its journey downhill. This process is guided by the total energy of the system, not just the steepness of the surface. Meltwater beneath the glacier can add to this effect by easing the ice over obstacles. In this way, these slow rivers of frozen water can quietly climb over buried hills as they continue their long migration. Clouds often form and dissolve along a mountain's edge. If you watch a mountain closely on a breezy day, you may see clouds appear and vanish with surprising speed. As air flows up the slope, it cools just enough for moisture to condense, creating thin veils of mist that hug the rocks. A few hundred feet higher, the air may dry and the cloud will fade, only to form again moments later. These shifting layers are known as orographic clouds, born directly from the mountain's influence on the air. In some places they linger in bands, drifting like scarves around the summit. To hikers, they bring sudden fog and bursts of rain. To distant observers, they make the mountains seem alive, breathing mist in and out. Each wisp of cloud is a temporary creation, a delicate interplay of wind, temperature, and shape that makes the sky dance upon the stone. The Appalachian Mountains were once as tall as the Himalayas. Today, the Appalachians are gentle, forested hills that roll across the eastern United States. But long ago, they rivaled the greatest mountains on Earth. When ancient continents collided over 400 million years ago, they crumpled the crust into massive peaks as high as the modern Himalayas. Over the ages, wind, rain, and ice slowly wore them down. What remains today are the roots of that once mighty range, their deep foundations exposed and softened by time. Beneath the trees lie rocks that have been bent, baked, and twisted by unimaginable pressures. The rounded summits we see now are like old bones of a long-vanished giant. Though they seem quiet, they still tell the story of Earth's restlessness, of the endless cycle of rising and eroding that shapes every landscape. The Appalachians are a memory of mountain grandeur, weathered but enduring. Some glaciers make deep, thunderous sounds when they shift. In cold, quiet valleys, the apparent stillness of the ice can suddenly be broken by booming echoes that roll across the landscape. These sounds often come from crevasses ripping open, or from blocks of ice grinding and slipping past each other under stress. The glacier is constantly adjusting to its own weight, temperature changes, and variations in how firmly it grips the rock beneath. When the stress builds beyond what the brittle upper ice can bear, it fractures, releasing energy as sound and vibration. Listeners might hear a cracking noise that grows into a rumble, then fades back into silence. Instruments placed on and inside the ice can detect many more of these events than human ears could catch, revealing a whole hidden symphony of snaps and groans. Each sound marks a moment when the glacier has rearranged itself, just a little, in response to the forces that drive it forward. Mountain peaks can create their own weather systems. When moist air rises along the slopes of a mountain, it cools and condenses, forming clouds that often cling to the summit. As the air moves over the ridge and descends on the other side, it warms again, creating a rain shadow where deserts can form. This process shapes entire climates. The Andes, for instance, help create the arid Atacama Desert to their west, while the Himalayas block cold winds from Siberia, warming the plains below. On smaller scales, individual peaks can summon storms of their own. Local updrafts create thunderheads that gather around the summit like a crown of weather. Even a single mountain can influence where rain falls, how winds move, and when fog forms. In this way, mountains are not only shaped by the atmosphere, they are sculptors of it, breathing life into the skies that surround them. The Alps are young compared to many other mountain ranges. Though the Alps feel timeless, they are geological adolescents. Formed only about 40 million years ago when Africa pressed into Europe, they are young compared to the worn-down Appalachians or the crumbling mountains. Greenland, their sharp ridges, steep cliffs, and snow-bright peaks owe their beauty to this youth. Glaciers still carve through them, sculpting valleys and summits into shapes of dramatic grace. Because the rocks are fresh and the uplift continues, landslides and avalanches are common, signs of a range still finding balance. Within the layers of limestone and granite, fossils of ancient seashells whisper of the Tethys Ocean that once covered this region. The Alps are a living moment in Earth's long story, captured between birth and erosion, rising high enough to pierce the weather, yet still young enough to remember the sea. Blue ice forms when glaciers compress snow for centuries. Fresh snow is bright and reflective, with countless tiny surfaces that scatter light in all directions. As snow is buried and compacted, the grains weld together into a denser mass, and many of the minute air pockets are squeezed away. Thick, pure ice absorbs the red and yellow parts of sunlight more strongly than the blue. The more distance light travels through this dense material, the more those warmer colors are stripped out, leaving a rich blue glow. In deep crevasses, along fractured cliffs of ice, or within compressed ice fields, this color can be striking, ranging from a soft turquoise to an intense sapphire. The shade tells a story about the purity, thickness, and internal structure of the ice. Where the blue appears most vivid, it can indicate long periods of quiet accumulation and compression, when snow quietly fell, settled, and slowly transformed into solid ice without frequent disturbance or melting. The Rocky Mountains formed in a surprisingly distant location. The Rocky Mountains did not rise where one might expect. Unlike most ranges that form along plate boundaries, the Rockies erupted far inland, nearly 1,000 miles from the edge of the Pacific Plate. Around 70 million years ago, a unique collision occurred. An oceanic plate slid shallowly beneath North America, instead of diving deep. This strange angle transmitted force far across the continent, buckling the crust in its middle and raising peaks where there had once been plains. Later, rivers cut deep valleys through the uplifted rock, revealing layers of ancient seabed and volcanic ash. Even now, geologists study the Rockies to understand how such distant forces created so vast a chain. They are a reminder that the planet's motions can reach far beyond the edges we see, reshaping landscapes in quiet, unexpected ways that only deep time can show. Reveal. The mountains of Antarctica hide peaks taller than the Alps. Beneath Antarctica's miles-thick ice sheet lies a hidden world of mountains. Using radar and gravity mapping, scientists have discovered the Gambortsev Range, a vast chain buried under the frozen surface. These secret peaks are as tall as the European Alps and stretch for more than 700 miles across the continent's interior. No human eye has ever seen them directly. The rocks remain locked beneath ice that has persisted for over 30 million years. Their origin is still a mystery, though some clues suggest they may have formed from the collision of ancient continents long before Antarctica froze. The mountains guide the flow of ice above them, shaping hidden valleys and subglacial lakes. They are a reminder that even on the coldest continent, unseen landscapes sleep in silence, mountains that have not felt the sky in tens of millions of years. Glaciers hold most of Earth's fresh water. Although they may seem remote, these frozen bodies contain an immense share of the planet's accessible fresh water. The ice stores snowfalls that accumulated through countless winters, preserving them in layers that stretch deep below the surface. If all that stored water were released at once, it would raise global sea levels dramatically. This reserve is so large that even small changes in glacier mass can influence entire ocean basins and coastal regions. The water stored in ice eventually returns to the environment through melting, feeding rivers and lakes that support communities, ecosystems, and far-reaching watersheds. This slow release helps moderate seasonal flows in many regions. Glaciers serve as guardians of planetary moisture, keeping vast quantities of water locked away and stable through long periods of time. When they change, the balance of water across Earth changes with them, linking frozen heights to distant shores in ways both subtle and profound. There are underwater mountains taller than Everest. Far below the surface of the ocean, where sunlight never reaches, lies a mountain range mightier than any on land. Along the mid-ocean ridge, molten rock wells up from the mantle, forming peaks that rise taller than Mount Everest when measured from base to summit. These submarine mountains stretch across the planet like a continuous scar, wrapping around Earth for more than 40,000 miles. Volcanic vents dot their slopes, releasing heat and minerals that nourish strange ecosystems in the darkness. Towering cliffs, steep ridges, and valleys form a landscape few have ever seen, yet it covers more than half the planet's surface. When explorers mapped it using sonar, they realized that the greatest mountain range on Earth was hidden beneath the waves all along. It is a world of fire and water, unseen but endlessly alive beneath the sea. Some glaciers create their own winds. Air that rests over high, cold ice fields can become extremely dense and chilled. As night falls or clear skies allow heat to radiate away, that heavy air begins to slide downslope along the surface of the glacier. The flow gathers strength as it descends, forming a steady, often very cold wind, known to locals in many glaciated regions. These winds can sweep through valleys, carrying fine snow and ice crystals, and creating distinct bands of colder air that influence local weather. They can clear clouds from certain slopes while piling them against others, shape snowdrifts, and affect how plants and animals cope with the harsh environment at the glacier margins. Instruments show that these air currents are guided not just by gravity, but by the contours of the ice, the surrounding topography, and the contrast between cold glacier surfaces and warmer ground below, a subtle climate engineered by frozen water. The largest mountain range on Earth is beneath the ocean. Stretching for more than 40,000 miles across the planet, the mid-ocean ridge forms a continuous chain of volcanic mountains, but encircles the globe. Like a seam, hidden beneath miles of water, it marks the place where Earth's crust is pulling apart, allowing molten rock to rise and cool into new seafloor. The ridge snakes through every ocean, crossing the Atlantic, winding into the Indian and Pacific, even threading beneath the polar ice. Though completely submerged, it covers nearly a quarter of the planet's surface. Along its crest, black smokers gush superheated water rich with minerals, creating oases of strange life in the darkness. Creatures that have never seen sunlight thrive among its vents, living on chemistry instead of photosynthesis. The mid-ocean ridge is not a single mountain, but an entire system, the beating tectonic heart of Earth's restless surface, always forming, always renewing. Some mountains lie buried beneath ice sheets miles thick. Antarctica and Greenland conceal ancient landscapes, frozen in silence. Beneath their vast ice sheets, radar surveys have revealed rugged mountain ranges, valleys, and plateaus that have not felt open air in millions of years. These hidden worlds were shaped long before the ice began to grow, sculpted by rivers and glaciers that vanished long ago. The weight of the ice above them presses the land down, bending the crust into deep basins where subglacial lakes still shimmer in total darkness. Scientists have detected entire watersheds beneath the Antarctic interior, flowing around unseen peaks and ridges. The ice preserves them like a time capsule, a frozen map of the world as it once was. If the ice were to melt, continents would be transformed, revealing mountains older than human memory, preserved under a white tomb of unimaginable weight and time. Volcanoes can grow into mountains in a single lifetime. While most mountains rise over millions of years, volcanoes can build themselves astonishingly fast. When magma finds a path to the surface, it begins to pile layer upon layer of ash and lava, solidifying into a peak that grows taller with every eruption. Paricutin, a volcano in Mexico, appeared suddenly in a farmer's cornfield in the year 1943. Within days, smoke and cinders filled the air, and within a single year the volcano had risen more than 1,000 feet high. By the time it went dormant 9 years later, it stood taller than the Empire State Building. Entire villages were buried in ash, Yet the landscape around it became a living record of creation itself. To watch a volcano form is to witness mountain building in real time, a reminder that the forces that shape Earth are not always slow or silent. Some glaciers glow with soft light from within. Under certain conditions, the interior of a glacier can appear to emit a gentle light. This glow is not produced by warmth or any biological process. Instead, it arises from the way dense, pure ice scatters and diffuses sunlight that enters through cracks, crevasses, or thin areas near the surface. Once inside, the light can travel surprising distances, bouncing between crystals and filtering into deeper layers. As it moves, the brighter wavelengths are gradually absorbed, leaving behind a cool blue radiance that seems to come from the ice itself. In overcast weather, the effect can be even stronger, since soft diffuse light spreads more evenly through the surface layers. The glow can reveal hidden textures and flowing bands of compressed snow laid down across ages. Observers who venture into safe ice caves sometimes describe the effect as standing within a lantern of frozen light, a still and silent world shaped entirely by tear, ice. Shield volcanoes can spread wider than entire countries. Not all volcanoes reach for the sky. Some, like those in Hawaii and Iceland, grow outward instead, spreading immense sheets of lava across hundreds of miles. These are shield volcanoes, named for their broad, gentle slopes that resemble a warrior's shield resting on the ground. Mauna Loa in Hawaii is one of the largest single structures on Earth, stretching nearly 75 miles from end to end. From its base on the ocean floor to its summit above the waves, it is taller than Mount Everest. The lava that builds such giants flows easily, spreading far before cooling, creating smooth plains of black rock that harden into new land. Over time, these overlapping flows form entire islands. Shield volcanoes remind us that not all mountains are born of violence. Some rise slowly, breath by breath, as rivers of fire become solid ground beneath a quiet sky. The tallest volcano in the solar system dwarfs every mountain on Earth. On the red planet Mars stands Olympus Mons, a volcano so vast that it could swallow the entire state of Arizona. Its slopes stretch for hundreds of miles, and its summit towers more than twice as high as Mount Everest. The mountain is so large that its curvature follows the shape of the planet itself. Scientists believe it grew to such immense size because Mars lacks tectonic plate movement. The crust never shifted beneath it, so eruptions built upon the same spot again and again, piling lava higher over millions of years. The result is a gentle, sprawling giant with cliffs taller than any on Earth. From orbit, it dominates the Martian landscape, a frozen monument to the planet's fiery past. Olympus Mons is a reminder that mountains are not bound by our world alone, but by the same cosmic forces that shape them everywhere. Some glaciers move faster than you might expect. The common image of a glacier is that of a motionless block of ice. Yet some move at speeds that can be surprisingly quick for such massive bodies. Their surfaces may advance several feet in a single day, driven by internal deformation, basal sliding, and the steady addition of new snow at high elevations. When meltwater trickles downward and accumulates along the bed of the glacier, it can act as a lubricant that reduces friction, allowing the ice to glide more easily over the rock below. Warm summers, heavy snowfall, and internal structural changes can all increase motion. Crevasses widen faster, surface features migrate downslope, and chunks of ice break away from the front more frequently. Even though the speed is slow compared with flowing rivers, the movement is powerful enough to shift boulders, alter landscapes, and reshape entire valleys. These faster-moving glaciers demonstrate how dynamic ice can be when conditions align. Some mountains are made almost entirely of coral, In certain tropical regions, what we call mountains were once living reefs beneath warm, shallow seas. Over millions of years, layers of coral and shells built massive structures of limestone that were later uplifted by tectonic forces. The island of New Guinea, for instance, contains entire ranges composed of ancient coral. Fossilized marine life lies embedded in cliffs thousands of feet above the modern ocean. These mountains tell the story of seas that vanished long ago, leaving behind stone skeletons of once living worlds. Rain and rivers carve the limestone into caverns, sinkholes, and spires, creating landscapes of surreal beauty known as karst terrain. In these places, mountains are not born from fire or collision, but from the quiet labor of countless small creatures. Each grain of stone was once part of something alive, building a world that now towers toward the sky. There are glaciers that carve icebergs taller than buildings. At the ocean front of certain glacial systems, enormous blocks of ice crack away from towering walls and fall into the sea. These events, known as calving, can produce icebergs that rise far above the waterline. The process begins with tension building deep within the glacier as it flows outward toward the coast. Waves, tides, and undercutting by warmer seawater can weaken the base, while the weight of overlying ice stresses the upper sections. When the fracture finally opens, an immense block separates and crashes into the ocean with tremendous force. The splash may send waves rolling across the fjord, and the newly formed iceberg drifts away like a drifting island of ancient ice. Some contain intricate bands of old snowfalls, compressed into patterns that reveal the history of the glacier. These enormous bergs are reminders of the sheer scale of frozen landscapes and the constant exchange between ice and sea. There are mountains made of frozen water on icy moons. Far from Earth, in the cold reaches of the outer solar system, mountains rise not from rock, but from ice as hard as granite. On Jupiter's moon, Europa, and Saturn's moon, Enceladus, the surface is frozen ocean, yet tectonic forces still twist and break it. Blocks of ice the size of cities collide and pile up, forming ridges and peaks thousands of feet tall. On Pluto, nitrogen and methane frost behave like rock, creating glaciers that flow slowly across the surface. These ice mountains gleam in the pale sunlight, their surfaces fractured and bluish, shining like glass. Some scientists believe liquid water may still flow beneath them, warmed by internal heat. If so, those hidden oceans could shelter life. These frozen peaks are reminders that even in the coldest corners of the solar system, the physics of mountains continues to sculpt worlds of wonder. Some mountains exist inside active lava fields. In the volcanic plains of Iceland and Hawaii, small peaks rise amid seas of cooling lava. These are cinder cones, born when molten rock erupts violently from a single vent, throwing glowing fragments into the air. The fragments cool as they fall, piling into steep, conical mounds. Some are only a few hundred feet tall, while others reach thousands, their sides coated with red and black ash. In places like Iceland's Holuhraun Field, new cones appear within years, glowing against the dark basalt that surrounds them. The air smells of sulfur and heat, and the ground trembles faintly beneath the surface. Though these mountains are small compared to great ranges, their youth makes them extraordinary. They stand as monuments to fire itself, fresh scars in the crust of a living planet, proof that Earth is still creating new summits beneath our gaze. You can sometimes see your own rainbow on the mountain mist. When the sun shines from behind you onto a bank of mist or cloud below, you may see a circular rainbow encircling your shadow. This is called a glory, a halo of color created by light scattering through tiny droplets. From an airplane, it can appear around the aircraft's shadow, but on a mountain, it feels deeply personal. The ring moves with you, fading and reappearing as the mist swirls. Climbers on high peaks often describe the sight with reverence, calling it the Brocken spectre. Sometimes the shadow appears enormous, magnified by perspective, as if the mountain itself were casting a luminous reflection of your presence. To witness a glory is to see sunlight turned to wonder, a brief moment when physics becomes art, and the boundary between self and landscape blurs into color. Light. Some glaciers form mysterious meltwater tunnels under ice. Deep beneath the surface, intricate channels can form where meltwater gathers and begins to flow. Pressure from the overlying ice forces the water to carve winding paths through the glacier's base and interior. These tunnels can stretch for miles, sometimes carrying water with astonishing speed. Their shape and size change constantly as melting expands them or flowing ice closes them again. During warm seasons, the tunnels may connect with surface streams that plunge into crevasses and disappear into the glacier's depths. When explorers map these passageways using instruments and careful remote sensing, they discover spiraling chambers, narrow corridors, and unexpected ambrées. Intersections that reveal the complex plumbing of the glacier. Each tunnel tells a story about temperature, pressure, and the flow of water within a world of ice, where darkness hides processes that continue around the clock. The air on mountains contains less oxygen, but more cosmic radiation. As altitude increases, the blanket of atmosphere around Earth thins. There are fewer oxygen molecules in each breath, and the body must work harder to draw in what it needs. At the same time, the thinner air provides less shielding from the constant rain of cosmic rays that drift in from space. At the summit of Everest, radiation exposure is roughly double that at sea level. Over time, this affects both humans and technology. Pilots and mountaineers often experience higher doses simply by spending time above the clouds. Yet in exchange for this harshness, the air offers unmatched clarity. Stars blaze brighter, and the sky deepens into a darker blue than most people ever see. Mountains bring us closer not only to the heavens we admire, but to the silent energy that fills the universe beyond them. Mountains can create wind patterns that circle the globe. When air encounters a mountain range, it is forced upward, cooling and releasing moisture. On the far side, it descends dry and warm, setting up pressure differences that ripple outward. These shifts in airflow can link together, influencing weather thousands of miles away. The Himalayas, for instance, play a crucial role in shaping the Asian monsoon, while the Andes steer the jet streams over South America. Even smaller ranges affect global circulation, guiding the paths of storms and trade winds. In the upper atmosphere, waves of air created by mountains can travel around the planet, their energy detectable from orbit. Each mountain acts like a musical note in Earth's symphony of wind, tuning the movement of air that governs climate. The peaks seem motionless, yet their presence helps conduct the rhythm of the sky itself. Glaciers leave behind giant, sculpted landscapes. As ice advances and retreats through valleys and across plains, it carves, grinds, and shapes the terrain in unforgettable ways. The immense weight of the ice presses stones into the ground, gouging grooves and polishing bedrock until it gleams. Steep cliffs form where the glacier has plucked away blocks of rock, and broad depressions develop where it has deepened old river channels. When the ice pulls back, it leaves behind ridges of moraine, long arcs of stones and soil carried from distant places. Lakes fill hollows dug by the ice, and rolling hills appear where the glacier deposited mixed sediments. Over time, plants and animals colonize these new landscapes, creating ecosystems on ground that was once hidden beneath frozen layers. The marks of glacial work can last for ages. Etched across continents, and visible long after the ice itself has vanished. Mountain air carries microscopic particles from distant deserts. Every gust of mountain wind is full of stories from faraway places. Tiny grains of dust lifted from the Sahara Desert can travel thousands of miles, crossing oceans and settling on the snowy slopes of the Alps or the Andes. These airborne travelers contain minerals, pollen, even traces of microbes. When they land on ice, they darken the surface slightly, speeding the melt beneath the sun. Volcanic ash, sea salt, and forest smoke join this global dance of particles, circulating endlessly through the sky. Scientists studying mountain snow can read these layers like the pages of a diary, revealing centuries of wind, drought, and storm. Even in the most remote summits, the air is never truly empty. It carries whispers of deserts, oceans, and fires from across the Earth, proof that every breath of wind is part of a single planetary story. Snowflakes form differently at high altitude. High in the cold, thin air of mountain skies, snowflakes grow into intricate crystalline shapes, unlike those formed closer to sea level. Temperature, humidity, and the speed of freezing all influence the geometry of each flake. At great heights, the air is often drier and colder, leading to needles, columns, and hollow prisms rather than broad, branching stars. Some flakes even form as perfectly hexagonal plates that sparkle like glass in sunlight. As they fall through varying layers of air, their shapes change, adding ridges and facets until they settle upon the snowfields below. No two flakes follow exactly the same path, making everyone a unique sculpture of the atmosphere. The snow that blankets mountains is a tapestry of countless small miracles, each crystal a frozen story of the sky's invisible breath, drifting gently toward the pre-Earth. Glaciers carve valleys with incredible strength. As they move, they do not simply ride over the landscape. They grind into it. Rocks frozen into the base of the ice act like cutting tools, scraping and polishing the bedrock beneath. This abrasive action can deepen and widen existing river valleys, reshaping them into broad troughs with steep sides and relatively flat floors. In places where the glacier plucks large blocks from fractured cliffs, the valley walls can become jagged and dramatic. Over repeated cycles of advance and retreat, the combined effect of this erosion can be enormous. Entire valley systems can be transformed from narrow, winding channels into sweeping corridors framed by towering slopes. Lakes may form where the glacier has over-deepened parts of the valley floor, ready to fill with meltwater once the ice pulls back. Each curve of the landscape bears the imprint of this hidden sculpting, worn into stone by the steady work of moving ice. Some mountain glaciers move faster than a person can walk. Glaciers seem timeless, but many are alive with motion. Deep within their mass, immense pressure causes ice to flow like thick syrup. Some glaciers, such as those in Greenland and Alaska, can surge forward several feet each day. A few have been known to move miles in a single year, faster than a person strolling across a valley below. The secret lies in meltwater beneath the ice, which acts like a lubricant, allowing the glacier to slide over the bedrock. As it moves, it grinds stone into fine powder and sculpts deep valleys. You can hear the glacier creak and groan as fractures open and close, as if it were breathing. Though it seems cold and still, a glacier is a river frozen in time, always flowing, always reshaping the mountains it embraces, carrying their stories slowly toward the sea. Others are frozen so solid they have not moved in thousands of years. In the coldest corners of the Earth, some glaciers are locked in place, their ice so brittle and frozen that it behaves like stone. These stagnant glaciers sit in Antarctica and high in the Himalayas, unmoving for centuries. Layers of snow have compacted into dense ice, trapping ancient air within tiny bubbles. Scientists drill deep cores into them to study the atmosphere of ages past, reading their compressed layers like pages of a frozen diary. These glaciers preserve a record of volcanic eruptions, shifting climates, and even the rise and fall of civilizations that depended on distant weather. Though they appear lifeless, they hold within them the breath of the ancient Earth, sealed beneath the surface. Each bubble of trapped air whispers from a world long gone, frozen in perfect silence, waiting patiently for the warmth of human curiosity to uncover its story. Glaciers carve valleys that outlast entire civilizations. As glaciers advance and retreat, they sculpt the land into vast U-shaped valleys, smoothing and deepening everything in their path. The slow grinding of ice against rock reshapes mountains over millennia, leaving behind polished cliffs and deep basins that later fill with rivers and lakes. When the glaciers melt, the marks of their passage remain for tens of thousands of years, long after human cities rise and crumble. Many of the world's great valleys, such as those in Norway and New Zealand, were carved this way, their grandeur shaped by the patience of ice. Even now, in places where glaciers have long vanished, their fingerprints linger in every curve of the landscape. They are the architects of deep time, working not in centuries, but in ages, their artistry measured in the soft perfection of a single valley floor. Some mountains act as time machines, revealing climates of the ancient Earth. Layers of rock within a mountain are more than just stone, they are pages from Earth's history. Each stratum preserves a chapter of ancient weather, captured in minerals, fossils, and chemical traces. By studying oxygen isotopes in limestone or the texture of old volcanic ash, scientists can reconstruct what the air and oceans were like millions of years ago. Some peaks in the Himalayas contain marine fossils from a time when the region was an ocean floor. Others hold layers of desert sandstone now sitting miles above sea level. To climb a mountain is to walk upward through time, from the present into the distant past. Every ridge, every outcrop is a frozen memory of a world that once was, a record of rain, heat, and life. Mountains do not merely touch the sky, they touch the ages before it. Mountains store most of the world's fresh water as ice and snow. High in the cold air, snow gathers year after year, compressing into glaciers that hold nearly 3/4 of the planet's freshwater. These frozen reservoirs feed rivers that sustain billions of people across Asia, Europe, and the Americas. In spring and summer, melting snow trickles down into valleys, filling streams, lakes, and reservoirs. When the snow arrives late or melts too soon, drought follows. The Himalayas, Andes, and Rockies are sometimes called the water towers of the world because of how many lives depend on their steady rhythm of freezing and thawing. Each winter, they lock away water in crystalline form, and each summer they release it again, a pulse that keeps entire ecosystems alive. To watch snow falling on a high peak is to see the planet quietly storing life, molecule by molecule, waiting for the warmth that will send it flowing home. The melting of mountain glaciers can shift the weight of continents. Glaciers are heavy, unimaginably so. A single cubic yard of ice weighs nearly a ton, and entire mountain ranges can be draped in ice sheets miles thick. When these glaciers melt, the weight on the crust below them lessens, allowing the land to slowly rebound upward in a process called isostatic adjustment. Northern Europe and Canada are still rising today from the loss of ancient ice that melted thousands of years ago. As the weight redistributes, it can trigger earthquakes and subtly alter sea levels across the globe. Even gravity changes slightly as the planet adjusts. This means that as the modern world warms and glaciers retreat, Continents are literally lifting their shoulders, shifting ever so slightly toward the sky. Mountains, rivers, and coastlines move in response, showing that even in thawing, the power of ice still shapes the Earth. Mountains can influence the tilt of the Earth's axis over long timescales. The rise of great mountain ranges does more than alter weather and rivers. It can subtly affect the balance of the entire planet. As massive slabs of rock are lifted high, their added weight and redistribution of mass can shift how Earth spins. Over millions of years, the formation of ranges like the Himalayas or Andes can change the wobble of the planet's axis, which in turn influences long-term back. Climate patterns. This feedback connects the movement of stone to the rhythm of the seasons. The mountains sculpted by plate collisions may help determine ice ages and warm periods far into the future. In this sense, the slow breathing of the planet's crust shapes not only the landscape, but the balance of sunlight that reaches every hemisphere. Mountains do not just rise from Earth's turning, they help guide its cosmic dance. Entire ecosystems exist only on mountain slopes. Each band of altitude on a mountain creates a different world, with its own climate, soil, and life forms. At the base, forests thrive in warmth and humidity. Higher up, evergreens give way to meadows and shrubs adapted to thin air and cold nights. Beyond the tree line, hardy mosses and lichens cling to bare rock, where few other organisms survive. Some mountain ranges host unique ecosystems that exist nowhere else on Earth, isolated by elevation and temperature. On the slopes of Mount Kilimanjaro, strange giant groundsels rise like prehistoric trees, while in the Andes, cushion plants form dense mats that trap warmth against the freezing wind. Each altitude is a different planet stacked atop the last, a vertical journey through evolution. Mountains are not just stone, they are entire worlds layered in height, each one a separate story of survival. There are glaciers that float on the ocean, where thick bodies of ice extend from land out over the sea. The front portions can become buoyant, forming ice shelves or floating tongues. The part still grounded on rock holds the upstream ice in place, while the floating section interacts directly with the ocean below. Seawater can flow into cavities under the shelf, melting it from beneath in patterns shaped by currents and water temperature. Above, large rifts can open in the floating ice, eventually leading to the release of huge tabular icebergs that drift away into open water. This floating extension affects how the glacier behind it flows, since the shelf acts somewhat like a brace that resists the pull of gravity on the inland ice. Changes in the thickness or extent of the floating portion can alter the speed at which ice from the interior reaches the sea, linking far inland snowfall to distant GWAF. Ocean environments. Some plants live nowhere else on Earth but a single peak. Isolation breeds uniqueness, and mountains are nature's laboratories of evolution. In the high Andes, a plant called the Puya Raymondi grows only on certain slopes between 10 and 15,000 feet. It can live for a century before sending up a flowering stalk 30 feet tall, blooming once before it dies. On Mount Kinabalu in Borneo, hundreds of plant species exist that are found nowhere else in the world. These isolated ecosystems evolve in secrecy, shaped by the thin air, the shifting mists, and the rhythm of temperature across the day. When climates change, these species have nowhere higher to climb. Many are already disappearing, leaving behind only the memory of their fragile kingdoms in the sky. Each rare bloom and twisted shrub is a reminder that life's creativity thrives in solitude, and that every mountain peak shelters a miracle all its own. Animals evolve smaller or larger on mountains depending on altitude. High altitudes shape life in surprising ways. In cold, oxygen-poor air, animals must adapt their size and physiology to survive. Some species become smaller to conserve energy, while others grow larger to retain heat. The snow leopard, for instance, has powerful lungs and a thick coat that allows it to roam effortlessly across the thin Himalayan air. Mountain rodents such as pikers remain tiny, darting among rocks to avoid the biting cold, while yaks develop massive chests and hearts to pull oxygen from the wind. Birds that live in high places often have more efficient blood chemistry, allowing them to fly where others would faint. Over generations, the altitude molds each creature like a sculptor shaping clay. The result is a tapestry of life uniquely fitted to its elevation, a living demonstration of evolution's quiet precision in the loftiest places on Earth. Glaciers can hide volcanic heat below their surfaces. Beneath certain ice-covered regions, volcanic systems continue to pulse with energy, even when the surface above appears silent and unmoving. The thick ice acts like a heavy blanket, trapping geothermal warmth below. That heat can melt the underside of the glacier, creating pockets of water that pool and flow in darkness. In some regions, entire networks of subglacial lakes form where volcanic warmth keeps the water liquid year-round. This hidden heat can alter the flow of the glacier by reducing friction along the bed, allowing the ice to slide more easily over bedrock. Steam and gases may rise through cracks in the ice, and in rare cases the pressure can trigger explosive interactions between molten rock and meltwater. What appears as a calm, frozen plateau may be quietly shaped by geological forces working far beneath the surface, where fire persists under a world of ice. Some frogs live in clouds that never reach the ground. In the misty forests of Central and South America, there are frogs that spend their entire lives within clouds. These cloud forests cling to mountain slopes where moist air condenses into constant fog. Here, tree frogs and glass frogs lay their eggs on leaves glistening with dew, and their skin absorbs the moisture of the air itself. They rarely, if ever, descend to the forest floor. The clouds provide both water and shelter, a floating world where raindrops form before they fall. The delicate balance of temperature and humidity allows these creatures to thrive in places that seem half sky, half earth. To live among clouds is to exist between worlds, and these frogs have made it home. Their gentle calls echo through mist-shrouded canopies, a chorus rising and fading like the vapor that sustains them. Birds can fly higher than any human has ever climbed unaided. While humans struggle for breath above 26,000 feet, some birds soar effortlessly far beyond. The bar-headed goose is known to migrate over the Himalayas, reaching altitudes of more than 29,000 feet, higher than the summit of Everest. It accomplishes this by taking advantage of cold, dense air currents at dawn, and by having blood that binds oxygen more efficiently than most species. Other birds, such as the Ruppell's vulture, have been recorded flying even higher, gliding above 37,000 feet where temperatures drop below freezing and Beatty. The air holds only a third of the oxygen found at sea level. At those heights, wings beat through a world few creatures will ever touch. These birds trace invisible highways through the sky, living proof of nature's astonishing adaptability, masters of the thin, shimmering edge between Earth and the air. Stratosphere. Mountain goats have specialized hooves that can grip near vertical cliffs. The mountain goat, one of nature's most extraordinary climbers, can ascend cliffs that seem impossible to scale. Its split hooves spread wide to balance weight, while the outer edge is hard and sharp for traction. Beneath lies a soft, rubbery pad that molds to the surface of the rock, gripping tiny cracks and ledges. Even newborn kids learn to climb within hours of birth, following their mothers up sheer slopes where predators cannot reach. Watching them leap from ledge to ledge It seems as though gravity has forgotten them. Their balance is so precise that a misstep is almost unheard of. The high cliffs they inhabit offer both protection and perspective, a place where the wind sings constantly and the view stretches into eternity. The mountain goat's hooves are an evolutionary masterpiece, perfectly crafted for life at the edge of the sky. There are glaciers that surge forward suddenly. Most glaciers advance slowly, shifting their mass in a steady, controlled flow. Yet some undergo dramatic periods when their movement accelerates far beyond their usual pace. These surges can send the glacier racing forward many times faster than normal for months or years at a time. Deep within the ice, changes in pressure or the buildup of meltwater can alter the delicate balance that keeps the glacier moving at a predictable rate. Once that balance shifts, the ice begins to slide more freely over its bed. Crevasses open with startling speed, ice folds buckle and stretch, and entire sections of the glacier lurch ahead. When the surge ends, the glacier settles back into a slower rhythm, often leaving behind jumbled ridges of debris and newly carved channels. These sudden accelerations remain one of the most intriguing mysteries in glacial science, showing how rapidly ice can respond to changes within its hidden interior. Some insects spend their entire lives above the tree line. Above the forests and meadows where cold winds strip away most vegetation, a few hardy insects endure. Stoneflies, snow fleas, and ice midges live among the rocks and snowfields, feeding on microscopic algae or the remains of wind-blown plants. Their dark bodies absorb what little heat the sun provides, and some produce natural antifreeze in their blood to survive the chill. They crawl across glaciers, appearing lifeless, until a patch of sunlight wakes them into motion. Because these environments change so slowly, the insects have remained almost unchanged for millennia. They are tiny survivors in a world too harsh for most forms of life, proof that even the bleakest landscapes can sustain delicate ecosystems. When you look at a snow-covered summit and imagine it barren, remember that beneath the frost, an unseen world of fragile endurance quietly persists. Certain mountain butterflies migrate across multiple altitudes each season. Some species of butterfly follow an invisible ladder through the mountains, moving up and down the slopes as the seasons shift. In the Himalayas and Andes, butterflies such as the Apollo and the Painted Lady rise to high meadows in summer, where alpine flowers bloom. As winter approaches, they descend to warmer valleys, tracing routes that span thousands of feet in elevation. Each altitude offers a different stage of life. Eggs and caterpillars in the lower forests, pupae in cool mid-level air, adults in the upper meadows. The journey is as precise as that of any migratory bird, guided by sunlight, temperature, and the scent of distant flowers. These fragile travelers connect ecosystems from base to summit, carrying pollen between worlds. Their wings shimmer across altitudes like moving petals, reminders that even the smallest life forms navigate the grand architecture of the Earth. Trees at high altitude grow in twisted shapes because of constant wind. Where the forest meets the mountain's open slopes, trees begin to warp and bend under the unending pressure of wind and cold. Their branches grow low and thick, their trunks leaning away from the direction of prevailing gusts. This phenomenon, called krumholtz, creates strange sculpted shapes that look like living art carved by the weather itself. Each twisted pine or spruce records years of struggle, each ring inside its trunk marking another season of endurance. The trees that survive here are smaller but tougher than their valley cousins, their bark thick and roots deep. Together they form tangled, beautiful borders between life and barrenness. Standing among them, you can hear the constant whisper of air that shaped them, a reminder that mountains are not just built by stone, but also by wind that never rests. The upper forest line changes with latitude and climate. There is a point on every mountain where trees can grow no higher. This boundary, known as the timberline, varies with temperature, rainfall, and distance from the equator. Near the tropics, trees may thrive up to 12,000 feet, while near the poles, they vanish only a few hundred feet above sea level. The position of the forest line reveals much about local climate. It shifts upward in warm centuries and descends in colder ones, marking the pulse of the planet's weather through time. Above this limit, cold and wind prevent seeds from taking root. Yet even there, low shrubs and grasses sometimes find a foothold. The timberline is not a hard edge, but a fading breath, where forest becomes sky. It is one of the mountain's most delicate boundaries, balancing life against the thin air of the high world. Some mountaintops are so high they resemble the surface of Mars. Above 20,000 feet, the air is thin, the sunlight fierce, and the soil barren. Only a few microbes and lichens survive in this near-sterile world. The temperature swings wildly between scorching days and freezing nights, and ultraviolet radiation beats down with unfiltered intensity. Scientists studying these environments often compare them to Martian landscapes, using high peaks like the Andes Atacama Plateau or the Himalayas as testing grounds for space missions. Instruments designed for Mars rovers are first tried here, where red dust and rock mimic alien terrain. Even the colors, oxidized by dry air and sunlight, glow in rusty hues. To stand on such a summit is to glimpse another planet without leaving Earth. These extreme peaks remind us that the line between our world and others is thin, drawn only by the warmth of the atmosphere we breathe. The human body begins to change within hours of reaching high altitude. At elevation, every breath carries less oxygen, and the body must quickly adapt. The heart beats faster, and breathing deepens even at rest. Within a day, the kidneys begin producing hormones that stimulate the creation of new red blood cells. Over time, muscles grow more efficient at using oxygen, and the blood thickens slightly to carry it. Yet these adaptations come with a cost: fatigue, insomnia, and the dull ache of altitude sickness for those who ascend too quickly. High-altitude people, such as the Sherpa of Nepal and the Andean Quechua, have inherited generations of physiological adjustments that allow them to thrive where others struggle. Their bodies produce nitric oxide that widens blood vessels and improves circulation. The transformation is a quiet miracle of biology, proof that life, even human life, can adjust to almost any height the mountains demand. At extreme heights, water boils at surprisingly low temperatures. Boiling water on a mountain can be a strange experience. Because air pressure decreases with altitude, water requires less heat to turn into vapor. At the summit of Everest, it boils at only about 160 degrees Fahrenheit instead of 212. This means food cooks more slowly, tea never becomes truly hot, and climbers often find themselves drinking lukewarm water that still steams in the cold air. The same principle affects weather too, as moisture evaporates and condenses differently in the thin atmosphere. For mountaineers, understanding this change can be vital for survival. It is a small but vivid reminder that the rules of everyday life bend as we climb higher. Even the simplest act of boiling water becomes an experiment in physics, proof that altitude alters not just the body, but the very nature of heat and air. People can develop new red blood cells within days of climbing high. When a person ascends to altitude, the body immediately senses the reduced oxygen. Within hours, it releases a hormone called erythropoietin from the kidneys, signaling the bone marrow to produce more red blood cells. These cells act as tiny fairies, carrying oxygen through the bloodstream to every organ. Over days and weeks, their numbers multiply, thickening the blood and improving its ability to capture each breath of thin air. This adaptation helps climbers and high-altitude dwellers survive where oxygen levels are nearly half those at sea level. Athletes sometimes train at elevation for this reason, returning stronger once their bodies adjust. The process is an elegant dance of biology and physics, proof that life is capable of remarkable flexibility. Every heartbeat at altitude is an experiment in endurance, the body quietly rewriting its chemistry to match the mountain's quiet challenge. The highest permanent settlement on Earth sits higher than some clouds. In the Peruvian Andes lies La Rinconada, a mining town perched over 16,000 feet above sea level. It is so high that clouds often drift below its streets, and visitors struggle to breathe after only a few minutes. Yet more than 30,000 people live and work there, mining gold in thin air where water boils at lukewarm temperatures. The town has no running water or sanitation, and every step requires effort. Still, its people endure, their bodies adapted to oxygen levels that would leave most faint. Above them stretch snowfields and glaciers below. The world feels impossibly distant. Nights are cold, days intense with sunlight that burns the skin. In this fragile place, life persists on the edge of human possibility. It is a reminder that home can exist even where air itself seems too light to sustain it. Indigenous cultures have lived in mountain valleys for millennia. Long before mountaineering or exploration, people made their homes among the high valleys and passes of the world. In the Andes, Quechua and Aymara communities cultivated potatoes and quinoa on terraced slopes, mastering agriculture at altitude. In the Himalayas, Sherpa villages thrived along ancient trade routes through the clouds. The Berbers of North Africa, the Gurung of Nepal, and the peoples of the Caucasus all shaped their lives around mountains, developing languages, music, architecture that reflected the landscape. Thin air, steep terrain, and isolation bred resilience and deep spiritual connection. For many, the mountains were not obstacles but living presences, protectors and teachers. Traditions tied to stars, glaciers, and wind still guide daily life in these regions. To walk among such communities is to see that humanity has always belonged to the mountains, not as conquerors, but as quiet companions in their shadow. Some ancient temples were built on peaks to be closer to the sky. Throughout history, civilizations have raised their most sacred monuments on high ground, believing altitude brought them nearer to the divine. In Greece, Mount Olympus was considered the home of the gods, and temples dotted its lower slopes. In the Andes, the Inca constructed shrines atop volcanic peaks more than 20,000 feet high, where priests offered golden figures to the heavens. In Japan, Mount Fuji became both a physical and spiritual ascent, its summit a gateway between worlds. Even small hilltop centers across Asia, Africa, and Europe followed the same instinct. The higher the place, the thinner the veil between heaven and earth. Building upon a mountain was both a feat of devotion and defiance, a human gesture toward the infinite. Each ancient stair and carved altar still whispers the same message, that the soul longs to rise as surely as stone. Pilgrims once crossed glaciers to reach sacred shrines. Long before the age of mountaineering, faith drove people into some of the harshest landscapes on Earth. In Tibet, devotees walked for months across frozen passes to reach monasteries hidden among snow peaks. In the Alps, pilgrims crossed glaciers to visit shrines such as the Great St. Bernard Hospice, a refuge standing above 9,000 feet where monks still welcome travelers today. These journeys were acts of endurance and reverence. Pilgrims carried little, relying on faith and one another to survive storms, avalanches, and thin air. The path itself was part of the prayer, each step an offering of effort to something greater. Even now, modern trekkers follow those ancient routes, echoing the rhythm of thousands before them. In the quiet of high places, among snow and stone, humanity's search for meaning has always found its way upward toward the light. Myths often describe mountains as homes of gods and spirits. In nearly every culture, mountains have been imagined as sacred dwellings of divine beings. The Greeks envisioned Zeus ruling from thunderous Mount Olympus, while in Hindu mythology, Mount Kailash is the axis of the universe, the seat of Lord Shiva. In Japan, the goddess Sengen resides atop Mount Fuji, and in Maori stories, New Zealand volcanoes are living ancestors who move and quarrel. Mountains touch the sky and vanish into clouds, a mystery that invites reverence. To ancient eyes, lightning on a summit was not weather, but conversation among gods. Even today, many peaks remain off-limits to climbers out of respect for spiritual traditions. Whether as holy mountains, protectors, or sleeping spirits, they remain bridges between the human and the divine, places where the earth reaches upward as if yearning for its own reflection in the heavens. Many ancient peoples believed mountains were the axis of the world. In mythology, the idea of a world mountain appears again and again. The Greeks called it Mount Olympus, the Hindus Mount Meru, and the Norse imagined Yggdrasil, a cosmic tree connecting heaven, earth, and the underworld. In Mesoamerica, pyramids mirrored sacred peaks, symbolizing the same connection between realms. The concept endures because mountains embody balance, stability, and the link between earthbound life and celestial order. To stand on a summit and look out in all directions feels like being at the center of creation, where the sky seems to pivot around the earth. These beliefs were not simple superstition, but intuitive expressions of cosmic understanding. Ancient peoples sensed that mountains represented the spine of the world, grounding it against chaos. Even now, we look to summits for perspective, feeling instinctively, but they are both anchor and axis of existence. Some mountains were said to touch the heavens themselves. Long before airplanes or satellites, humanity imagined peaks that reached into the very realm of the gods. In Mesopotamian myth, the mountain Meshu stood at the gate of the rising sun. In the Old Testament, Moses climbed Mount Sinai to receive the law, amid thunder and cloud. The Inca believed their highest summits were pathways to the afterlife. These stories gave mountains a spiritual geography, their height a metaphor for transcendence. To climb a mountain was not just to ascend, but to cross the boundary between mortal and divine. The thin air, the silence, and the nearness of the stars all reinforced the illusion that one stood at the threshold of heaven. Even today, standing on a high peak can feel like touching something infinite, the same ancient awe that turned geography into myth. Lightning strikes mountains more often than anywhere else on land. Mountains rise into the paths of storm clouds, their peaks acting like natural lightning rods. The electric charge of the atmosphere concentrates near summits, and when the balance becomes too great, lightning leaps from cloud to stone. On average, tall peaks are struck hundreds of times a year. Some, like Mount Rainier or the Matterhorn, glow with static energy before a storm, making climbers' hair stand on end. In that moment, the air hums with invisible tension. Trees splinter, rocks explode, and new paths of melted glass called fulgurites trace across the ground. Each strike is a reminder that even stone cannot resist the sky's fury. Yet from a distance, the sight is beautiful, a flash of energy linking earth and air. Lightning crowns the mountains like fleeting halos, nature's own illumination of the places closest to the clouds. Some peaks hum with natural electricity during storms. Before lightning strikes, the air around a summit can become charged with static electricity. Metal objects buzz, hair stands upright, and faint humming sounds ripple through the air. This phenomenon occurs when charged particles build up along the ridge, turning the entire mountain into a conductor. On the tallest peaks, climbers have reported hearing a soft, eerie song before the storm breaks, a chorus created by millions of ions dancing along the rock. In some cases, faint blue glows appear at the tips of metal tools or around outstretched hands, a manifestation known as St. Elmo's fire. It is both beautiful and dangerous, a prelude to a lightning strike that may follow moments later. In that instant, the mountain becomes alive with electricity, humming like a great instrument played by the sky itself. Minerals deep within mountains can generate magnetic fields. Within certain rocks lie minerals rich in iron and nickel that can align with Earth's magnetic field as they form. When heated and cooled deep underground, they capture a magnetic signature that endures for millions of years. Massive deposits of magnetite, hematite, and pyrrhotite within mountain roots can create faint local magnetic anomalies detectable by instruments. In some regions, compasses spin or drift near such deposits, misleading travelers. These magnetic records are vital to science, helping geologists trace how continents moved and where ancient poles once lay. Mountains thus act as magnetic archives, preserving the invisible whispers of Earth's shifting field. Each mineral grain becomes a compass frozen in time, pointing not north as it is now, but to where north once was. The stones remember the planet's ancient orientation long after the magnetic poles have wandered away. Certain rocks inside mountains record the movement of Earth's poles. As molten rock cools, magnetic minerals inside it align with the direction of Earth's magnetic field at that moment. When those rocks solidify within mountain layers, they lock that alignment permanently in place. By studying the orientation of these minerals in rocks of different ages, scientists can reconstruct how the magnetic poles have shifted through history. This science, known as paleomagnetism, reveals that continents have drifted thousands of miles and rotated in unexpected ways. Some ancient mountain ranges show that what is now north once pointed east or west. The very stones beneath our feet are silent maps of planetary motion. Mountains, by preserving these records, have become libraries of invisible directions. They store the memory of a world turning through deep time, where even the pull of a compass is only a momentary truth written upon a restless earth. Earthquakes can raise or destroy mountains in a matter of minutes. While most mountains rise slowly, a single earthquake can change them in the blink of an eye. When immense pressure builds along faults deep underground, it can suddenly release, thrusting rock upward or causing entire slopes to collapse. The 1960 earthquake in Chile lifted parts of the coast by more than 10 feet, creating new cliffs overnight. Conversely, landslides triggered by quakes can erase peaks that stood for thousands of years. In the Himalayas and Alaska, mountain faces have crumbled in seconds under the violent shaking. These events remind us that the same forces that create beauty also unleash destruction. The Earth's crust behaves like a living skin, cracking, healing, and reshaping itself in cycles of unimaginable energy. Mountains are born from chaos, and sometimes, with a single shudder, they return to it again. Some entire lakes have vanished because a mountain shifted. When the ground beneath a lake moves during an earthquake or landslide, water can drain away almost instantly. In China's Sichuan province, the Wenchuan earthquake of 2008 triggered landslides that both created and destroyed mountain lakes within hours. Some rivers were dammed by fallen rock, forming temporary reservoirs that later burst, while others vanished as fissures opened in the bedrock. In Iceland and Alaska, similar shifts have emptied glacial lakes in a single day, leaving behind cracked basins and stranded fish. The phenomenon is both awe-inspiring and unsettling, a reminder that mountains are not fixed but breathing structures, capable of transformation even within our lifetimes. What appears permanent can vanish overnight, reshaped by the hidden movement of the Earth's deep bones beneath the surface. Landslides can travel faster than a racing car down a mountain slope. When rock and soil give way on a steep slope, gravity takes over with terrifying speed. Some landslides accelerate to more than 100 miles per hour, tearing through forests and valleys in seconds. The largest in recorded history, in Alaska's Lituya Bay, sent a wave over 1,700 feet high crashing across the fjord. The power released by such an event equals that of a major explosion. Though they can be triggered by rain, melting snow, or earthquakes, the outcome is always sudden, leaving little warning. Scientists study these events to understand how friction and heat turn solid rock into flowing debris. In the aftermath, the landscape looks as if it has been rewritten. Valleys buried and rivers diverted. Landslides are the mountain's most dramatic exhale, a fleeting moment when the weight of ages comes rushing down at once. Avalanches can release more energy than an exploding bomb. When layers of snow build up on a steep slope, each layer carries its own tension. A single crack, a shout, or a change in temperature can cause them to collapse, sending thousands of tons of snow hurtling downhill. The speed can exceed 200 miles per hour, and the pressure generated at the base can snap trees and crush buildings. The energy released in a large avalanche rivals that of small explosives. Yet within their violence lies an eerie beauty, a white river cascading in silence until it hits the valley floor, where the air fills with glittering frost. Mountains store this potential energy all winter long, invisible until unleashed. To those who study them, avalanches are both catastrophe and choreography, nature's brief but powerful reminder that even snow can move with the strength of thunder. Some avalanches create temporary airwaves that can flatten forests. As a massive wall of snow races down a mountain, it pushes a wave of air ahead of it, moving faster than the snow itself. This air blast can reach hurricane strength, snapping trees, lifting roofs, and hurling debris hundreds of feet. In the Alps and the Rockies, rescue teams have found entire forests flattened by these invisible fronts, while the snow stopped short of the trees. The phenomenon explains why even sheltered valleys can suffer destruction when avalanches strike nearby. It is not just the snow that kills, but the breath of the avalanche itself, a moving shockwave of displaced atmosphere. Afterward, the silence is profound. The forest lies in tangled ruin, and the air feels unnaturally still. It is a strange echo of the power that moments earlier swept through, unseen yet unstoppable. The snow on mountains can sing as it shifts and compresses. On rare occasions, when conditions are just right, snowfields produce an eerie humming sound as layers move and settle. The vibration resonates through the frozen crystals, creating a low musical tone that can carry for miles. Known as singing snow, it has been heard in deserts, on glaciers, and across polar plateaus. The frequency depends on the density and moisture of the snow, turning wind-blown drifts into natural instruments. Ancient travelers spoke of these voices as spirits within the ice. Modern science explains them as friction between uniform grains sliding over one another, yet the experience feels no less magical. Standing on a slope and hearing the earth sing back is unforgettable. The sound drifts through the air like a whisper from another world, proof that even silence in the mountains is never truly still. Mountain caves form when water dissolves ancient limestone layers. Many mountains hide labyrinths beneath their surfaces, carved by the slow work of water. When rain absorbs carbon dioxide from the air and soil, it becomes slightly acidic. Over millennia, it seeps into cracks within limestone, dissolving the rock grain by grain. These passages widen into tunnels, chambers, and vast underground rivers. Stalactites and stalagmites grow where mineral-rich droplets fall, creating forests of stone. Some of the world's deepest caves, such as those in the Caucasus and the Carpathians, stretch for miles under the mountains above. Each echo inside them carries the sound of time itself, dripping in rhythm with the slow heartbeat of geology. These caves are the lungs of the mountains, breathing water and air through hidden veins, forever shaping the unseen architecture beneath the peaks we see above. Some cave systems run beneath entire mountain ranges. In places like the Alps, the Dinaric Alps, and the Appalachians, networks of caves weave through the bedrock for hundreds of miles. They connect through sinkholes, underground rivers, and chambers large enough to hold cathedrals. The Mammoth Cave system in Kentucky stretches for more than 400 miles beneath the surface, with new passages still being discovered. Such systems form over millions of years as groundwater follows natural fractures, expanding them into corridors of silence. These subterranean labyrinths are often home to unique creatures, from blind fish to translucent spiders, adapted to eternal darkness. Above ground, hikers may walk unaware of the vast, hollow world below their feet. Entire mountains can rest upon a delicate maze of caverns, each drip of water continuing the work that began before the first human eyes ever looked upon the Pan. Peaks above. Underground rivers can flow silently through mountains for centuries. Beneath the surface of many mountain ranges, water follows unseen paths, carving its own secret geography. Rain and meltwater seep into cracks, vanishing into the limestone and granite, where they gather in channels worn smooth by time. These underground rivers can flow for miles, winding through caverns older than the mountains themselves. Some resurface as springs that gush from cliffsides, while others remain hidden forever, known only by the faint sound of distant dripping. Scientists trace them with dyes and instruments, watching bright colors appear miles away, days or even weeks later. In these depths, water carries whispers of the surface world, shaping stone grain by grain. The rivers move slowly, patient as sleep, etching their signature through the mountain's heart. To imagine them is to picture a planet breathing inward, its pulse flowing quietly beneath rock and darkness. Rare crystals grow deep within mountain caverns. Far below where sunlight reaches, the still air of caverns nurtures minerals into spectacular forms. Droplets of mineral-rich water evaporate slowly, leaving behind shimmering crystals of calcite, aragonite, and gypsum that twist and bloom like frozen flowers. In Mexico's Cave of the Crystals, enormous selenite pillars rise taller than houses, glowing with a ghostly translucence in the dim light. Some of these formations took hundreds of thousands of years to grow, expanding at the pace of a heartbeat. The balance of temperature and humidity must remain perfect, or the crystals will stop growing entirely. Each one is a record of patience, a sculpture shaped by time and chemistry. Deep inside the earth, where silence reigns, the mountains continue to create beauty unseen by human eyes, an underground world of lightless elegance that sleeps within the bones of stone. Precious metals often form where ancient mountains once stood. Gold, silver, and copper do not simply appear by chance. They are born from the heat and pressure that once pulsed beneath ancient mountains. When magma cools slowly underground, it releases mineral-rich fluids that seep through cracks and faults, leaving behind veins of metal. As mountains erode over millions of years, these veins become exposed, ready to be discovered by rivers or by human hands. Many of the world's greatest gold fields, such as those in South Africa and Australia, lie where long-vanished mountains once towered. Mining them is, in a sense, unearthing the ghosts of peaks that disappeared before humans existed. Each nugget of gold or trace of silver is a relic of fire and time, a fragment of the planet's deep alchemy. Mountains are not only monuments of rock, they are the crucibles where Earth refines its hidden treasures. Diamonds can rise to the surface during mountain-building events. Deep beneath the crust, at depths greater than 100 miles, carbon atoms crystallize under immense heat and pressure into diamonds. These gems remain buried for ages until violent eruptions or tectonic collisions thrust them upward. The same forces that fold and lift mountains can carry diamonds closer to the surface through volcanic pipes called kimberlites. In places like Africa and Siberia, these eruptions left behind vast deposits scattered through ancient mountain roots. Some diamonds contain tiny inclusions of minerals formed at incredible pressures, providing clues about the deep earth that no instrument could reach. Each gem is a messenger from a world few will ever see. When light passes through a cut diamond, it carries with it a story that began in darkness, born from the same upheaval that raises continents and shapes the spines of the world. The rocks of mountains can reveal the chemistry of early Earth's oceans. Long before life flourished, minerals within seabed sediments recorded the chemistry of ancient oceans. When these sediments were later uplifted into mountain ranges, they preserved a chemical fingerprint of the water in which they formed. By studying these rocks, scientists can reconstruct the oxygen, carbon, and iron levels of Earth's early seas, tracing the gradual changes that allowed life, to emerge. Some mountain limestones still contain the faint imprint of stromatolites, layered structures built by ancient microbes billions of years ago. Others hold bands of red and grey that tell of the planet's first rusting, when oxygen began to fill the atmosphere. To hold such a rock is to touch the memory of the world's first oceans, trapped within stone and raised skyward. Mountains do not just reach into the heavens, they carry the story of the sea. Fossils found in mountains prove that ancient seas once covered them. High among the peaks, far from any shore, seashells and coral fossils lie embedded in stone. These remnants of marine life are silent witnesses to the fact that mountains once lay beneath vast oceans. When tectonic forces collided and pushed the seafloor upward, these fossils rode with it, preserved in limestone and shale. The Alps, the Himalayas, and the Rockies all hold shells and fish bones that formed millions of years ago under shallow seas. Fossils in these rocks reveal not only lost creatures, but also the ancient climates that shaped them. They are the perfect contradiction, proof of water found in the heart of stone. To find a seashell on a mountaintop is to realize that every peak was once a seabed, and that even the loftiest summits were born from the depths of a living ocean. Some mountains contain evidence of lost continents. Beneath the visible crust of modern continents lie fragments of vanished worlds. Within certain mountain ranges, scientists have found rocks that do not match the land around them. These exotic blocks, known as terranes, are pieces of ancient continents carried across oceans by drifting tectonic plates. When the plates collide, the fragments are welded into new mountains, preserving clues about lands that no longer exist. The Himalayas, for instance, contain rocks once part of the Tethys ocean floor, while Canada's northern mountains hold remnants of a forgotten microcontinent called Arctica. By studying their composition and age, geologists can reconstruct entire continents erased from the map of time. Mountains thus serve as living archives of Earth's migrations, holding within their layers the puzzle pieces of a planet that has been forever breaking apart, reassembling itself across deep history. A few ranges still carry traces of the supercontinent Pangaea. 200 million years ago, all the continents were joined together in a single vast landmass called Pangaea. When it began to break apart, the fractures became future oceans, and the ridges became mountain chains. Today, the Appalachian Mountains in North America and the Atlas Mountains in Africa share the same geological roots, once part of the same continuous range. Even their rocks and fossils match like separated pages of a single book. As the continents drifted apart, these shared mountains were divided, carried away to different corners of the world. To stand on an Appalachian summit is to touch the same ancient stone that forms peaks across the Atlantic. Mountains are the stitching that once bound the continents together, and through them, the memory of Pangaea endures, a reminder that every shore was once joined in a single embrace of stone. Mountains have influenced global wind and rain patterns for millions of years. When a mountain range rises, it changes the way air and moisture move around the planet. Winds forced upward cool and release rain on one side, leaving deserts in the shadow behind. Over millions of years, this reshapes ecosystems, rivers, and even the course of evolution. The Andes created the arid Atacama Desert. The Himalayas redirected the jet stream. The Rockies guided storms that helped carve North America's plains. By altering atmospheric circulation, mountains influence where forests grow and where grasslands spread. They even affect the amount of carbon drawn from the air, since rain falling on young mountains carries minerals that trap carbon dioxide in the ocean. The link between stone and climate is profound. As the land lifts, the air learns new paths, and in that constant dialogue between height and wind, the rhythm of the planet itself evolves. The rise of the Himalayas helped shape the world's monsoon systems. When the Indian plate collided with Asia, it lifted not only mountains but entire weather systems. The growing Himalayas created a vast wall that trapped moisture from the Indian Ocean, forcing it to rise and cool into heavy seasonal rains. This process gave birth to the monsoons that now nourish millions of lives each year. The plateau behind the range acts like a giant heat engine, absorbing sunlight and driving air currents across the region. Without the Himalayas, the climate of Asia would be unrecognizable, and much of the continent might be arid desert. The very water that sustains fields and forests owes its pattern to the shape of stone. Each drop of monsoon rain is a distant echo of that ancient collision, a reminder that mountains and atmosphere are bound in a partnership that still dictates the bowl, turning of the seasons. Mountain weather can change faster than any other place on Earth. In the span of a few minutes, a mountain can transform from calm sunlight to blinding storm. Warm air rises quickly along the slopes, cooling as it meets colder layers above. Clouds form, lightning flashes, and winds shift with almost no warning. Climbers have watched blue skies vanish into snow squalls before they can descend. This rapid change occurs because mountains disrupt the smooth flow of the atmosphere, forcing air into turbulence. The peaks become engines of unpredictability, their height and temperature differences spawning storms that appear and dissolve in hours. In the Alps, weather can shift 4 seasons in a single day. Such volatility gives mountains their sense of living presence, as if they breathe weather in and out. To stand on a summit beneath racing clouds is to witness nature's swiftest transformations unfolding in real time. Some storms form and vanish within a single valley. In mountainous regions, the air's behavior is shaped by the land beneath it. A single valley can act as a cradle for weather, trapping warm air during the day and releasing it at night. When moist air rises from the valley floor and cools, sudden storms can bloom and fade within minutes, never crossing the surrounding ridges. Thunder rolls between the slopes, echoing in perfect rhythm, while rain falls on one side of a river and not the other. Locals learn to read the signs: the shape of a cloud, the scent of ozone, the stillness before a downpour. These miniature weather systems are a reminder that not all storms are vast or global. Some belong only to a single mountain, a private conversation between air and stone that begins and ends before the world beyond even notices. Entire cities depend on mountain snowmelt for their water supply. The snow that gathers each winter on mountain slopes is a vast reservoir, storing the water that sustains life below. As spring warmth arrives, it melts gradually, feeding rivers that supply entire cities. Los Angeles relies on snow from the Sierra Nevada, while much of South Asia depends on Himalayan meltwater for drinking, irrigation, and power. This delicate system depends on balance. Too little snow brings drought, too much causes floods. Scientists monitor snowpack carefully, knowing that a shift in temperature can change the fate of millions. Every flake that falls in winter is a promise written in white, a contract between mountains and the valleys below. When it melts, that promise flows outward as rivers, turning ice into abundance. To understand the true generosity of mountains is to realize that they give life drop by frozen drop. When mountains lose snow, downstream rivers can disappear. As global temperatures rise, many glaciers and snowfields are retreating faster than they can replenish. These frozen stores of water once released steady flows through the warm seasons, feeding rivers long after the last rainfall. Now, as they shrink, streams run dry earlier each year. In the Andes and Himalayas, entire communities that depend on meltwater are beginning to feel the loss. Rivers that have flowed for centuries are dwindling into trickles by midsummer. This change affects far more than humans. It transforms ecosystems, wetlands, and agriculture across continents. The disappearance of mountain snow is silent but immense, a vanishing reservoir hidden at the world's roof. To watch it fade is to witness the unraveling of time itself, for once the ice is gone, it will take millennia to return. The mountains remember water, even as the valleys forget. Certain mountain valleys act as natural amplifiers for sound. In some high valleys, sound behaves like light in a mirror. The walls of rock and the shape of the terrain reflect and focus waves of air, amplifying even the faintest noise. A single call, a crack of ice, or the roll of thunder can echo for miles, repeating again and again until it fades into silence. Some valleys produce long, haunting reverberations that seem to come from nowhere, while others distort sound so that it feels closer than it is. Ancient peoples often believed these echoes were voices of spirits or gods answering from the cliffs. Scientists now understand that it is the acoustics of the stone itself, perfectly curved to trap vibration. Still, when you hear your own voice returned by the mountains, it feels less like physics and more like communication, a conversation between self and landscape, never truly ends. Voices can echo for minutes inside some mountain basins. In rare geological formations, echoes do not fade quickly. A single shout or bell strike can linger, bouncing between curved walls of rock for nearly a full minute. The fjords of Norway, the volcanic calderas of Iceland, and certain Himalayan valleys are famous for this phenomenon. The echo seems alive, repeating and reshaping itself as the air moves. Early travelers wrote of mountains that spoke back, their words carried across frozen lakes and amplified by cliffs. Even today, the effect feels otherworldly. Sound becomes a physical presence, filling space like mist. These long echoes reveal how mountains hold and release energy, how air and stone work together in resonance. When all falls silent again, the quiet feels deeper, as though the world itself has exhaled. Mountains teach us that even a single sound can outlive its source among their vast walls of memory. Thin air at high altitude allows light to scatter in brilliant colors. At great heights, the thinner atmosphere means there are fewer particles to diffuse sunlight. As a result, the sky appears a deeper blue, and at sunrise and sunset, colors stretch across the spectrum in vivid bands of crimson and gold. Dust and ice in the upper air refract light into halos and glories, sometimes producing rare green or violet flashes. The reduced scattering also makes stars sparkle more sharply at night, their colors pure and bright. On the highest peaks, shadows appear sharper and distances more surreal, as if the world itself has been polished by altitude. Photographers and climbers alike speak of the light as almost supernatural. It is the same sunlight we know, yet at these heights, stripped of haze and interference, it reveals its true clarity. The mountains show us light as it was meant to be seen. Raw, radiant, and infinite. Mountains are some of the best places on Earth to see the stars. Far from city lights, where the air is thin and dry, the night sky unfolds in astonishing clarity. On mountain summits, you can see more stars than most people ever imagine exist. The Milky Way arches from horizon to horizon like a river of pale fire, and faint nebulae glow where airglow and pollution cannot reach. Astronomers build observatories on high peaks for precisely this reason. The atmosphere is calmer, the view sharper, and the stars more stable for observation. On Mauna Kea in Hawaii or La Silla in Chile, telescopes peer deep into space through air that has barely been touched by moisture or dust. To stand outside at such altitude is to feel suspended between Earth and the universe, surrounded by silence and starlight. The mountains bring the heavens close enough to feel, as if the cosmos were leaning nearer to listen. Ancient astronomers used mountain peaks to study the heavens. Long before telescopes, mountains served as natural observatories. In ancient Babylon, priests climbed ziggurats modeled after sacred hills to chart the movement of stars. In the Andes, the Inca aligned temples with solstices and used mountain ridges as celestial markers. Greek astronomers scaled Mount Helicon and Mount Ida to watch the skies unobstructed by haze. Even in ancient China, emperors built stone platforms on high ground to track comets and eclipses. These early sky watchers understood that altitude meant clarity, that each step upward brought them closer to the eternal rhythm above. From their vantage points, they mapped constellations, predicted seasons, and wove myths from the patterns of light. Every high place became both temple and telescope, a reminder that our desire to understand the heavens has always been intertwined with our instinct to climb closer to them. Some of the world's largest observatories sit high above the clouds. Modern science continues the ancient tradition of watching the heavens from the heights. The European Southern Observatory in Chile's Atacama Desert, the Keck Observatory atop Hawaii's Mauna Kea, and the Indian Astronomical Observatory in Ladakh all stand at altitudes where air is thin and dry. From these summits, telescopes can peer through the atmosphere with minimal distortion, capturing light from galaxies billions of years old. Engineers and astronomers live and work in thin air, surrounded by silence and stars. Above the clouds, the night is so clear that the Milky Way casts shadows on the ground. These observatories represent humanity's highest reach for knowledge. built where the sky itself begins. The same mountains that once sheltered myths of gods now host the instruments that reveal the true scale of the universe. Stone and starlight have always shared the same horizon. The tallest mountains on other planets defy imagination. Earth's peaks are impressive, but in our solar system, they would be considered modest. On Mars stands Olympus Mons, a shield volcano nearly 3 times the height of Mount Everest. Its base is so vast that it could cover the entire state of Arizona. Because Mars has lower gravity and no plate tectonics to drag the crust downward, the volcano grew unchecked for millions of years. Its slopes are gentle, stretching hundreds of miles from summit to plain. Other worlds host mountains that rise even higher relative to their size. On the asteroid Vesta, a peak called Resilvia towers across a world barely 300 miles wide. In the thin Martian air, Olympus Mons casts a shadow that stretches beyond the horizon. These alien mountains remind us that the forces shaping landscapes are universal, sculpting beauty from fire and stone, wherever planets dare to stand tall. There are mountains made of metal on Mercury. Mercury, the smallest and innermost planet of our solar system, hides mountains unlike any found on Earth. Its surface, scarred by ancient impacts, holds ridges and cliffs made partly of metallic rock, rich in iron and silicate. These mountains formed when the planet's interior cooled and shrank, wrinkling the crust like the skin of a drying fruit. Some cliffs, called lobate scarps, rise more than a mile high and stretch for hundreds of miles across the landscape. Because Mercury's crust is denser and harder than Earth's, its mountains gleam in sunlight like burnished steel. Scientists believe these ridges mark the planet's gradual contraction as it lost heat from its molten core. To stand upon them would be to see sunlight reflecting from stone that once flowed like liquid metal, a vision of geology frozen in its final breath, glittering beneath an endless sky of fire. Ice mountains drift across Pluto like floating glaciers. At the edge of our solar system, where the sun is only a distant star, Pluto wears a crown of icy peaks that move slowly across its surface. These mountains are made of water ice, frozen so hard that it behaves like granite. Yet beneath them lies a sea of softer nitrogen ice that flows like syrup under its own weight. Over centuries, entire ranges drift, pushed by the slow currents of frozen nitrogen beneath. Some peaks rise taller than the Rockies, their summits gleaming in the faint light of the sun. When NASA New Horizons spacecraft flew past Pluto, it captured these drifting giants gliding across a pale plain called Sputnik Planitia. They are mountains without roots, floating upon an alien sea, reminders that even in the coldest darkness, motion and transformation continue, shaping worlds far beyond the warmth of our own. Venus has volcanoes larger than any on Earth. Beneath its thick yellow clouds, Venus hides volcanoes that dwarf most of Earth's. The largest, Mont Mons, stands nearly 5 miles high and spans hundreds of miles across its base. Around it lie vast lava plains and shield volcanoes so broad they merge into one another, covering nearly 80% of the planet's surface. Unlike Earth, Venus shows little sign of plate tectonics. Instead, its crust seems to rise and fall as giant plumes of magma push upward from below. Some of these volcanoes may still be active, releasing heat and gas into the choking atmosphere. Recent radar data suggests changes in their shapes, hinting at ongoing eruptions. If you could stand there, the air would shimmer with heat thick enough to crush steel. These mountains are monuments to a planet forever remaking itself in fire, where even the landscape burns with unending creation. Mars holds cliffs taller than Mount Everest stacked 3 times. Along the equator of Mars lies Valles Marineris, a canyon system so immense that it defies comprehension. It stretches over 2,000 miles long and plunges more than 6 miles deep. Deeper than Mount Everest is tall, even if stacked 3 times over. Scientists believe it formed when the Martian crust cracked as the nearby Tharsis volcanoes swelled with lava. Over time, landslides and ancient floods widened the chasms into a labyrinth of cliffs and valleys. Standing on its rim, you would see walls vanishing into red haze, shadows fading into a horizon that curves with the planet itself. The scale of Valles Marineris redefines what a mountain can be, transforming the landscape into a scar so vast it could swallow the entire United States. It is Mars's Grand Canyon, carved not by rivers, but by the slow tearing of a restless world. Some asteroids are shaped like miniature mountains in space. Not all mountains rise from planets. Some drift freely through space, mountain-sized fragments of rock born from ancient collisions. Many asteroids, such as Bennu and Ryugu, are roughly 1/3 of a mile tall, their peaks and ridges sculpted by eons of micrometeorite impacts. Because gravity is weak, their shapes can be jagged, resembling spinning mountains adrift in the void. Spacecraft visiting these bodies have found boulders balanced on slopes where a single touch could send them floating away. Some asteroids even rotate so fast that material drifts outward, forming faint rings of dust. To land upon one is to stand on a mountain with no horizon, where the stars never move and up and down lose all meaning. They are reminders that mountains are not confined to worlds, but are scattered throughout the cosmos, fragments of creation suspended between light and silence. Scientists study mountains to understand how planets evolve. Each mountain is a record of pressure, temperature, and time. By examining how peaks form and erode, scientists can infer the inner workings of planets both near and far. The patterns of uplift and collapse reveal how heat escapes from a planet's core, how its crust thickens, and how its atmosphere responds. On Earth, the study of mountain formation has illuminated the behavior of plate tectonics, while comparisons with Mars and Venus show what happens when those processes cease. Even the icy ridges of moons like Europa and Enceladus offer clues to how water and rock interact under alien conditions. Mountains are natural laboratories, conducting experiments in physics and chemistry on scales impossible to reproduce elsewhere. Each ridge and fold tells a story about balance and change, the same forces shaping every world that spins in the darkness of space. Climbing mountains helps reveal how life adapts to extremes. High altitudes test every limit of biology. The air grows thin, temperatures drop far below freezing, and sunlight becomes harsh and unfiltered. Yet, life endures. Scientists studying climbers, yaks, and even microorganisms living on glaciers have discovered remarkable adaptations. Bud chemistry changes to absorb more oxygen, while certain plants alter their metabolism to resist frost. Tiny microbes have been found thriving on bare rock near summits, feeding on minerals and light alone. Studying these survivors helps researchers understand how life might exist on other planets, with thin atmospheres or frozen surfaces. Every expedition into the mountains becomes an experiment in resilience, revealing the deep inventiveness of living things. In the thin air, among stone and silence, evolution speaks in whispers, reminding us that life will always find a way, even where the world itself seems to have reached its edge. Mountaineers have reached places no scientist had ever studied before. Long before satellites and aircraft, mountaineers served as the first explorers of the upper world. Their climbs often led to discoveries that scientists could not have made from below. New species of plants and insects, rare minerals, and even meteorites caught in glaciers. On Everest, climbers collected atmospheric samples that helped reveal the composition of high-altitude air. Expeditions in the Andes and the Karakoram uncovered fossils that rewrote geological history. Even today, mountaineers gather data on glacier retreat, rock stability, and weather patterns, acting as both adventurers and field scientists. Many mountains remain so remote that only those willing to climb them can study them. Every ascent is a fusion of courage and curiosity, a partnership between human endurance and scientific wonder. In reaching higher, these explorers have expanded not only horizons, but the boundaries of what humanity can know. Every mountain on Earth is slowly changing shape. To the casual eye, mountains seem timeless, yet they are in constant motion. Wind smooths their ridges, rain cuts their valleys, and earthquakes tilt their slopes. Even the weight of ice and the warmth of the sun cause daily cycles of expansion and contraction. Some peaks rise as nearby crust compresses, while others sink as erosion removes their mass. Satellite measurements reveal that no mountain stands still. Every day, the Himalayas gain a fraction of an inch, the Alps erode by the width of a grain of sand, and volcanoes breathe through subtle inflation and collapse. Though imperceptible in human lifetimes, the changes are relentless. Mountains are sculpted not once, but forever, evolving through invisible rhythms of stress and release. They are the planet's great slow-motion works of art, always in flux, always being remade by the same patient hand that first raised them. Even ancient peaks are still rising, sinking, or eroding away. The oldest mountains on Earth, like the worn-down Appalachians and the ancient ranges of South Africa, may appear quiet, the deep forces continue to shape them. Beneath their roots, the mantle still moves, sometimes lifting whole regions by slow buoyancy. Elsewhere, the crust cools and contracts, pulling mountains downward into subtle subsidence. Over it all, wind and water grind away at the surface, carrying the dust of summits into rivers and seas. The balance between uplift and erosion never ends. Geologists can trace cycles where a range has risen, vanished, and been reborn in new form millions of years later. Even a mountain that seems eternal is only a phase in the planet's breathing. The Earth is never still, and the quiet grace of these ancient hills conceals a secret truth. They are still alive, changing one invisible heartbeat at a time. Some mountains vanish as fast as they are born. In regions of volcanic or tectonic activity, entire peaks can rise and crumble within human memory. The island of Surtsey, off the coast of Iceland, was born from a volcanic eruption in 1963 and immediately began eroding into the sea. Similar mountains form along ocean ridges or in desert craters, where soft ash and lava cool quickly and yield to wind and rain. Some volcanic cones have collapsed only years after their creation, leaving behind circular lakes or valleys of ash. This fleeting existence shows how dynamic Earth's surface truly is. Mountains are not all monuments of eternity. Some are sparks that flare briefly and fade. They remind us that even grandeur can be temporary, that creation and destruction are inseparable forces in nature's design. Every vanished peak adds another layer to the world's memory of transformation. The roots of mountains extend deep into the crust like icebergs. What we see above the surface is only part of a mountain's true size. Beneath every range lies a vast hidden foundation called the mounting root, composed of dense rock that sinks deep into the mantle. These roots balance the visible peaks above, much like the submerged bulk of an iceberg. As erosion wears down the summit, the crust slowly rises to restore equilibrium, a process known as isostasy. In this way, mountains seem to float upon the planet's interior, adjusting their height in response to their own weight. Some routes extend tens of miles downward, forming immense structures that mirror the peaks above in reverse. The visible mountain is only half the story. The other half lies buried in silence and darkness, pressing gently against the heat of the Earth's heart, unseen yet essential be. To its graceful balance, a mountain's weight can bend the Earth beneath it. The immense mass of a mountain is enough to warp the crust upon which it stands. Under the Himalayas, the weight of stone pushes the lithosphere downward by several miles, creating a deep depression that supports the range like a raft. This bending is not fixed. It flexes slowly as glaciers melt, rivers carve valleys, and new rock accumulates. The crust behaves like a flexible plate, curving beneath the load and rebounding as that load lightens. Satellites can measure these subtle shifts, mapping the way the planet adjusts under pressure. The process is invisible yet continuous, part of the great balancing act between gravity and buoyancy that governs every landscape. Each mountain, by simply existing, reshapes the planet beneath it, its mass bending the Earth into curves that ripple far beyond the summit where the first stone meets the bar. Sky. Mountains create gravity anomalies that satellites can measure. Because gravity depends on mass, regions with tall, dense mountains exert a slightly stronger pull than surrounding plains. Sensitive satellites can detect these variations, measuring changes in gravity as small as 1 part in a billion. Instruments like GRACE and GOES have mapped these subtle differences, revealing how mass shifts as glaciers melt, rivers erode, and earthquakes rearrange the crust. The Himalayas, for example, show a measurable gravitational bulge, while nearby basins exhibit weaker fields where material has been displaced. These findings allow scientists to track water flow, tectonic stress, and even magma movement deep underground. To think that mountains can tug on satellites orbiting hundreds of miles above is astonishing. Their influence extends far beyond their peaks, shaping not only weather and land, but the invisible field that binds every object to the planet's surface. Some mountain ranges are used to calibrate Earth's satellite systems. Certain satellite instruments rely on fixed reference points to align their sensors precisely. The crisp outlines of large, stable mountain ranges provide ideal markers. The Andes, the Rockies, and the Himalayas are so well mapped that space agencies use them to test optical resolution, radar alignment, and elevation models. Because their features change slowly, these mountains serve as benchmarks for measuring sea level rise, glacier retreat, and even atmospheric thickness. Every pass of a satellite refines its accuracy against the ridges and valleys below. In a sense, the mountains have become instruments themselves, part of the global network that watches the planet's pulse. Their silhouettes, once used by early navigators for orientation, now guide spacecraft orbiting hundreds of miles above. The partnership between stone and satellite is a quiet reminder that ancient landscapes still anchor our most advanced eyes in the sky. The study of mountains has its own science called orogeny. The word orogeny comes from Greek, meaning the birth of mountains. It describes the processes that fold, uplift, and shape the Earth's crust into ranges. Scientists who study orogeny examine how continents collide, how rocks deform under pressure, and how erosion interacts with tectonic motion. Each range tells a different story: the explosive birth of the Andes, the steady rise of the Himalayas, the ancient sculpting of the Appalachians. By comparing these stories, geologists can trace the history of Earth's surface back billions of years. Orogeny connects every peak to a cycle of creation and decay, showing that mountains are not accidents, but essential expressions of the planet's restless energy. The term captures both the power and the poetry of geology, naming the process by which the solid earth breathes, rises, and dreams itself into shape. Mountains exist on every continent, even under the sea. Every corner of the planet bears the marks of uplift. From the icy ridges of Antarctica to the steaming volcanoes of Hawaii, mountains rise wherever forces meet. Beneath the oceans, vast underwater ranges like the Mid-Atlantic Ridge stretch for tens of thousands of miles, forming the longest mountain chain on Earth. Even small islands often conceal towering peaks beneath the waves, their summits breaking the surface as atolls or volcanic cones. Whether cloaked in snow or coral, mountains represent the universal language of planetary motion. They form wherever heat, pressure, and gravity find balance. No continent, no ocean floor is free from their touch. The world's spine is continuous, wrapping the globe in stone and silence. Wherever we look, the outline of a mountain is there, shaping the horizon of every world we call home. The story of mountains is the story of our planet's restless surface. Every mountain range marks a chapter in Earth's autobiography. Their peaks rise from collision, their valleys from collapse, their stones from the cooling of ancient fire. Together, they record the ceaseless movement of the crust, the shifting of continents, and the breathing of the mantle beneath. When scientists read this story, they see a planet that has never stopped evolving. Mountains grow and fade. Oceans open and close, yet the rhythm continues. Each grain of sand once belonged to a summit. Each summit will someday return to dust. The mountains are both memory and prophecy, telling us what the world was and what it will become. They remind us that stability is an illusion and that beauty often emerges from upheaval. To study them is to glimpse the Earth's heartbeat, pulsing steadily beneath the stillness of stone. Every mountain holds a memory of the forces that shaped the world. Within every ridge and boulder lies a story written in texture and grain. Some rocks bear the marks of ancient volcanoes, others hold fossils of vanished seas. The minerals inside reveal the pressures they endured, the heat they survived, the journeys they made from deep within the earth to the light of the sky. Mountains are memory made solid, the planet's diary in stone. To touch one is to reach across millions of years, to feel the pulse of creation still faintly warm beneath the surface. Every peak, no matter how distant or silent, carries this memory forward. When we gaze upon them, we are not just looking at rock, but at history itself, compressed into form. Mountains do not forget. They stand as witnesses to everything that has ever moved, breathed, or dreamed upon the face of the earth. Glaciers can create powerful outburst floods. Sometimes water builds up behind natural ice dams or in lakes trapped within glacier basins. When the pressure becomes too great, the barrier can give way, releasing a sudden and massive flood. These events send torrents of water, ice blocks, and sediment rushing downstream with immense force. The floodwaters can reshape valleys, sweep away vegetation, and change river courses within hours. The timing is often unpredictable, since the internal structure of a glacier can shift without warning. Researchers study patterns of melting and water accumulation to understand when such floods might occur, but the hidden nature of the water makes forecasting difficult. Once the rush has passed, new landscapes remain in its wake, marked by fresh channels and deposits of silt and stone. These floods are reminders of the power stored within frozen environments, where ice can hold back vast reservoirs until the moment of release. Some glaciers preserve ancient creatures perfectly. In extremely cold environments, animals that perish near glaciers can become locked within the ice before decay has a chance to begin. Over time, snowfall buries them deeper, insulating them from warmth and oxygen. The ice surrounds the remains and halts biological activity, preserving everything from skin and fur to internal organs. When the glacier eventually melts or shifts, these frozen beings may reappear near the surface, looking almost unchanged despite the passing of long ages. Scientists study such discoveries to understand ancient ecosystems, migration patterns, and environmental conditions that shaped the world in earlier times. The ice becomes a vault that holds these creatures in suspended stillness, connecting the present to distant eras when climates, landscapes, and living communities were vastly different. In this way, each preserved organism becomes a messenger from a forgotten chapter of life on Earth. There are glaciers that grind mountains into powder. As these massive bodies of ice move, they press stones into the bedrock beneath them with enormous force. Every inch of motion drags rocks across the ground like countless heavy blades scraping the surface. Larger fragments fracture and break into smaller pieces, and those smaller pieces are crushed again into even finer particles. Over long periods, this relentless grinding produces a soft, pale material often called rock flour. When meltwater carries this fine powder into lakes and rivers, it gives them the distinctive cloudy or turquoise appearance because the tiny particles scatter sunlight in a unique way. The entire process reveals just how powerful moving ice can be. Peaks that once towered high can be worn down grain by grain. Valleys become smoother and deeper. Even the seemingly immovable strength of mountains is no match for the slow, unstoppable pressure of glacial ice. Some glaciers sing with high-pitched sounds. Within the cold walls of certain glaciers, delicate tones can rise and fade in the air. These high-pitched sounds come from a variety of subtle movements inside the ice. Tiny fractures opening and closing can release a brief, sharp note. Pressurized meltwater pushing through narrow channels can whistle softly. Even the shifting of ice crystals under changing temperature can produce faint vibrations that carry through the glacier. When conditions are just right, these small sources combine into a shimmering soundscape that locals sometimes describe as singing. Sensitive equipment placed on the surface can capture a rich chorus of pitches that human ears might not fully detect. Each tone reflects the physical state of the glacier, revealing changes in temperature, pressure, and internal flow. The effect is a reminder that glaciers are not silent at all. They hold a subtle acoustic life shaped entirely by movement within frozen walls. Glacial ice can be older than human civilization. Deep inside the thickest ice sheets, layers of snow from distant ages have been compressed into solid ice and preserved far beyond the span of recorded history. Each layer represents a winter that fell before cities rose, before written languages formed, before agriculture shaped human societies. The deeper one goes, the further back the record stretches, in some places reaching into times when the planet followed very different rhythms of temperature and climate. These ancient layers contain dust from volcanic eruptions, traces of distant storms, and even tiny bubbles of air that formed long before any modern human breathed. Scientists drill long cylinders of this ancient ice and examine them carefully to reconstruct environmental conditions from ages beyond memory. In this frozen archive, history is measured not in centuries, but in enormous sweeps of time, preserved with extraordinary clarity within the depths of the glacier. Some glaciers feed rivers that travel across continents. In many regions, meltwater that emerges from a glacier becomes the headwater of a river that flows for great distances. As the glacier melts during warmer seasons, clear, cold streams trickle from beneath the ice and gather strength as they move downslope. These streams combine to form rivers that cross plains, forests, and grasslands, supporting countless ecosystems along the way. Communities rely on this steady supply of water for agriculture, daily use, and hydropower. Even regions far downstream feel the influence of glacial melt, since the timing and volume of water can shape the rhythm of entire watersheds. Long after the meltwater leaves the shadow of the ice, it continues its journey across varied landscapes, linking distant environments to the high frozen source where the river was born. The glacier becomes part of a vast network that sustains life far from the cold world of its origin. There are glaciers hidden inside desert mountains. It may seem unlikely that ice can survive in regions known for heat and dryness, yet in certain high-altitude deserts, isolated glaciers persist in deep Iran. Shadows where sunlight rarely reaches. These glaciers form in sheltered ravines or cirques, where cold air sinks and remains trapped. Snowfall, though rare, can accumulate over time and slowly transform into ice if temperatures stay low enough. The surrounding landscape may be bare rock and sand, but within these protected pockets, frozen masses hold on through long periods of dryness. Their presence reveals how local topography and microclimates can preserve ice even in environments that seem too warm or arid for it to exist. These hidden glaciers offer scientists a chance to study how ice can survive in extreme conditions and how small, sheltered environments can maintain cold refuges even when the broader climate is harsh. Some glaciers create mirages on clear days. When sunlight strikes cold surfaces and meets pockets of warmer air rising from nearby ground, unusual distortions can appear above the ice. These shimmering visual effects bend light in ways that make distant shapes appear lifted or stretched. A ridge far away might look like it is floating, or a dark patch of rock may seem to ripple like water. On especially clear days, the contrast between cold air near the ice and warmer air from surrounding terrain can create layered temperature gradients that bend light dramatically. Travelers have sometimes mistaken these mirages for distant lakes or sudden cliffs, only to discover that the landscape shifts as they move. These optical illusions provide clues about the delicate balance of temperature and air density that forms above glaciers, revealing the invisible motions of the EAR, atmosphere that play out quietly over frozen ground. Glaciers can crack with tremendous vibrating roars. Although glaciers often appear solid and unchanging, the forces inside them build constantly. When the stress becomes too great for the brittle upper layers to withstand, a crack can open with explosive energy. The sound bursts outward as both noise and vibration, echoing along valley walls and resonating through the ice itself. These roars can start with a sharp snap that grows into a rumbling growl before fading back into stillness. Instruments record the shaking as seismic signals that help researchers track how the glacier is moving and shifting. Some cracks open along the surface, creating deep crevasses. Others occur inside the glacier, unseen but powerful. Each event marks a moment when internal forces rearrange the structure of the ice. The memory of that sudden fracture remains in the glacier's layers, preserved in patterns that continue to evolve as the ice flows downslope. Some glaciers create rare frozen waterfalls. During certain cold periods, meltwater that usually flows freely from the glacier's surface or interior can freeze in mid-descent along steep cliffs. The result is a sheet or curtain of ice suspended where a waterfall once fell, capturing motion in still form. These crystal structures can grow thicker with each new freeze, forming delicate patterns that vary with temperature, sunlight, and wind. Some frozen waterfalls contain layers of blue or white ice that reveal changes in water flow, while others hold translucent columns shaped by splashes that crash, solidified instantly. When temperatures warm again, the structure begins to melt from the inside or crack apart in large sections. These fleeting formations offer a rare glimpse into moments when flowing water and freezing air meet in perfect balance, preserving movement in the intricate kit. Sculpture of a frozen fall. There are glaciers that move on layers of slippery mud. Not all glaciers slide across solid bedrock. In some regions, a layer of soft, water-saturated sediment lies beneath the ice. This muddy foundation can deform easily, acting almost like a thick fluid that supports and transports the glacier above. As the ice pushes forward, the mud shifts and squishes, altering the speed and shape of the glacier's movement. This type of base allows even heavy ice to move more quickly than it would over a rough, rocky surface. The mud also traps and rearranges stones carried by the glacier, leaving behind unusual patterns of sediment once the ice retreats. Scientists study these muddy beds to understand how glaciers respond to changing water conditions and how soft ground influences the resilience and stability of entire ice systems. Glaciers can grow from a single persistent snowpatch. In certain cold, sheltered locations, one patch of snow can survive summer after summer without melting away. Each winter brings new snowfall that adds to the old layer. Over time, the weight of these accumulated layers presses the lower snow into firn and eventually into ice. What began as a small patch becomes the seed of a miniature glacier. As it grows thicker, the mass becomes heavy enough to start creeping down slope. Small crevasses appear. Rocks fall onto the ice and become embedded. The patch transforms into a genuine glacier with its own flow, structure, and meltwater channels. This slow birth process shows how glaciers can arise from the simplest beginnings when conditions allow snow to outlast the warmth of summer. From a single persistent remnant of winter, an entire frozen system can emerge. Some glaciers hold clues to ancient climate shifts. Layer by layer, the snow that falls on a glacier becomes a record of the atmosphere that existed at the time it settled. Each winter leaves behind a sheet of snow with its own blend of dust, trapped air, and chemical signatures. Over long spans of time, these layers compress into ice that preserves an incredibly detailed timeline of environmental change. Scientists who study the deepest sections of glacier cores can detect past periods of warming and cooling, shifts in wind patterns, major volcanic eruptions, and even traces of vegetation carried from distant places. The thickness of each layer reveals how much snow fell in a particular year. The composition of tiny air bubbles tells how much carbon dioxide and methane were in the atmosphere. By examining these features, researchers can reconstruct climate patterns that stretch far beyond human memory. Glacier ice becomes a silent witness to Earth's shifting rhythms, preserving each turn in the planet's long environmental story. There are glaciers that form delicate needle ice structures. On the surfaces of some high-altitude glaciers, thin spires of ice can rise from the ground like tiny crystalline forests. These needle-shaped formations grow when strong sunlight warms the surface just enough to cause slight melting, followed by rapid freezing in cold air. The meltwater evaporates upward, leaving behind narrow ridges of ice that point toward the sky. Over time, these ridges can sharpen into intricate shapes that seem almost impossible for nature to produce. They form only under very specific conditions, where intense light meets extremely dry air and strong temperature gradients. Climbers sometimes find these fragile spikes difficult to cross, since the spires can be sharp enough to cut fabric or collapse unexpectedly beneath their weight. Their presence reveals how sunlight, wind, and cold interact in rare combinations to create formations as artistic as they are fleeting. Some glaciers stretch across multiple climate zones. Large glacier systems that originate high in mountain ranges or across polar plateaus often extend into regions with very different environmental conditions. At the top, snow drifts across ridges under frigid air, where accumulation far exceeds melting. As the ice flows down slope, it can pass into milder zones where temperatures rise and melting increases. Further down, the glacier may enter valleys with warmer summers and more variable weather, where meltwater streams cut channels across the ice. Yet the glacier remains one connected body, shaped by the contrasts between these zones. This creates striking differences in surface texture, color, and even motion along its length. The upper sections may be covered in fresh snow, while lower levels may reveal bare blue ice marked by debris bands. These gradients offer scientists a living laboratory for studying how a single glacier responds to entirely different climate influences from top to bottom. Glaciers can create their own lakes. As a glacier moves, it can carve deep hollows in the land beneath or leave behind large depressions once the ice retreats. Meltwater pools in these basins, forming lakes that owe their existence entirely to the glacier's earlier activity. Sometimes the lake forms while the glacier is still present, trapped behind natural ice or moraine dams. These glacial lakes can be vivid shades of turquoise or green because rock flour suspended in the water scatters sunlight in a distinctive way. In other cases, the lake appears only after the glacier melts back, filling the newly exposed landscape with fresh water. These features can grow, shrink, or change shape as melting patterns shift. They support unique ecosystems adapted to cold, mineral-rich water and provide important sources of fresh water for nearby communities. The landscape shape becomes a reminder of the glacier's powerful sculpting long after the ice is gone. Some glaciers cause Earth's crust to rebound when they melt. The sheer weight of thick ice sheets compress the ground beneath them downward over thousands of years. When that weight is removed, the crust slowly rises again in a process known as isostatic rebound. This uplift continues long after the glacier has disappeared, sometimes for many centuries. Entire coastlines can rise, altering the shape of bays and inlets. Rivers may shift their courses as the land tilts upward. Ancient shorelines can be found far above modern sea level, marking previous positions of the land before rebound occurred. Scientists measured this ongoing rise using satellites and ground sensors, allowing them to track how the planet responds to long-term changes in ice cover. In this way, glaciers influence the shape of continents not only when they move, but also long after they melt, leaving behind a landscape that slowly rises to K. Meet the sky once more. There are glaciers that trap entire forests beneath them. In some regions, advancing ice sheets have swept over valleys filled with trees and vegetation, burying them beneath tons of ice. The cold temperatures under the glacier preserve the organic material in remarkable condition. Roots, branches, bark, and even leaves can remain intact for long periods, protected from decay by the freezing environment. When the glacier melts or retreats, it may reveal these ancient forests, offering a glimpse into ecosystems that existed before the ice swept through. Scientists study the preserved wood to understand what species lived there, how the climate differed from today, and how landscapes changed as glaciers advanced. These fossilized forests provide an intimate view of a world that vanished under ice, yet left behind clues that help reconstruct the past with unusual clarity. Some glaciers creep through dense mountain passes. When a glacier encounters a narrow gap between mountains, the pressure of the ice behind it forces the mass into the constricted space. The ice adjusts by stretching, folding, and deforming to fit the shape of the terrain. Large crevasses may open as the glacier squeezes into the pass, while the sides can scrape along steep rock walls. This movement creates spectacular flow patterns that resemble frozen waves captured in mid-motion. Even though the passage may be tight and steep, the glacier continues forward, guided by gravity and the slow deformation of ice. Over time, the glacier widens the pass, smoothing sharp points and grinding away loose rock. These narrow channels bear the marks of the glacier's slow persistence, showing how frozen water can navigate and reshape even the most confined landscapes. Glaciers can split into multiple ice streams. Although a glacier may begin as a single mass of accumulated snow and ice, its flow can divide into separate branches as it moves across uneven terrain. Valleys, ridges, and variations in bedrock shape can direct the ice into distinct channels that act like independent rivers within the same glacier. Each stream may move at a different speed or follow a unique path depending on the slope, thickness, and underlying conditions. Where the streams rejoin, they may form dramatic folds or twisting patterns that reveal how the ice converged again. These divisions show the complexity of glacial motion and how sensitive the ice is to changes in topography. By studying how these ice streams behave, researchers gain insight into the forces that control glacial flow, from the smallest crevasse to entire frozen basins. Some glaciers create deep crevasses wide enough to swallow houses. The surface of a glacier is constantly under tension as the ice pulls, stretches, and bends while moving downslope. When the stress becomes too great, the brittle upper layer fractures into deep, narrow openings called crevasses. In large glaciers, some of these cracks can plunge down many stories, their depths disappearing into blue darkness. Their widths can grow so large that a person could walk through them if the edges were stable enough, though they rarely are. The sight of these immense fractures reveals the enormous forces acting inside the glacier. Snow bridges often conceal the openings, masking their true size beneath a thin cover of surface snow. The presence of such crevasses is a powerful reminder that glaciers are dynamic systems with immense internal tension, even when their surfaces appear smooth and calm. There are glaciers that flow all the way to the sea. In certain coastal regions, glaciers travel from high inland basins down through valleys and finally reach the ocean. These tidewater glaciers interact directly with seawater, forming dramatic ice cliffs at their fronts. As they continue to move, they release huge chunks of ice that break away and drift into the ocean as icebergs. The interface between glacier and sea is a place of constant change, where tides rise beneath the ice and waves carve patterns into its face. Seawater can flow into cavities under the glacier, melting it from below while cold air works on the upper surface. This dynamic environment influences both the glacier's speed and the conditions of nearby marine ecosystems. The flow of ice to the ocean becomes a powerful demonstration of how glaciers link high mountain snowfall to distant coastal waters in one continuous journey. Some glaciers create natural ice bridges. In certain places, meltwater streams carve tunnels through the lower layers of a glacier, hollowing out arches that remain standing even after the water has drained or frozen again. Over time, the roof of such a tunnel can harden into a smooth, curved span of ice that stretches from one side of a crevasse or valley wall to the other. These arches can be translucent or streaked with bands of blue and white, revealing layers of old snowfall pressed together by the weight above. Cold nights strengthen the structure, while warmer days can soften it, creating a shifting balance that changes the shape slightly over time. Though they may appear delicate, some of these bridges can withstand heavy loads because of the internal strength and density of the ice. Each formation is temporary, sculpted by water, light, and temperature into a natural bridge that eventually collapses as seasons and conditions change. Glaciers can flip over layers of ice like pages in a book. As layers of snow accumulate, they compress into ice sheets stacked one upon another. When a glacier encounters an obstacle such as a buried ridge or a sudden change in slope, the lower ice can be forced upward, The intense pressure can fold the layers, twisting them until the older sections lie on top and the newer sections lie below. These overturned layers may appear along cliffs or crevasse walls as colorful stripes of blue, white, or gray. Each stripe represents a different time in the glacier's past. The folding process can occur slowly or during periods of rapid movement when the glacier flows faster than usual. Scientists read these layers to reconstruct the glacier's history, learning how it advanced and retreated long before modern observers took note. The ice becomes a physical record of its own journey, written in folds created by enormous subterranean force. Some glaciers hold hidden rivers rushing beneath them. Far beneath the quiet surface of a glacier, water can flow in powerful streams created by melting at the base. Pressure from the weight of the ice lowers the melting point, allowing liquid water to appear even in freezing temperatures. That water collects in channels that twist and branch through the darkness, sometimes forming networks that rival surface rivers in complexity. These subglacial rivers can move with surprising speed as gravity and pressure push the water through narrow passages. Some of the channels remain stable for long periods, while others shift or collapse as ice flows and refreezes. The water shapes the glacier from below, influencing flow speed by lifting sections of the ice slightly or by carving deeper grooves into the bedrock. Researchers use specialized sensors to map these hidden waterways, uncovering dynamic systems that remain invisible to anyone standing on the surface above. There are glaciers that grow even while surroundings warm. Although many glaciers shrink in warmer climates, a few unusual systems manage to grow despite rising temperatures in the regions around them. These glaciers exist where local conditions overshadow broader climate trends. Deep shade from steep cliffs, persistent cloud cover, or strong winds that blow drifting snow into certain basins can supply more snowfall than nearby melting can remove. In some cases, glaciers receive extra snow from avalanches that fall from surrounding peaks, adding layers faster than heat can melt them. These unusual accumulations allow the glacier to thicken and extend even when surrounding valleys experience warmer seasons. Their behavior reminds scientists that glaciers respond not only to large-scale temperature, but also to local geography, snowfall patterns, and wind-driven redistribution of snow. Each example offers insight into the many factors that govern how glaciers evolve. Some glaciers store fallen meteorites. In certain polar deserts, meteorites that land on the ice become frozen into the upper layers of the glacier. As the ice slowly flows, wind-driven sublimation removes surface snow and ice from specific areas, causing the embedded meteorites to accumulate on core. Exposed surfaces. Over thousands of years, these dark stones can gather in clusters on blue ice fields where they are concentrated naturally by the movement of the glacier. Scientists search these locations to recover rocks that originated from asteroids, the Moon, and even Mars. The ice preserves them in remarkable condition, protecting them from weathering and contamination. Each meteorite offers clues about the early solar system, materials that formed planets, and processes that shaped worlds long before Earth's surface cooled. The glacier becomes a collector and curator of cosmic fragments, gathering pieces of distant space onto frozen ground. Glaciers can sculpt massive bowl-shaped cirques. At the head of many mountain glaciers lies a deep hollow carved by the repeated action of ice grinding against the rock. Over long periods, the glacier erodes the floor and walls of this space until it forms a steep-sided basin with a rounded floor. Snow accumulates in these protected hollows, feeding the growing glacier above. The cirque often remains shaded for much of the year, allowing ice to persist even when surrounding slopes lose their snow. Each cycle of freezing, thawing, and glacial abrasion deepens the basin further. When the glacier eventually retreats, the cirque remains as a permanent mark on the landscape. Many of these basins later fill with water, forming pristine lakes that reflect the cliffs around them. The cirque stands as a reminder of where the glacier was born and of the immense force it wielded in shaping its birthplace. Some glaciers grind boulders into smooth stones. As a glacier drags rocks across its bed, the stones grind against each other and against the underlying rock. Large boulders trapped in the base of the ice are worn down slowly. Edges soften. Corners crumble. The stones become rounded and polished as the glacier continues its journey. In some regions, enormous fields of these smoothed stones lie scattered where the ice once passed, each one shaped by the glacier's relentless movement. These stones provide clues about how long the glacier remained in a particular area, how quickly it moved, and how much pressure it exerted. Their smooth surfaces reflect the immense force that flattened and polished them without shattering them completely. These polished stones are the glacier's footprints, left behind long after the ice has gone. There are glaciers that glow blue under moonlight. At night, when the sky is clear and the moon shines on the surface of dense ice, certain glaciers take on an otherworldly blue radiance. The light that enters the ice is scattered by its crystal structure, filtering out warmer colors and leaving behind soft shades of blue that appear to glow from within. This effect becomes most striking where the ice is pure and deeply compacted, such as along cliffs or within exposed crevasses. The glow shifts gently as the moon moves, revealing patterns that remain invisible during the day. The stillness and quiet of the night amplify the effect, creating a luminous landscape shaped entirely by ice, crystal, and faint light. This natural glow is not constant. It depends on the angle of the moon, the clarity of the sky, and the purity of the ice. Each appearance is unique to that moment. Some glaciers move in rhythmic pulses. Although glaciers generally move at steady rates, some display oscillations in their motion. These rhythmic pulses can occur daily, seasonally, or at irregular intervals. They may be driven by meltwater pressure building beneath the ice, by changes in snowfall at higher elevations, or by shifts in the internal structure of the glacier. When water pressure at the base increases, the glacier may slide more quickly over the bed. As the pressure drops, the movement slows again. This cycle can repeat, creating a pulse that scientists track with precision instruments. These oscillations reveal how sensitive glaciers are to subtle changes in water, temperature, and internal stress. The pulses can reshape patterns of crevasses, alter surface features, and influence how much ice reaches the glacier's front each season. These periodic surges highlight the living character of ice in motion. Glaciers can trap dust from distant continents. Fine airborne dust can travel astonishing distances on global winds before finally settling. When that dust falls onto glaciers, it becomes locked into the surface snow. Over time, new layers bury it deeper, and the dust becomes part of the glacier's stratigraphy. Each dusty layer provides a clue about conditions far beyond the reach of the glacier itself. Some layers contain volcanic ash from eruptions across the planet. Others contain particles from deserts thousands of miles away. As the glacier flows, these layers stretch and bend, preserving thin sheets of foreign material within the ice. Researchers analyze the composition of these particles to track long-range atmospheric movement, historical storm patterns, and major climate events. The glacier becomes a collector of signals from the wider world, storing them like pages in a global archive. Some glaciers form tall ice spires called penitentes. In extremely high-altitude regions where the air is cold, dry, and thin, the surface of a glacier can develop tall, blade-like structures that stand in clustered groups. These formations grow when strong sunlight causes surface snow to sublimate rather than melt, turning directly into vapor. Tiny depressions in the snow deepen faster than flat areas, and over time the surrounding surface is left standing in narrow peaks. These peaks grow taller as the sun continues to remove material from the hollows between them. The spires often point toward the sun, forming fields of pale blue blades that can rise higher than a person. Their edges can be sharp, and their shapes shift with each change in temperature and sunlight. These icy structures reveal how, even in a frozen landscape, light and air can sculpt delicate formations that stand like frozen gardens on the glacier's surface. There are glaciers that create vast, muddy outwash plains. As meltwater flows from the front of a glacier, it carries with it a mixture of sand, silt, gravel, and stones that the ice has ground from the surrounding landscape. Over time, these materials spread across broad, flat regions, creating a braided network of channels that shift with each season. The plain grows layer by layer as fresh sediment settles during high melt periods. During warmer months, the watercourses weave through the area, depositing new material and rearranging the surface. The result is a landscape defined by constantly changing patterns of mud, gravel bars, and shallow streams. These outwash plains can stretch for great distances, linking the glacier to far downstream ecosystems. Their presence shows how glacial meltwater shapes terrain long after the ice has retreated, leaving behind sprawling zones created entirely by the steady release of sediment from the glacier's edge. Some glaciers carry massive boulders called erratics. Large stones that rest on glacier surfaces can be transported across long distances as the ice moves. These rocks may fall onto the glacier from surrounding cliffs or be plucked from the bedrock below and lifted upward through ice flow. Once on the surface, they travel quietly, carried far from their original source. When the glacier melts, the stones are left behind in strange and often isolated positions, sometimes perched in open fields or on hillsides where no similar beguine rock exists. Their size can be imposing, with some reaching the scale of small buildings. These misplaced giants tell the story of the glacier's path and the distance the ice traveled. Their unusual locations help researchers trace ancient glacial routes, revealing how ice once moved across landscapes now free of snow. Each boulder is a marker of past motion, delivered by the slow but relentless transport of ice. Glaciers can turn rocks into fine silt called rock flour. When glaciers drag stones across their beds, the grinding action reduces larger fragments into extremely fine particles. This powdery material is known as rock flour. Each grain is tiny, often far smaller than grains of sand. Meltwater streams carry rock flour away from the glacier, creating milky or turquoise water in lakes and rivers because the fine particles scatter incoming light. Over long periods, large quantities of this material accumulate in valleys and basins, forming fertile soil once plants colonize the area. Rock flour also reveals the intensity of glacial erosion, since its presence indicates that the ice has scraped and crushed rock beneath tremendous pressure. It is one of the most distinctive signatures of an active glacier, a direct result of ice shaping the ground it passes over grain by grain, moment by moment, across immense stretches of time. Some glaciers form vast layers of folded ice bands. Deep inside certain glaciers, alternating layers of snow from many different years compress into distinct bands of ice. These bands often vary slightly in color or clarity, reflecting changes in snowfall, temperature, or dust content. As the glacier flows over uneven terrain or bends around obstructions, the layers twist and fold like soft fabric under immense weight. Over time, these folds become graceful curves, loops, and arcs that can stretch for vast distances inside the glacier. When exposed along crevasse walls or polished ice cliffs, the folded layers create stunning patterns that resemble ribbons trapped in frozen motion. Scientists examine these folds to understand how the glacier once moved and how pressure changed the structure of the ice. The patterns serve as a visible memory of the glacier's shifting journey across its landscape. There are glaciers that collapse in towering icefalls. In steep mountain areas, glaciers can descend over abrupt drops or cliffs where the ice breaks apart into chaotic, towering masses. These icefalls resemble frozen waterfalls with blocks and columns stacked at impossible angles. The ice fractures as it moves over the sudden slope change, creating deep crevasses, jagged ridges, and unstable towers. The constant motion prevents the formation from ever settling into a stable shape. New cracks appear frequently as the glacier flows, causing pieces to topple or split without warning. The sound of ice shifting echoes across the valley as the glacier navigates this dramatic transition. Though dangerous and unpredictable, these icefalls provide insight into how glaciers respond to steep terrain. They reveal the raw power of frozen water forced into motion by gravity, shaping a landscape of frozen cliffs and shattered ice. Some glaciers hide hidden caves, sculpted by meltwater. Inside many glaciers, flowing meltwater carves sinuous tunnels and hollow chambers that wind deep into the frozen mass. These caves form when surface meltwater finds a crack or opening and plunges downward, melting channels as it flows. Over time, these channels widen into passages decorated with flowing patterns in the ice. Smooth walls shimmer with shades of blue, while ceilings arch in shapes molded by water swirling overhead. The structure of each cave evolves constantly as water flows, freezes, or changes course. Access to these caves can be limited and dangerous, yet they offer an extraordinary view into the heart of a glacier. Their presence shows how liquid water and ice interact, shaping hidden spaces within the glacier that remain unknown to anyone standing on the surface above. Glaciers can record volcanic eruptions within ice. When a volcano releases ash into the atmosphere, fine particles can travel great distances before settling. In glaciated regions, that ash becomes trapped in falling snow. Over time, these ash-laden layers compress into thin, dark lines inside the glacier. Each line marks a specific eruption, providing a precise record of volcanic activity that can be traced through time. Scientists drill into the glacier and analyze the ash to determine the strength and origin of past eruptions. These layers also reveal how atmospheric currents carried the ash across continents. The glacier preserves these events with remarkable accuracy, storing evidence of distant volcanoes in immaculate frozen layers. Each dark band becomes a timestamp, linking the history of fire to the slow accumulation of ice. Some glaciers move over lands that rise after ice melts. Under the immense weight of a glacier, land can be pressed downward. When the glacier retreats, the relieved ground begins to rise slowly. This uplift can continue for many centuries, reshaping coastlines, altering river paths, and changing the slope of entire regions. Glaciers that move over such rising land experience shifts in their flow because the landscape is changing beneath them. Slight tilts can influence how meltwater drains or how the glacier distributes its weight. These interactions reveal a dynamic relationship between ice and bedrock, where each affects the other across long spans of time. As the land rises, it carries with it the memory of the glacier's presence, showing how the ground itself responds to the ebb and flow of ice. There are glaciers that break apart in slow, spiraling patterns. Certain glaciers develop unusual rotational movements when ice flows unevenly across complex terrain. One side may move faster than the other, or subtle shifts in underlying rock may create curved pathways within the ice. Over time, the surface features of the glacier begin to twist, forming graceful spirals or arcs that drift down slope. Debris carried within the ice becomes arranged in looping stripes that reveal the rotational flow. These slow spirals form over many seasons and can continue evolving as the glacier changes shape. They demonstrate how sensitive glaciers are to tiny differences in slope, pressure, and inner structure. The patterns remain visible reminders of the glacier's internal choreography, a slow turning dance created by the movement of frozen water across shifting land. Some glaciers form stacked layers of ancient winters. Every winter adds a fresh blanket of snow to a glacier, and each summer compresses it beneath the weight of new snowfall. Over centuries, these layers transform into bands of ice that remain distinct from one another. Each band preserves tiny hints of the season in which it formed. Some contain faint dust from distant storms. Others hold clearer ice from particularly cold years when snow compacted more efficiently. Viewed in cross-section, these layers appear as subtle stripes of differing brightness, texture, or clarity. They can stretch deep into the glacier, forming a chronological staircase of ancient winters stacked one upon another. Scientists can trace these bands back through tremendous spans of time to study snow patterns, atmospheric changes, and environmental shifts that took place long before recorded history. The glacier becomes a vast frozen archive, storing the passage of seasons with extraordinary precision. Glaciers can cool entire regions around them. A glacier's massive surface reflects sunlight and emits cold air that flows down slope. As this chilled air spreads into nearby valleys, it lowers local temperatures and creates microclimates that would not exist without the presence of the ice. Plants that normally grow at higher elevations can survive at lower levels thanks to the cooling effect. Animals adjust their habitats accordingly, relying on the glacier's influence to maintain stable conditions in the surrounding landscape. In some mountain regions, villages experience cooler summers because cold air pours from glacial basins each night. This cooling can even influence cloud formation and wind patterns, subtly shaping the weather. The glacier becomes not only a feature of the land, but also a quiet climate regulator. Its presence alters the environment in ways that ripple far beyond its frozen surface, linking the rhythm of melting and freezing to the daily life of entire valleys. Some glaciers have surfaces covered in dark algae. During warm periods, microscopic algae can grow in thin films on the surface of glacier ice. These organisms thrive in small pockets of meltwater, using sunlight to fuel their growth. The pigments they produce give the ice a darker appearance, ranging from pale gray to deep purple depending on the species. This darker surface absorbs more sunlight, causing the top layer of ice to melt faster. The algae spread in patterns that follow the flow of water across the glacier, creating streaks and patches that shift each season. Their presence reveals how even the most seemingly barren environments support life. Researchers study these algae to understand how biological processes influence melting rates and how microorganisms adapt to extreme conditions. The glacier becomes a living canvas marked by organisms that flourish in one of the coldest habitats on Earth. There are glaciers that slide on cushions of pressurized water. At the base of some glaciers, meltwater accumulates under such intense pressure that it acts as a thin, slippery layer between the ice and the rock beneath. This pressurized water reduces friction dramatically. As a result, the glacier can glide over the ground more easily than it would otherwise. The speed of the glacier changes depending on how much water is present and how rapidly it moves through subglacial channels. During warm seasons, increased meltwater can cause the glacier to surge forward slightly faster than usual. During colder periods, the water may freeze or drain away, slowing the motion again. This cushion of water acts like a hidden conveyor, guiding the glacier as it travels across the landscape. The process reveals how meltwater plays a crucial role in the behavior of glaciers, even when the ice above appears completely rigid and still. Some glaciers make cracking sounds that travel miles. Within certain glaciers, stress builds up as ice stretches, bends, or shifts over uneven terrain. When a fracture opens suddenly, the sound can echo across the mountains, amplified by cliffs and valleys. These cracking noises can be sharp, like splitting wood, or deep, like distant thunder. Even small changes in temperature can trigger these events as ice expands or contracts. Some of the fractures occur high on exposed slopes where sunlight warms the surface, while others form in deeper layers hidden from view. Sensitive instruments detect these vibrations from far away, revealing patterns of internal movement that help scientists understand how the glacier is evolving. The cracks travel outward in waves, carrying the message that the glacier is alive with motion. What seems silent from a distance is actually filled with sound, born from the immense forces shaping the ice. Glaciers can create sand dunes from ground rock. As glaciers grind rock into fine powder, they carry that material out through meltwater streams. When the water slows, the heavier grains settle first. Over time, winds pick up these loose sediments and shape them into dunes in nearby valleys or plains. These dunes can grow quite large, their shapes shifting under the influence of strong gusts that sweep down from the glacier. Although they resemble desert dunes, their origins lie in ice rather than heat. The sand often has a unique mineral composition that reflects the rock types the glacier has eroded. These formations reveal the extended reach of glacial activity. Even long after the ice has receded, the dunes remain as reminders of the glacier's grinding power and the sediment it created. The dunes become part of the changing landscape, shaped by wind but born from the work of ice. Some glaciers form sharp ridges of ice called arêtes. When two glaciers occupy opposite sides of a mountain ridge, each one erodes its valley by plucking and grinding rock from the walls. As both glaciers deepen their valleys, the ridge between them becomes narrower and sharper. Over long periods, this ridge evolves into a dramatic spine of rock, shaped by the tireless work of ice on both sides. The ridge may include jagged points and thin crests that rise high above the surrounding slopes. These arêtes stand as bold features in mountain landscapes, marking the line where two glaciers once shaped the terrain in parallel. Even after the glaciers retreat, the ridges remain prominent landmarks formed through careful sculpting by frozen water. Their form reveals the power of ice to carve mountains into elegant, angular shapes. There are glaciers that shape jagged mountain peaks. In regions where glaciers surround high summits, the combined forces of ice grinding on all sides can sharpen the peaks into striking pyramidal shapes. These pointed summits, often called horns, arise when multiple glaciers erode a mountain from different directions. Each glacier carves out a cirque basin, and where these basins meet, the remaining peak becomes narrower and steeper. Over time, frost, wind, and continued glacial erosion refine the shape even further. These dramatic peaks rise as remnants of rock left untouched by the deepest ice, yet shaped by its persistent influence. They reveal how glaciers not only carve valleys, but also sculpt mountains into distinctive forms that stand as icons of alpine scenery. Their sharp profiles reflect thousands of years of erosion focused around a single central point. Some glaciers leave behind giant crescent moraines. When glaciers push forward, they carry with them stones, soil, and debris scraped from the land. At the glacier's front, this material accumulates in ridges shaped by the outline of the ice. When the glacier retreats, These deposits remain as curved ridges called moraines. The shape of each moraine mirrors the glacier's former edge, often forming broad crescents that arc across the landscape. These ridges can be massive, containing layers of sediment transported from far upstream. Inside them lie stones of many sizes, from fine silt to boulders that once rode in or on the ice. By studying moraines, researchers can trace the glacier's former size and movement. Each crescent ridge becomes a frozen monument to the glacier's reach, marking where the ice once stood before it melted away. Glaciers can reflect sunlight in dazzling patterns. The surface of glacier ice often contains countless tiny crystals that scatter and refract light. When the sun strikes at the right angle, these crystals catch the light and send it across the surface in shimmering patterns. On windy days, drifting snow moves across the ice and sparkles like drifting stars. Crevasses' walls reveal deeper shades of blue and white that glow when illuminated by sunlight. In some places, thin layers of surface meltwater act like mirrors, reflecting the sky in luminous patches. All these effects combine to create a dynamic and mesmerizing play of light across the glacier. Even small changes in cloud cover or sun angle shift the patterns instantly. The glacier becomes a living landscape of reflections that reveal its layered structure and crystalline beauty in motion. Some glaciers carve U-shaped valleys. When a glacier moves through a landscape, it modifies the original shape of the valley beneath it. A river-carved valley usually has a narrow floor and steep sloping sides. Once a glacier enters the same space, its massive weight presses downward and outward, widening the valley walls and deepening the center far beyond what flowing water could achieve. The glacier grinds the bedrock with embedded stones, smoothing and reshaping the sides while pushing debris forward. Over long spans of time, the valley becomes broad and flat at the bottom, framed by tall walls that curve in a gentle arc. This U-shaped form remains long after the glacier retreats, offering a clear signature of glacial passage. Lakes, meadows, and forests often grow within these wide valleys, flourishing in the terrain the glacier created. The shape itself becomes a permanent reminder of the immense forces once present, a memory etched into the land by slow-moving ice. There are glaciers that trap ancient pollen. As snow falls on a glacier, it occasionally brings tiny grains of pollen carried on high-altitude winds. These grains settle into the snow and later become buried under fresh layers. Over centuries, the pollen becomes sealed within the ice, preserved alongside dust, crystals, and bubbles of ancient air. Scientists can extract these trapped particles to learn what plants once thrived in distant regions. Some grains originate from forests that no longer exist in the same form, while others come from ecosystems that shifted with climate changes. Because pollen can survive for long periods in cold environments, it becomes a record of vegetation patterns long before written history. By studying these microscopic pieces of the past, researchers reconstruct the landscapes that surrounded ancient glaciated areas and track the movement of winds that carried the pollen across vast distances. The glacier becomes a quiet archivist, storing fragments of life from worlds long vanished. Some glaciers spill into fjords filled with marine life. Where a glacier reaches the coast, it may descend into a deep ocean inlet carved by earlier glacial activity. These fjords are often teeming with marine creatures that gather near nutrient-rich waters stirred by meltwater runoff. The glacier's front drops towering blocks of ice into the sea, creating floating platforms that shelter fish and invertebrates. As the ice melts, it releases minerals that nourish plankton, forming the base of a complex food web. The cold meltwater mixes with the salt water and creates layers of differing temperature and density that influence circulation patterns within the fjord. Seals, birds, and whales are frequently drawn to these icy environments, seeking food in waters shaped by the glacier's presence. The interplay of frozen and marine worlds forms a dynamic habitat where two very different realms meet. Each interaction between ice and sea becomes part of the larger ocean ecosystem connected to the glacier's steady flow. Glaciers can form massive plateaus of compressed ice. In some regions, glaciers accumulate so much snow that the upper sections spread outward rather than flowing rapidly down slope. The immense weight compresses layers of snow into a broad, elevated plateau that rises far above surrounding terrain. These ice fields can be incredibly thick, with smooth surfaces that stretch for many miles. Beneath the top layer, countless seasons of snowfall lie compressed into dense crystalline structures. The plateau acts as a reservoir that feeds multiple glaciers radiating outward from its edges. Weather patterns around these elevated surfaces can be unique, with cold air spilling down into valleys and strong winds sculpting intricate patterns across the ice. The stability of these plateaus depends on snowfall, temperature, and long-term climatic cycles. They stand as enormous frozen crowns atop mountain ranges, shaping the movement of ice far below them and influencing the surrounding climate through their sheer size and height. Some glaciers leave behind giant kettle lakes. When a glacier retreats, it can leave behind large blocks of ice buried under layers of sediment. These isolated pieces melt slowly, creating depressions in the surrounding ground as they shrink. Over time, the hollows fill with water that collects from rain, groundwater, or nearby streams. The resulting lakes can be small or surprise the landscape with their immense size. Each lake forms in a distinct depression, shaped entirely by the melting of the buried ice block. These basins often develop irregular shapes and varying depths, creating diverse habitats for plants and animals. Long after the glacier has vanished, the kettle lakes remain as markers of its presence. Their outlines reflect the random placement of the ice chunks left behind during the glacier's retreat, providing a clear example of how frozen remnants continue to shape the land. There are glaciers that carry entire layers of frozen ash. When volcanic eruptions send ash into the atmosphere, some of it eventually drifts down onto glaciated regions. Snowfall traps this ash within its layers, and over time, those layers become part of the glacier. The ash appears as dark stripes or bands within the ice, marking the season and event that produced the material. As the glacier flows, the ash layers bend, fold, and stretch into intricate patterns that trace the glacier's movement. Scientists use these layers to date volcanic events and track how atmospheric conditions transported the ash across long distances. Each stripe becomes a frozen snapshot of a moment in geologic history. The glacier preserves these moments with clarity, creating a record that links fire from deep within the Earth to the slow accumulation of ice on distant mountains. Some glaciers contain hidden networks of crystal ice. Within the depths of some glaciers, the pressure and temperature conditions cause ice crystals to grow into unique patterns that differ from surface layers. These crystals can interlock in complex arrangements that reflect the stress and flow within the glacier. When crevasses open or ice caves form, these networks become visible as shimmering patterns with varied textures and colors. The layers can shift from fine-grained to large faceted structures that catch light differently. These hidden zones reveal how ice adapts to the weight above it and the subtle movements of the glacier. Scientists examine these structures to understand how ice behaves under immense pressure, how crystals migrate and align, and how frozen water stores mechanical energy deep within its lattice. The glacier becomes an enormous laboratory of natural crystallography, shaped entirely by cold, pressure, and time. Glaciers can change sea levels around the world. When glaciers grow, they store vast quantities of water that would otherwise contribute to sea level. When they shrink, that stored water returns to the ocean. Even small changes in major glacial systems can influence coastlines across the planet. As more water enters the oceans, sea levels rise and reshape shorelines, flood low-lying areas, and affect currents. When glaciers expand during colder periods, sea levels drop, exposing land bridges that once connected continents. This exchange between ice and ocean has occurred repeatedly throughout Earth's history, altering migration routes, ecosystems, and the distribution of life. Modern measurements show how sensitive sea levels are to glacial changes, linking distant mountains and polar regions directly to the experience of coastal chaos. Communities. The glacier's influence extends far beyond its frozen boundary, carrying global consequences with each gain or loss of ice. Some glaciers form ripple patterns on their surfaces. On certain glaciers, the surface becomes decorated with repeating ridges and troughs shaped by wind, meltwater, and the slow deformation of the ice. These ripple-like formations may form where cold winds sweep across the glacier consistently in one direction. They can also appear where meltwater drains in thin sheets and refreezes, creating parallel lines that drift down slope as the glacier moves. The texture of these ripples changes with season and weather, sometimes appearing crisp and clear, at other times softened by fresh snowfall. The patterns offer insight into the glacier's immediate environment and the forces acting on its surface. Each line marks the interaction of air, water, and ice at a scale fine enough to reveal subtle changes in the glacier's daily life. Seen across a large expanse, the ripples give the glacier a textured appearance that reflects its ongoing response to surrounding conditions. There are glaciers that grow in volcanic calderas. In rare locations, glaciers form inside the circular basins left by volcanic eruptions. These calderas often sit high above surrounding terrain and collect snow in deep, sheltered depressions. The walls of the caldera protect the snow from strong winds, allowing it to accumulate year after year. As the layers build, they compress into ice that slowly begins to flow outward or inward, depending on the basin's shape. The combination of volcanic rock and frozen water creates a striking landscape, with warm geothermal areas sometimes sitting only a short distance from BD, solid ice. These caldera glaciers offer researchers a unique environment where volcanic and glacial processes interact. The ice records changes in volcanic activity, while the rock walls influence the glacier's shape and temperature. The result is a frozen body shaped by heat and cold in an unusual partnership found only in these remarkable basins. Some glaciers shed ice that sparks with static energy. In extremely cold and dry conditions, pieces of ice that break away from a glacier can build up static charge as they scrape against surrounding surfaces. When these charged fragments tumble or collide, they may release faint sparks that dance across their edges. This effect is most noticeable when brittle surface layers crack apart suddenly, allowing freshly exposed ice to slide against the older material. The motion creates friction that lifts electrons from one surface and deposits them on another. In the still air of polar nights, the sparks can be visible as tiny flashes of pale light. They vanish quickly, yet each flash gives a glimpse of the hidden electrical processes active in frozen environments. Scientists studying these sparks gather clues about the insulating properties of glacial ice and the behavior of charge in extremely cold climates. Although brief, the sparks mark moments when frozen water carries energy usually associated with storms and dry deserts, revealing another layer of ectine, complexity in the life of a glacier. Glaciers can create hollow chambers that echo for distances. Deep beneath the surface, meltwater can carve large chambers where sound travels in unusual ways. The interior walls of these hollow spaces are smooth, polished by flowing water that has sculpted arcs and domes from the ice. When noise enters such a chamber, it bounces between the curved surfaces, amplifying and extending the sound. A single drop of water can create a series of echoes that drift through the darkness like distant bells. These chambers change shape constantly as freezing and melting adjust the thickness of the ice. Air pressure inside may rise and fall with the movement of outside weather, adding further resonance. Explorers who enter such spaces often describe the acoustic environment as surreal, because even soft footsteps seem magnified. These echoing chambers show how water and ice can collaborate to produce natural sound stages hidden from the world above. Some glaciers leave behind stripes on bedrock. As a glacier passes over solid rock, stones frozen into its base scrape grooves into the surface like blades pulled through clay. These grooves form long, straight stripes aligned with the direction of ice flow. Their spacing and depth depend on the size of the embedded rocks and the pressure exerted by the glacier. When the ice retreats, the bedrock remains etched with these parallel lines that reveal the path of the glacier and the force of its movement. Some grooves appear shallow and delicate, while others cut several inches deep. Scientists study the orientation of these stripes to reconstruct the motion of long-vanished glaciers and to understand how the landscape evolved under the weight of ancient ice. Each stripe is a lasting mark of contact between rock and frozen mass, carved by a glacier that continued moving long after the bedrock below recorded its sea. Passing. There are glaciers that form without ever snowing heavily. In certain cold, windswept regions, snowfall may be minimal, yet glaciers still develop. These glaciers grow not from frequent local snowstorms, but from snow transported by strong winds from distant areas. The winds sweep loose snow across open terrain and deposit it in sheltered basins where temperatures remain low enough for it to accumulate year after year. Even small amounts of snowfall can create a glacier if the temperature remains cold and the snow does not melt in summer. Over time, the captured snow compresses into firn and eventually into solid ice. The glacier then begins to move slowly downslope, shaped by gravity and internal deformation. These wind-fed glaciers demonstrate how ice can form under unexpected circumstances, supported by the steady gathering of snow from far away rather than from tree. Heavy local precipitation. Some glaciers move in curving S-shaped paths. Most glaciers flow in straightforward directions dictated by gravity, but some encounter irregular terrain that forces them into curved paths. When the glacier moves over uneven bedrock or through twisting valleys, the ice responds by bending and redirecting its flow. Over long distances, this can create graceful S-shaped patterns visible from above. The internal structure of the glacier reflects these curves as well. Bands of sediment and compressed ice follow the same winding pattern, revealing the glacier's changing direction over time. These curves show how sensitive glacial movement is to tiny variations in slope, pressure, and subglacial topography. They highlight the glacier's ability to navigate complex landscapes while maintaining steady forward motion. The resulting path becomes a frozen trace of the land's hidden contours, captured in the glacier's slowly shifting form. Glaciers can create hidden waterfalls beneath their ice. Where meltwater drains along steep slopes under a glacier, it can form cascading drops that behave like underground waterfalls. Although unseen, the flow echoes through tunnels and chambers carved by the constant movement of water. These falls can be powerful enough to shape new channels, sculpting the ice above them and the bedrock below. The sound of the falling water resonates within the confined space, producing deep rhythmic tones that travel through the ice. The falls change position as the glacier migrates, forming a dynamic system of shifting cascades hidden in darkness. Scientists use sensors to detect the vibrations created by these concealed waterfalls, learning how water moves within the glacier and how its flow affects the speed and stability of the ice. These secret cascades reveal the lively world that exists in the glacier's unseen interior. Some glaciers produce rare floating pancake ice. When circular pieces of thin ice form near a glacier's outlet in cold, moving water, they can bump against each other and spin gently. Their collisions create raised rims around the edges, giving each disk a rounded shape, reminiscent of stacked pancakes. These formations occur when water remains cold enough to freeze, but also turbulent enough to shape the ice into circles. As more disks form, they cover the water's surface in floating clusters. Their soft edges rub together with every movement of the current, creating quiet murmurs that drift across the surface. The formation of pancake ice shows how glaciers influence nearby waterways by cooling them and supplying the right conditions for rare forms of ice to grow. The floating circles drift through the fjord or river, shaped by the interplay of temperature, motion, and the glacier's meltwater. There are glaciers that change color with the seasons. Throughout the year, the surface of a glacier can shift in appearance as light, temperature, and moisture vary. In winter, the ice often appears pale and powdery because new snow covers most of the surface. As spring arrives, the upper snow layers melt slightly and refreeze into smooth sheets that reflect more blue light. During summer, pockets of meltwater darken some areas while dust blown from surrounding land settles on the surface, giving certain sections a muted grey tone. Algae can also appear, adding subtle shades of green or purple in warm periods. When cooler temperatures return in autumn, the glacier brightens again, as new snow softens the colors. These seasonal changes reveal the glacier's constant interaction with the atmosphere and its sensitivity to shifts in light and temperature. Its colors become a living indicator of conditions around it. Some glaciers contain ice so dense it sinks like stone. At great depths within a glacier, the pressure becomes intense enough to squeeze nearly all air bubbles out of the ice. Without trapped air, the ice becomes significantly denser than ordinary surface ice. When chunks of this deep ice break away near the front of the glacier and fall into water, they sink instead of floating. These submerged pieces descend slowly, shimmering as light refracts through the compact crystal structure. The formation of such dense ice takes long periods of compression under heavy loads of overlying snow. Its presence tells scientists that the glacier has maintained considerable thickness over extended periods. This type of ice demonstrates how frozen water can behave differently depending on pressure and environment, creating a material that looks ordinary at first glance yet carries properties far removed from the ice found at the surface. Glaciers can produce meltwater that glows turquoise. When meltwater streams emerge from a glacier, they often carry microscopic particles of rock flour created by the glacier's grinding action. These tiny particles remain suspended in the water and scatter sunlight in a unique way. The shorter blue wavelengths of light are scattered more strongly, giving the water a vivid turquoise appearance. The effect becomes especially striking when the sky is clear and the sun is high, causing the water to shine with an almost luminous quality. Lakes fed by this meltwater can take on the same brilliant shade, creating colorful basins surrounded by rugged terrain. The glowing water reveals the glacier's influence long after the ice itself has melted, linking the color to the fine debris carried from deep within the frozen mass. The turquoise glow becomes a visual signature of glacial activity shaping the land and water. Some glaciers stretch across hundreds of miles. In certain polar regions, ice accumulates on such an immense scale that individual glaciers grow into sprawling bodies that cover vast distances. These giants extend from high interior plateaus all the way to distant coastlines, flowing steadily through valleys, across plains, and over buried mountain ranges. Their surfaces may look uniform from above, Yet each section has its own rhythm of movement shaped by snowfall, internal pressure, and changes in terrain. The thickness of these glaciers can vary greatly from one region to another, with deep interior sections holding layers of snow laid down far earlier than the ice-found K, closer to the edges. Despite their enormous reach, they remain in constant motion, responding to shifting temperatures and the slow buildup of winter storms. Scientists who study these massive glaciers track subtle variations in their movement to understand how ice travels across such great distances. The scale of these frozen systems makes them among the most impressive features on Earth, storing memories of climates far older than any human record. There are glaciers that survive entire climate cycles. Throughout Earth's history, periods of warming and cooling have come and gone, altering coastlines, forests, and deserts. Yet certain glaciers endure through these cycles, shrinking during warmer phases, but never vanishing completely. Their survival depends on a delicate balance of snowfall, shade, and temperature, unique to their location. High mountain walls might shield them from direct sunlight, or cold winds may deliver more snow than surrounding areas receive. Over thousands of years, these glaciers witness dramatic environmental changes while maintaining a continuous presence. Their ice holds layered evidence of these ancient shifts, preserving traces of volcanic eruptions, dust storms, and atmospheric changes from each cycle. By studying these resilient glaciers, scientists can track climate patterns across timescales far beyond human observation. Their survival offers a reminder of how certain frozen landscapes can persist even as the world around them transforms again and again. Some glaciers leave behind polished rock called glacial pavement. As a glacier moves across solid rock, stones embedded in its base scrape the surface with steady, grinding force. Over long periods, this abrasion can smooth the bedrock into a flat, polished expanse known as glacial pavement. The surface often shines with a subtle sheen created by countless microscopic scratches aligned with the direction of the glacier's movement. Larger grooves may also appear where bigger stones dragged against the rock. When the glacier retreats, the polished surface remains as clear evidence of the ice that once passed over it. This type of erosion creates unique patterns on the land, showing how powerful and persistent glacial forces can be. Researchers examine these surfaces to reconstruct the ancient paths of glaciers and to understand how ice shaped the terrain. The pavement stands as a permanent marker of contact between rock and moving ice. Glaciers can create entire networks of braided rivers. When meltwater flows from a glacier, it often carries vast amounts of sediment from the ice and from the ground beneath. As this water emerges into open valleys, it spreads out and slows, causing the heavier particles to settle. The flow must then divide into multiple channels to navigate around the growing deposits. This process repeats continually as water rises and falls with daily and seasonal changes. The result is a shifting maze of rivers that weave around bars of gravel and sand, forming a braided pattern across the landscape. These channels join and separate repeatedly, creating a dynamic system that changes shape with each melt cycle. Plants and animals adapt to the fluctuating water levels, developing unique ecosystems along the riverbanks. These networks show how glaciers influence not only the land beneath them, but also the rivers that flow through distant plains. Some glaciers hold enormous frozen reservoirs. Deep within thick glacial systems, immense volumes of water become locked away as compacted ice. These frozen reserves can store moisture from countless winters, preserving it in layers that stretch far below the surface. The weight of the overlying ice compresses the lower layers into dense formations that hold this water in near-perfect stability for long spans of time. When the glacier melts or retreats, these reservoirs release their stored water gradually, feeding streams, lakes, and rivers that depend on this steady supply. Entire regions rely on these frozen reserves to balance seasonal water cycles. Scientists study the volume and rate of change within these glacial reservoirs to understand how water availability will shift in the future. The reservoirs remain silent, hidden within the glacier's depths, yet they sustain life far beyond the frozen environment itself. There are glaciers that collapse in cascades of ice blocks. On steep or unstable slopes, sections of a glacier can fracture into towering blocks that tumble forward in dramatic collapses. These events occur when internal stresses build faster than the glacier can adjust, causing large chunks of ice to break apart and cascade downhill. The falling blocks create thunderous crashes that echo through surrounding valleys. Each collapse reshapes the glacier's front, revealing fresh layers of ice that soon begin their own slow journey downslope. The process can be triggered by changes in temperature, meltwater buildup, or shifts in the glacier's weight distribution. Although short-lived, these cascades leave behind fields of shattered ice that record the moment of failure. Researchers study these collapse zones to understand the stability of fast-moving glaciers and to predict similar events in the future. Some glaciers generate their own local weather. Large glaciers influence air movement and temperature in ways that can create distinct weather conditions around them. As sunlight strikes the ice, heat is reflected rather than absorbed, causing the air above to remain cold. That dense cold air flows down the glacier, displacing warmer air in nearby valleys. This movement can trigger cloud formation where the two air masses meet. Moisture carried on winds may condense along the glacier's edges, producing fog, light snow, or sudden shifts in wind direction. The glacier effectively becomes a natural climate engine, shaping conditions in its vicinity regardless of broader regional patterns. Plants and animals living near such glaciers experience these microclimates daily, adapting to temperatures and winds shaped by frozen water. These local weather patterns reveal how ice can influence not only the land, but also the atmosphere above it. Glaciers can trap microscopic life in suspended animation. Tiny organisms living in snow or meltwater can become trapped within glacial ice as new layers accumulate. Once enclosed, they enter a state where biological activity slows nearly to a halt. Low temperatures, limited oxygen, and lack of nutrients preserve them in remarkable condition for long periods of time. When the glacier melts or shifts, these microorganisms can re-emerge and resume activity as though little time has passed. Scientists study these revived organisms to understand how life adapts to extreme cold, low-energy environments and long-term isolation. Some microbes provide clues about early life on Earth, while others help researchers predict how life might survive on icy worlds elsewhere in the solar system. The glacier becomes a vault that stores microscopic communities in suspended stillness until the moment they are released again. Some glaciers form jagged crests called seracs. In steep and heavily fractured areas of a glacier, towering blocks of ice rise in chaotic formations known as seracs. These structures form as the glacier moves over sharp changes in slope, causing deep crevasses to open and intersect. The remaining columns of ice stand as irregular towers separated by narrow gaps. Their sides can be smooth or heavily sculpted by wind and meltwater. Seracs shift constantly as the glacier flows, making them unpredictable and unstable. Their jagged silhouettes create dramatic landscapes that show how the glacier responds to rapid deformation. The presence of seracs reveals areas where the ice is under intense stress, stretched and broken as it moves across rugged terrain. They offer a powerful reminder of the glacier's dynamic nature, even in places where the surface appears frozen and still. There are glaciers that march slowly across tundra landscapes. Some glaciers extend into low-lying tundra regions, where the terrain is relatively flat. In these environments, the glacier advances slowly across ground covered in mosses, shrubs, and frozen soil. As it moves, the ice pushes aside or buries the vegetation, leaving behind a trail of disturbed earth. The glacier may override permafrost, influencing soil temperature and moisture patterns beneath its mass. Over time, the leading edge of the glacier can reshape the tundra, creating shallow depressions, ridges of pushed earth, and new drainage patterns. Wildlife living in the tundra adapts to the slow advance, shifting habitats as the ice encroaches. These glaciers demonstrate how frozen systems interact with delicate ecosystems far from mountainous terrain. Their movement across flat ground shows the versatility of glacial flow and its ability to transform landscapes one slow step at a time. Some glaciers carry layers of sediment that look like stripes. As glaciers move, they collect fine silt, sand, and small stones from the ground beneath, or from debris that falls onto their surfaces. Over time, these materials become trapped between seasonal layers of snow that later compress into ice. The result is a set of dark and light bands that run through the glacier like stripes. These layers stretch and bend as the glacier flows, recording its internal motion in graceful arcs. Some bands form from volcanic ash, others from dust storms, and others from rock fragments gathered along the glacier's margins. When crevasses open or cliffs of exposed ice appear, the stripes become visible as long lines that reveal the glacier's layered history. Scientists study these patterns to understand how much sediment the glacier has transported, how the ice has moved over time, and how environmental conditions shaped each distinct layer. Glaciers can bury entire landscapes under moving ice. A glacier's slow advance can completely cover valleys, forests, and fields in thick layers of ice. When the ice accumulates faster than it melts, it spreads outward, swallowing the surrounding land. Vegetation becomes trapped beneath the glacier's weight, preserved in cold darkness for centuries. Rivers may disappear under the ice, forced into new paths or sealed entirely. Hills become flattened, and natural landmarks vanish under a frozen sheet. This transformation alters the landscape not only during the glacier's expansion, but long after it retreats. Once the ice melts, the buried land re-emerges, marked by erosion, compressed soil, and new drainage patterns. Lakes may form where the glacier once stood, and sediments left behind shape the topography for generations. The glacier reshapes everything it covers, creating a new world on the surface and leaving ancient features hidden beneath its frozen reach. Some glaciers make trembling vibrations felt through bedrock. The movement of a glacier is not silent. Deep within the ice, grinding against stone and shifting under immense stress, vibrations travel through the bedrock below. These tremors can be too subtle for humans to notice, but strong enough for instruments to detect from great distances. When ice presses against a slope or rocks beneath the glacier crack under pressure, small seismic waves pulse outward. Meltwater rushing beneath the ice can also create rhythmic vibrations that resonate through the ground. These movements offer scientists valuable information about the glacier's internal dynamics and the conditions at its base. By listening to the faint tremors, researchers can map regions of fast flow, hidden cavities, and shifts in subglacial pressure. The glacier becomes a source of quiet seismic activity, marking its presence through subtle motions felt far beyond its visible boundaries. There are glaciers that form giant ice domes. Certain glacial systems accumulate so much snow and ice in their central regions that the surface rises into vast rounded domes. These domes act like frozen summits, feeding ice outward in every direction. From above, they appear smooth and uniform, But within the dome, layers of ice flow slowly under their own weight, deforming and stretching as they move outward. The center often experiences extremely cold temperatures and constant compression, creating some of the densest ice found on Earth. Weather patterns around these massive domes are shaped by their height, with winds sweeping across their surfaces and cold air spilling down their sides into surrounding valleys. These ice domes function as engines that drive entire glacial systems, influencing how ice is distributed across hundreds of miles. They stand as monumental structures formed entirely from snowfall and time. Some glaciers leave behind long ridges of deposited sediment. As a glacier moves, it transports a mixture of ground rock, soil, and stones. When the glacier melts or pauses during its retreat, it drops this debris along its edges or at its front. Over many seasons, these deposits accumulate into elongated ridges called moraines. The ridges mark the glacier's former boundaries, preserving the shape of its advance and retreat. Some moraines stretch for great distances, curving gently across the land. They contain stones of many sizes, carried from distant mountains, and released when the ice could no longer hold them. Plants eventually take root in the ridges, turning them into rolling hills that blend with the surrounding terrain. These deposits remain long after the glacier disappears, offering a map of its past movements and the path it once followed across the landscape. Glaciers can sculpt landforms that persist for ages. The relentless grinding, plucking, and shaping performed by glaciers leave behind distinct landforms that endure long after the ice melts. Valleys are deepened and widened. Cliffs become sharpened or smoothed. Depressions carved by ice fill with water to form lakes. Plateaus emerge where thick ice once pressed down on the land. Even isolated rocks perched on surfaces reveal how the glacier once carried them from distant sources. The combination of erosion and deposition creates a landscape of features that can last for thousands of years. These landforms tell the story of past glacial paths, marking where ice once flowed and how it altered the environment with its powerful movement. The marks remain like signatures etched into the land, offering a silent history that persists across ages. Some glaciers spread out into wide fans of ice. When a glacier flows from a narrow valley into a flatter region, the ice may fan outward, spreading like a river forming a delta. This broad expanse of ice is shaped by gravity and the topography beneath it. The glacier thins as it spreads, creating a gentle slope that extends across open terrain. Surface features shift as the glacier widens, forming patterns that radiate outward from the valley mouth. Meltwater streams branching from the glacier also fan across the landscape, distributing sediment in widening arcs. These fan-shaped glaciers show how ice responds when confinement disappears and space opens before it. Their shapes offer clues about underlying terrain and how the glacier transitions from steep highlands to open lowlands. There are glaciers that crack apart in glittering showers. In some regions, surface layers of glacier ice fracture into countless small pieces that scatter light like broken crystal. These glittering showers occur when brittle ice expands or contracts rapidly due to sudden changes in temperature. The cracking produces tiny shards that slide or tumble down the glacier's surface, catching sunlight as they move. In cold, clear conditions, the fragments can sparkle intensely, creating a momentary shimmer across the frozen slope. Each small crack is part of a larger pattern of stress release within the glacier, revealing how sensitive the surface can be to temperature variations. Though brief, these sparkling events add a dynamic visual beauty to the glacier, illustrating the constant adjustments occurring in its upper layers. Some glaciers move in secret beneath thick snow layers. In places where heavy snowfall blankets the glacier year after year, the movement of the ice beneath becomes hidden from view. The smooth white surface gives little hint of the crevasses, ridges, and streams flowing below. Yet the glacier continues its steady advance, carrying layers of ice and embedded debris forward. The snow above shifts gently as the glacier moves, forming subtle waves and depressions that reveal the faintest traces of the motion beneath. Scientists use ground-penetrating radar to study these concealed movements, uncovering a world of shifting ice and flowing water hidden below the thick cover. The glacier travels silently, unseen, shaping the land beneath while its presence appears calm and featureless from above. Glaciers can leave behind boulders carried from far away. As glaciers advance, they pick up large rocks from cliffs, valleys, and mountain slopes. These boulders become lodged within the ice or ride on its surface as the glacier moves. When the glacier melts or retreats, it drops these rocks in locations far from their original homes. The boulders may appear stranded on open plains, perched on ridges, or resting in meadows where no similar rocks exist. These transported stones, known as erratics, reveal the reach and direction of ancient glaciers. Their size and placement tell the story of how the ice once flowed and how powerful its movement must have been to carry such massive objects. Even centuries after the glacier disappears, these far-traveled boulders remain as unmistakable evidence of its past journey. As we come to the end of our journey through geology, you can let the last images settle like dust in warm light. We wandered through a planet that is always becoming. We listened for the long hush of deep time, where rock is not just rock, but a record of change. We traced mountains as they rose, not in a hurry, but with steady patience. We followed rivers as they carried tiny grains onward, turning sharp edges smooth, shaping valleys with every passing season. We felt the hidden heat below the crust, where mineral crystals assemble in darkness and where new stone is born from cooling magma. And we brushed close to the places where Earth flexes, folds, and sometimes snaps, reminding us that even solid ground can move. Geology has a way of widening the mind. It invites you to picture oceans that once covered quiet plains, deserts that became stone, and living worlds pressed into fossils, held safely until time decides to reveal them. If you're still awake and you'd like to keep drifting, there's another video waiting on your screen. You can follow it into a new corner of science or into another slow wander of the natural world. And if this episode brought you a little calm, you might like to subscribe, leave a kind comment, or share the channel with someone who could use a soft place to land. For now, there is nothing you need to solve, and nowhere you need to go. Let your shoulders drop. Let your jaw unclench. Feel the weight of your body supported, and allow your breathing to find its own easy rhythm. The earth can keep turning without your help. You can rest. Sleep well, and good night.